gases through the plug is found by adding the forces due to pressures to those due to resistances, and equating these to the moving force, which in the case of slow motions may be neglected altogether. The result for the first is, making use of the simplifications we have just discovered, this becomes W, hence the rate of diffusion due to the motion of translation may be found. 4. To find the diffusion due to the motion of agitation, we must find the value of Q1. Similarly, the whole diffusions are Q1 plus Q1 and Q2 plus Q2. The values of Q1 and Q2 have a term not following Graham's law of the square roots of the specific gravities, but following the law of equal volumes. The closer the material of the plug, the less will this term affect the result. Our assumptions that the porous plug acts like a system of fixed particles, and that Graham's law is fulfilled more accurately the more compact the material of the plug, are scarcely sufficiently well verified for the foundation of a theory of gases, and even if we admit the original assumption that they are systems of moving elastic particles, we have not very good evidence as yet for the relation among the quantities A, B, C, and D. Prop. XX. To find the rate of diffusion between two vessels connected by a tube. When diffusion takes place through a large opening, such as a tube connecting two vessels, the question is simplified by the absence of the porous diffusion plug, and since the pressure is constant throughout the apparatus, the volumes of the two gases passing opposite ways through the tube at the same time must be equal. Now the quantity of gas which passes through the tube is due partly to the motion of agitation as in Prop. 14, and partly to the mean motion of translation as in Prop. 15. Let us suppose the volumes of the two vessels to be A and B, and the length of the tube between them C, and its transverse section S. Let A be filled with the first gas, and B with the second at the commencement of the experiment, and let the pressure throughout the apparatus be P. Let a volume Y of the first gas pass from A to B, and a volume Y of the second pass from B to A. Then if P1 and P2 represent the pressures in A due to the first and second kinds of gas, and P1 and P2 the same in the vessel B, since there is still equilibrium, which gives the rate of diffusion will be plus for the one gas, and, for the other, measured in volume of gas at pressure P. Now the rate of diffusion of the first gas will be, and that of the second. We have also the equation, derived from props 16 and 17. From these three equations we can eliminate V1 and V2, and find in terms of P and, so that we may write. Since the capacity of the tube is small compared with that of the vessels, we may consider constant through the whole length of the tube. We may then solve the differential equation in P and X, and then making P equals P1 when X equals 0, and P equals P1 when X equals C, and substituting for P1 and P1 their values in terms of Y, we shall have a differential equation in Y and T, which being solved, will give the amount of gas diffused in a given time. The solution of these equations would be difficult unless we assume relations among the quantities A, B, C, D, which are not yet sufficiently established in the case of gases of different density. Let us suppose that in a particular case the two gases have the same density, and that the four quantities A, B, C, D are all equal. The volume diffused, owing to the motion of agitation of the particles, is the NAND that due to the motion of translation, or the interpenetration of the two gases in opposite streams, is. The values of V are distributed according to the law of Prop. IV, so that the mean value of V is and that of K being A2. The diffusions due to these two causes are therefore in the ratio of 2 to 3, and their sum is. If we suppose constant throughout the tube, or, in other words, if we regard the motion as steady for a short time, then will be constant and equal to, or substituting from. Closing parenthesis. Whence, by choosing pairs of gases of equal density, and ascertaining the amount of diffusion in a given time, we might determine the value of L in this expression. The diffusion of nitrogen into carbonic oxide or of deutoxide of nitrogen into carbonic acid would be suitable cases for experiment. The only existing experiment which approximately fulfills the conditions is one by Graham, quoted by Herapath from Brand's Quarterly Journal of Science, Volume 18, page 76. A tube 9 inches long and 0.9 inch diameter, communicated with the atmosphere by a tube 2 inches long and 0.12 inch diameter, 152 parts of olefiant gas being placed in the tube, the quantity remaining after 4 hours was 99 parts. In this case there is not much difference of specific gravity between the gases, and we have cubic inches, B equals infinity, C equals 2 inches, and square inches. Prop. 21. To find the amount of energy which crosses unit of area in unit of time when the velocity of agitation is greater on one side of the area than on the other. The energy of a single particle is composed of two parts, the vis viva of the center of gravity, and the vis viva of the various motions of rotation round that center, or, if the particle be capable of internal motions, the vis viva of these. We shall suppose that the whole vis viva bears a constant proportion to that due to the motion of the center of gravity, or, where beta is a coefficient, the experimental value of which is 1/634. Substituting E for M in Prop. 14, we get for the transference of energy across unit of area in unit of time where J is the mechanical equivalent of heat in foot-pounds, and Q is the transfer of heat in thermal units. Also, if T is the absolute temperature, where P must be measured in dynamical units of force. Let J equals 772 foot-pounds, P equals 2,116 pounds to square foot, inch, V equals 1,505 feet per second, T equals 522 or 62 degrees Fahrenheit, then, where Q is the flow of heat in thermal units per square foot of area, and T are the temperatures at the two sides of a stratum of air x inches thick. In Professor Rankine's work on the steam engine, page 259, values of the thermal resistance, or the reciprocal of the conductivity, are given for various substances is computed from a table of conductivities deduced by M. Peclet from experiments by M. Despretz. It appears, therefore, that the resistance of a stratum of air to the conduction of heat is about 10 million times greater than that of a stratum of copper of equal thickness. It would be almost impossible to establish the value of the conductivity of a gas by direct experiment, as the heat radiated from the sides of the vessel would be far greater than the heat conducted through the air, even if currents could be entirely prevented. Part 3. On the collision of perfectly elastic bodies of any form. When two perfectly smooth spheres strike each other, the force which acts between them always passes through their centers of gravity, and therefore their motions of rotation, if they have any, are not affected by the collision, and do not enter into our calculations. But, when the bodies are not spherical, the force of compact will not, in general, be in the line joining their centers of gravity, and therefore the force of impact will depend both on the motion of the centers and the motions of rotation before impact, and it will affect both these motions after impact. In this way the velocities of the centers and the velocities of rotation will act and react on each other, so that finally there will be some relation established between them, and since the rotations of the particles about their three axes are quantities related to each other in the same way as the three velocities of their centers, the reasoning of Prop. IV will apply to rotation as well as velocity, and both will be distributed according to the law. Also, by Prop. V, if CC be TBE average velocity of one set of particles, and y that of another, T ben the average value of the sum or difference of the velocities is. From which it is easy to see that, if in each individual case, where x, y, z are independent quantities distributed according to the law above stated, then the average values of these quantities will be connected by the equation. Prop. 22. Two perfectly elastic bodies of any form strike each other, given their motions before impact, and the line of impact, to find their motions after impact. Let M1 and M2 be the centers of gravity of the two bodies. M1x1, M1y1, and M1z1 the principal axes of the first, and M2x2, M2y2 and M2z2 those of the second. Let I be the point of impact, and R1I R2 the line of impact. Let the coordinates of I with respect to M1 be x1 y1 z1, and with respect to M2 let them be x2 y2 z2. Let the direction cosines of the line of impact R1I R2 be L1 M1 N1 with respect to M1, and L2 square meters N2 with respect to M2. Let M1 and M2 be the masses, and A1 B1 C1 and A2 B2 C2 the moments of inertia of the bodies about the principal axes. Let the velocities of the centers of gravity, resolved in the direction of the principal axes of each body, be. And let the angular velocities round the same axes be. And let R be the impulsive force between the bodies, measured by the momentum it produces in each. Then, for the velocities of the centers of gravity, we have the following equations. with two other pairs of equations in V and W. The equations for the angular velocities are with two other pairs of equations for Q and R. The condition of perfect elasticity is that the whole vis viva shall be the same after impact as before, which gives the equation. The terms relating to the axis of x are here given. Those relating to y and z may be easily written down. Substituting the values of these terms, as given by equations 62 and 63, and dividing by r, we find. Now if version 1 be the velocity of the striking point of the first body before impact, resolved along the line of impact. And if we put v2 for the velocity of the other striking point resolved along the same line, and v1 and v2 the same quantities after impact, we may write equation 65. Or, which shows that the velocity of separation of the striking points resolved in the line of impact is equal to that of approach. Substituting the values of the accented quantities in equation 65, by means of equations 63 and 64, and transposing terms in R, we find the other terms being related to y and z as these are to x. From this equation we may find the value of R, and by substituting this in equations 63, 64, we may obtain the values of all the velocities after impact. We may, for example, find the value of u1 from the equation. Prop. 23. To find the relations between the average velocities of translation and rotation after many collisions among many bodies. Taking equation 69, which applies to an individual collision, we see that u1 is expressed as a linear function of u1, u2, p1, p2, and c, all of which are quantities of which the values are distributed among the different particles according to the law of Prop. IV. It follows from Prop. V, that if we square every term of the equation, we shall have a new equation between the average values of the different quantities. It is plain that, as soon as the required relations have been established, they will remain the same after collision, so that we may put u12 equals u12 in the equation of averages. The equation between the average values may then be written. Now since there are collisions in every possible way, so that the values of L, M, N, and C, and X, Y, Z, and C, are infinitely varied, this equation cannot subsist unless the final state, therefore, of any number of systems of moving particles of any form is that in which the average vis viva of translation along each of the three axes is the same in all the systems, and equal to the average vis viva of rotation about each of the three principal axes of each particle. Adding the vis vivce with respect to the other axes, we find that the whole vis viva of translation is equal to that of rotation in each system of particles, and is also the same for different systems, as was proved in Prop. Vi. This result, which is true, however nearly the bodies approach the spherical form, provided the motion of rotation is at all affected by the collisions, seems decisive against the unqualified acceptation of the hypothesis that gases are such systems of hard elastic particles. For the ascertained fact that gamma, the ratio of the specific heat at constant pressure to that at constant volume, is equal to 1/408, requires that the ratio of the whole vis viva to the vis viva of translation should be. Whereas, according to our hypothesis, beta equals 2. We have now followed the mathematical theory of the collisions of hard elastic particles through various cases, in which there seems to be an analogy with the phenomena of gases. We have deduced, as others have done already, the relations of pressure, temperature, and density of a single gas. We have also proved that when two different gases act freely on each other, that is, when at the same temperature, the mass of the single particles of each is inversely proportional to the square of the molecular velocity, and therefore, at equal temperature and pressure, the number of particles in unit of volume is the same. We then offered an explanation of the internal friction of gases, and deduced from experiments a value of the mean length of path of a particle between successive collisions. We have applied the theory to the law of diffusion of gases, and, from an experiment on olefin gas, we have deduced a value of the length of path not very different from that deduced from experiments on friction. Using this value of the length of path between collisions, we found that the resistance of air to the conduction of heat is 10 million times that of copper, a result in accordance with experience. Finally, by establishing a necessary relation between the motions of translation and rotation of all particles not spherical, we proved that a system of such particles could not possibly satisfy the known relation between the two specific heats of all gases. Read at the meeting of the British Association at Aberdeen, September 21, 1859. In the Philosophical Magazine of 1860, Volume 1 pp. 434-6 Clausius explains the method by which he found his value of the mean relative velocity. It is briefly as follows. If u, v be the velocities of two particles, their relative velocity is, and the mean of this as regards direction only, all directions of v being equally probable, is shown to be. If v equals u, these expressions coincide. Clausius, in applying this result and putting u, v for the mean velocities, assumes that the mean relative velocity is given by expressions of the same form, so that when the mean velocities are each equal to u, the mean relative velocity would be u. This step is, however, open to objection, and in fact, if we take the expressions given above for the mean velocity, treating u and v as the velocities of two particles which may have any values between 0 and infinity, to calculate the mean relative velocity we should proceed as follows. Since the number of particles with velocities between u and u plus do is the mean relative velocity is. This expression, when reduced, leads to which is the result in the text. Ed. The methods and results of this paper have been criticized by Clausius in a memoir published in Poggendorff's Annalen, Volume CXV, and in the Philosophical Magazine, Volume 23. His main objection is that the various circumstances of the strata, discussed in the paper, have not been sufficiently represented in the equations. In particular, if there be a series of strata at different temperatures perpendicular to the axis of x, then the proportion of molecules whose directions form with the axis of x angles whose cosines lie between mu and mu plus d mu is not d mu as has been assumed by Maxwell throughout his work, but h d mu, where h is a factor to be determined. In discussing the steady conduction of heat through a gas, Clausius assumes that, in addition to the velocity attributed to the molecule according to Maxwell's theory, we must also suppose a velocity normal to the stratum and depending on the temperature of the stratum. On this assumption, the factor h is investigated along with other modifications, and an expression for the assumed velocity is determined from the consideration that when the flow of heat is steady there is no movement of the mass. Clausius, combining his own results with those of Maxwell, points out that the expression contained in 28 of the paper involves as a result the motion of the gas. He also disputes the accuracy of expression 59 for the conduction of heat. In the introduction to the memoir published in the Phil. Trans. 1866, it will be found that Maxwell expresses dissatisfaction with his former theory of the diffusion of gases, and admits the force of the objections made by Clausius to his expression for the conduction of heat. Ed. Clausius, in the memoir cited in the last footnote, has pointed out two oversights in this calculation. In the first place, the numbers have not been properly reduced to English measure, and have still to be multiplied by 4356, the ratio of the English pound to the kilogram. The numbers have, further, been calculated with 1 hour as the unit of time, whereas Maxwell has used them as if a second had been the unit. Taking account of these circumstances and using his own expression for the conduction, which differs from 59 only in having in place of on the right-hand side, Clausius finds that the resistance of a stratum of air to the conduction of heat is 1400 times greater than that of a stratum of lead of the same thickness, or about 7000 times greater than that of copper. Ed. From the Philosophical Transactions, MDCCCLX. 21. On the theory of compound colors, and the relations of the colors of the spectrum. Communicated by Professor Stokes, Sec. U.S. Received January 5, read March 22, 1860. Section I. Introduction. According to Newton's analysis of light *, every color in nature is produced by the mixture, in various proportions, of the different kinds of light into which white light is divided by refraction. By means of a prism we may analyze any colored light, and determine the proportions in which the different homogeneous rays enter into it, and by means of a lens we may recombine these rays, and reproduce the original colored light. Newton has also shown how to combine the different rays of the spectrum so as to form a single beam of light, and how to alter the proportions of the different colors so as to exhibit the result of combining them in any arbitrary manner. The number of different kinds of homogeneous light being infinite, and the proportion in which each may be combined being also variable indefinitely, the results of such combinations could not be appreciated by the eye, unless the chromatic effect of every mixture, however complicated, could be expressed in some simpler form. Colors, as seen by the human eye of the normal type, can all be reduced to a few classes, and expressed by a few well-known names, and even those colors which have different names have obvious relations among themselves. Every color, except purple, is similar to some color of the spectrum, although less intense, and all purples may be compounded of blue and red, and diluted with white to any required tint. Brown colors, which at first sight seem different, are merely red, orange or yellow of feeble intensity, more or less diluted with white. It appears therefore that the result of any mixture of colors, however complicated, may be defined by its relation to a certain small number of well-known colors. Having selected our standard colors, and determined the relations of a given color to these, we have defined that color completely as to its appearance. Any color which has the same relation to the standard colors, will be identical in appearance, though its optical constitution, as revealed by the prism, may be very different. We may express this by saying that two compound colors may be chromatically identical, but optically different. The optical properties of light are those which have reference to its origin and propagation through media, till it falls on the sensitive organ of vision. The chromatical properties of light are those which have reference to its power of exciting certain sensations of color, perceived through the organ of vision. The investigation of the chromatic relations of the rays of the spectrum must therefore be founded upon observations of the apparent identity of compound colors, as seen by an eye either of the normal or of some abnormal type, and the results to which the investigation leads must be regarded as partaking of a physiological, as well as of a physical character, and as indicating certain laws of sensation, depending on the constitution of the organ of vision, which may be different in different individuals. We have to determine the laws of the composition of colors in general, to reduce the number of standard colors to the smallest possible, to discover, if we can, what they are, and to ascertain the relation which the homogeneous light of different parts of the spectrum bears to the standard colors. Section 2. History of the theory of compound colors. The foundation of the theory of the composition of colors was laid by Newton. He first shows that, by the mixture of homogeneal light, colors may be produced which are like to the colors of homogeneal light as to the appearance of color, but not as to the immutability of color and constitution of light. Red and yellow give an orange color, which is chromatically similar to the orange of the spectrum, but optically different, because it is resolved into its component colors by a prism, while the orange of the spectrum remains unchanged. When the colors to be mixed lie at a distance from one another in the spectrum, the resultant appears paler than that intermediate color of the spectrum which it most resembles, and when several are mixed, the resultant may appear white. Newton is always careful, however, not to call any mixture white, unless it agrees with common white light in its optical as well as its chromatical properties, and is a mixture of all the homogeneal colors. The theory of compound colors is first presented in a mathematical form in Prop. 6, in a mixture of primary colors, the quantity and quality of each being given, to know the color of the compound. He divides the circumference of a circle into 7 parts, proportional to the 7 musical intervals, in accordance with his opinion about the proportions of the colors in the spectrum. At the center of gravity of each of these arcs he places a little circle, whose area is proportional to the number of rays of the corresponding color which enter into the given mixture. The position of the center of gravity of all these circles indicates the nature of the resultant color. A radius drawn through it points out the color of the spectrum which it most resembles, and the distance from the center determines the fullness of its color. With respect to this construction, Newton says, "This rule I conceive accurate enough for practice, though not mathematically accurate." He gives no reasons for the different parts of his rule, but we shall find that his method of finding the center of gravity of the component colors is completely confirmed by my observations, and that it involves mathematically the theory of 3 elements of color, but that the disposition of the colors on the circumference of a circle was only a provisional arrangement, and that the true relations of the colors of the spectrum can only be determined by direct observation. Young appears to have originated the theory that the 3 elements of color are determined as much by the constitution of the sense of sight as by anything external to us. He conceives that 3 different sensations may be excited by light, but that the proportion in which each of the 3 is excited depends on the nature of the light. He conjectures that these primary sensations correspond to red, green, and violet. A blue ray, for example, though homogeneous in itself, he conceives capable of exciting both the green and the violet sensation, and therefore he would call blue a compound color, though the color of a simple kind of light. The quality of any color depends, according to this theory, on the ratios of the intensities of the 3 sensations which it excites, and its brightness depends on the sum of these three intensities. Sir David Brewster, in his paper entitled, On a New Analysis of Solar Light, indicating three primary colors, forming coincident spectra of equal length *, regards the actual colors of the spectrum as arising from the intermixture, in various proportions, of three primary kinds of light, red, yellow, and blue, each of which is variable in intensity, but uniform in color, from one end of the spectrum to the other, so that every color in the spectrum is really compound, and might be shown to be so if we had the means of separating its elements. Sir David Brewster, in his researches, employed colored media, which, according to him, absorb the three elements of a single prismatic color in different degrees, and change their proportions, so as to alter the color of the light, without altering its refrangibility. In this paper I shall not enter into the very important questions affecting the physical theory of light, which can only be settled by a careful inquiry into the phenomena of absorption. The physiological facts, that we have a threefold sensation of color, and that the three elements of this sensation are affected in different proportions by light of different refrangibilities, are equally true, whether we adopt the physical theory that there are three kinds of light corresponding to these three color sensations, or whether we regard light of definite refrangibility as an undulation of known length, and therefore variable only in intensity, but capable of producing different chemical actions on different substances, of being absorbed in different degrees by different media, and of exciting in different degrees the three different color sensations of the human eye. Sir David Brewster has given a diagram of three curves, in which the baseline represents the length of the spectrum, and the ordinates of the curves represent, by estimation, the intensities of the three kinds of light at each point of the spectrum. I have employed a diagram of the same kind to express the results arrived at in this paper, the ordinates being made to represent the intensities of each of the three elements of color, as calculated from the experiments. The most complete series of experiments on the mixture of the colors of the spectrum is that of Professor Helmholtz** of Königsberg. By using two slits at right angles to one another, he formed two pure spectra, the fixed lines of which were seen crossing one another when viewed in the ordinary way by means of a telescope. The colors of these spectra were thus combined in every possible way, and the effect of the combination of any two could be seen separately by drawing the eye back from the eyepiece of the telescope, when the compound color was seen by itself at the eye hole. The proportion of the components was altered by turning the combined slits round in their own plane. One result of these experiments was that a color, chromatically identical with white, could be formed by combining yellow with indigo. Helmholtz was not then able to produce white with any other pair of simple colors, and considered that three simple colors were required in general to produce white. One from each of the three portions into which the spectrum is divided by the yellow and indigo. Professor Grassmann showed that Newton's theory of compound colors implies that there are an infinite number of pairs of complementary colors in the spectrum, and pointed out the means of finding them. He also showed how colors may be represented by lines, and combined by the method of the parallelogram. In a second memoir, Helmholtz describes his method of ascertaining these pairs of complementary colors. He formed a pure spectrum by means of a slit, a prism, and a lens, and in this spectrum he placed an apparatus having two parallel slits which were capable of adjustment both in position and breadth, so as to let through any two portions of the spectrum, in any proportions. Behind this slit, these rays were united in an image of the prism, which was received on paper. By arranging the slits, the color of this image may be reduced to white, and made identical with that of paper illuminated with white light. The wavelengths of the component colors were then measured by observing the angle of diffraction through a grating. It was found that the colors from red to green-yellow, lambda equals 2082, were complementary to colors ranging from green-blue, lambda equals 1818, to violet, and that the colors between green-yellow and green-blue have no homogeneous complementaries, but must be neutralized by mixtures of red and violet. Helmholtz also gives a provisional diagram of the curve formed by the spectrum on Newton's diagram, for which his experiments did not furnish him with the complete data. Accounts of experiments by myself on the mixture of artificial colors by rapid rotation may be found in the Transactions of the Royal Society of Edinburgh, Volume 21, Part 2. 1855, in an appendix to Professor George Wilson's work on color blindness, in the Report of the British Association for 1856, page 12, and in the Philosophical Magazine, July 1857, page 40. These experiments show that, for the normal eye, there are three, and only 3 elements of color, and that in the color-blind one of these is absent. They also prove that chromatic observations may be made, both by normal and abnormal eyes, with such accuracy as to warrant the employment of the results in the calculation of color equations, and in laying down color diagrams by Newton's rule. The first instrument which I made, in 1852, to examine the mixtures of the colors of the spectrum was similar to that which I now use, but smaller, and it had no constant light for a term of comparison. The second was 6 feet long, made in 1855, and showed 2 combinations of color side by side. I have now succeeded in making the mixture much more perfect, and the comparisons more exact, by using white reflected light, instead of the second compound color. An apparatus in which the light passes through the prisms, and is reflected back again in nearly the same path by a concave mirror, was shown by me to the British Association in 1856. It has the advantage of being portable, and need not be more than half the length of the other, in order to produce a spectrum of equal length. I am so well satisfied with the working of this form of the instrument, that I intend to make use of it in obtaining equations from a greater variety of observers than I could meet with when I was obliged to use the more bulky instrument. It is difficult at first to get the observer to believe that the compound light can ever be so adjusted as to appear to his eyes identical with the white light in contact with it. He has to learn what adjustments are necessary to produce the requisite alteration under all circumstances, and he must never be satisfied till the 2 parts of the field are identical in color and illumination. To do this thoroughly implies not merely good eyes, but a power of judging as to the exact nature of the difference between 2 very pale and nearly identical tints, whether they differ in the amount of red, green, or blue, or in brightness of illumination. In the following paper I shall first lay down the mathematical theory of Newton's diagram, with its relation to Young's theory of the color sensation. I shall then describe the experimental method of mixing the colors of the spectrum, and determining the wavelengths of the colors mixed. The results of my experiments will then be given, and the chromatic relations of the spectrum exhibited in a system of color equations, in Newton's diagram, and in 3 curves of intensity, as in Brewster's diagram. The differences between the results of 2 observers will then be discussed, showing on what they depend, and in what way such differences may affect the vision of persons otherwise free from defects of sight. Section 3. Mathematical theory of Newton's diagram of colors. Newton's diagram is a plane figure, designed to exhibit the relations of colors to each other. Every point in the diagram represents a color, simple or compound, and we may conceive the diagram itself so painted, that every color is found at its corresponding point. Any color, differing only in quantity of illumination from one of the colors of the diagram, is referred to it as a unit, and is measured by the ratio of the illumination of the given color to that of the corresponding color in the diagram. In this way the quantity of a color is estimated. The resultant of mixing any 2 colors of the diagram is found by dividing the line joining them inversely as the quantity of each. Then, if the sum of these quantities is unity, the resultant will have the illumination as well as the color of the point so found, but if the sum of the components is different from unity, the quantity of the resultant will be measured by the sum of the components. This method of determining the position of the resultant color is mathematically identical with that of finding the center of gravity of 2 weights, and placing a weight equal to their sum at the point so found. We shall therefore speak of the resultant tint as the sum of its components placed at their center of gravity. By compounding this resultant tint with some other color, we may find the position of a mixture of 3 colors, at the center of gravity of its components, and by taking these components in different proportions, we may obtain colors corresponding to every part of the triangle of which they are the angular points. In this way, by taking any 3 colors we should be able to construct a triangular portion of Newton's diagram by painting it with mixtures of the 3 colors. Of course these mixtures must be made to correspond with optical mixtures of light, not with mechanical mixtures of pigments. Let us now take any color belonging to a point of the diagram outside this triangle. To make the center of gravity of the 3 weights coincide with this point, 1 or more of the weights must be made negative. This, though following from mathematical principles, is not capable of direct physical interpretation, as we cannot exhibit a negative color. The equation between the 3 selected colors, X, Y, Z, and the new color U, may in the first case be written X, Y, Z being the quantities of color required to produce U. In the second case suppose that Z must be made negative. As we cannot realize the term Z as a negative color, we transpose it to the other side of the equation, which then becomes, which may be interpreted to mean that the resultant tint, U plus Z, is identical with the resultant, X plus Y. We thus find a mixture of the new color with one of the selected colors, which is chromatically equivalent to a mixture of the other two selected colors. When the equation takes the form, two of the components being negative, we must transpose them thus. Which means that a mixture of certain proportions of the new color and two of the three selected, is chromatically equivalent to the third. We may thus in all cases find the relation between any three colors and the fourth, and exhibit this relation in a form capable of experimental verification, and by proceeding in this way we may map out the positions of all colors upon Newton's diagram. Every color in nature will then be defined by the position of the corresponding color in the diagram, and by the ratio of its illumination to that of the color in the diagram. Section IV. Method of representing colors by straight lines drawn from a point. To extend our ideas of the relations of colors, let us form a new geometrical conception by the aid of solid geometry. Let us take as origin any point not in the plane of the diagram, and let us draw lines through this point to the different points of the diagram. Then the direction of any of these lines will depend upon the position of the point of the diagram through which it passes, so that we may take this line as the representative of the corresponding color on the diagram. In order to indicate the quantity of this color, let it be produced beyond the plane of the diagram in the same ratio as the given color exceeds in illumination the color on the diagram. In this way every color in nature will be represented by a line drawn through the origin, whose direction indicates the quality of the color, while its length indicates its quantity. Let us find the resultant of two colors by this method. Let O be the origin and AB be a section of the plane of the diagram by that of the paper. Let OP, OQ be lines representing colors, A, B the corresponding points in the diagram, then the quantity of P will be and that of Q will be. The resultant of these will be represented in the diagram by the point C, where AC, CB, Q, P, and the quantity of the resultant will be P plus Q, so that if we produce OC to R, so that OR equals P plus Q, OC, the line OR will represent the resultant of OP and OQ in direction and magnitude. It is easy to prove, from this construction, that OR is the diagonal of the parallelogram of which OP and OQ are two sides. It appears therefore that if colors are represented in quantity and quality by the magnitude and direction of straight lines, the rule for the composition of colors is identical with that for the composition of forces in mechanics. This analogy has been well brought out by Professor Grassmann in Poggendorff's aniline, BD. LXXXIX. We may conceive an arrangement of actual colors in space founded upon this construction. Suppose each of these radiating lines representing a given color to be itself illuminated with that color, the brightness increasing from 0 at the origin to unity, where it cuts the plane of the diagram, and becoming continually more intense in proportion to the distance from the origin. In this way every color in nature may be matched, both in quality and quantity, by some point in this colored space. If we take any three lines through the origin as axes, we may, by coordinates parallel to these lines, express the position of any point in space. That point will correspond to a color which is the resultant of the three colors represented by the three coordinates. This system of coordinates is an illustration of the resolution of a color into three components. According to the theory of Young, the human eye is capable of three distinct primitive sensations of color, which by their composition in various proportions, produce the sensations of actual color in all their varieties. Whether any kinds of light have the power of exciting these primitive sensations separately, has not yet been determined. If colors corresponding to the three primitive sensations can be exhibited, then all colors, whether produced by light, disease, or imagination, are compounded of these, and have their places within the triangle formed by joining the three primaries. If the colors of the pure spectrum, as laid down on the diagram, form a triangle, the colors at the angles may correspond to the primitive sensations. If the curve of the spectrum does not reach the angles of the circumscribing triangle, then no color in the spectrum, and therefore no color in nature, corresponds to any of the three primary sensations. The only data at present existing for determining the primary colors are derived from the comparison of observations of color equations by color-blind and by normal eyes. The color-blind equations differ from the others by the non-existence of one of the elements of color, the relation of which to known colors can be ascertained. It appears, from observations made for me by two color-blind persons *, that the elementary sensation which they do not possess is a red approaching to crimson, lying beyond both vermilion and carmine. These observations are confirmed by those of Mr. Pole, and by others which I have obtained since. I have hopes of being able to procure a set of color-blind equations between the colors of the spectrum, which will indicate the missing primary in a more exact manner. The experiments which I am going to describe have for their object the determination of the position of the colors of the spectrum upon Newton's diagram, from actual observations of the mixtures of those colors. They were conducted in such a way, that in every observation the judgment of the observer was exercised upon two parts of an illuminated field, one of which was so adjusted as to be chromatically identical with the other, which, during the whole series of observations, remained of one constant intensity of white. In this way the effects of subjective colors were entirely got rid of, and all the observations were of the same kind, and therefore may claim to be equally accurate, which is not the case when comparisons are made between bright colors of different kinds. The chart of the spectrum, deduced from these observations, exhibits the colors arranged very exactly along two sides of a triangle, the extreme red and violet forming doubtful portions of the third side. This result greatly simplifies the theory of color, if it does not actually point out the three primary colors themselves. Section V. Description of an instrument for making definite mixtures of the colors of the spectrum. The experimental method which I have used consists in forming a combination of three colors belonging to different portions of the spectrum, the quantity of each being so adjusted that the mixture shall be white, and equal in intensity to a given white. Fig. 1, Plate Vi. Page 444, represents the instrument for making the observations. It consists of two tubes, or long boxes, of deal, of rectangular section, joined together at an angle of about 100 degrees. The part AK is about 5 feet long, 7 inches broad, and 4 deep. Knots is about 2 feet long, 5 inches broad, and 4 deep. BD is a partition parallel to the side of the long box. The whole of the inside of the instrument is painted black, and the only openings are at the end AC, and at E. At the angle there is a lid, which is opened when the optical parts have to be adjusted or cleaned. At E is a fine vertical slit, L is a lens, at P there are two equilateral prisms. The slit E, the lens L, and the prisms P are so adjusted, that when light is admitted at E a pure spectrum is formed at AB, the extremity of the long box. A mirror at M is also adjusted so as to reflect the light from E along the narrow compartment of the long box to BC. See Fig. 3. At AB is placed the contrivance shown in Fig. 2. Plate IB is a rectangular frame of brass, having a rectangular aperture of 6 times 1 inch. On this frame are placed 6 brass sliders, X, Y, Z. Each of these carries a knife edge of brass in the plane of the surface of the frame. These 6 movable knife edges form 3 slits, X, Y, Z, which may be so adjusted as to coincide with any 3 portions of the pure spectrum formed by light from E. The intervals behind the sliders are closed by hinged shutters, which allow the sliders to move without letting light pass between them. The inner edge of the brass frame is graduated to 1/20ths of an inch, so that the position of any slit can be read off. The breadth of the slit is ascertained by means of a wedge-shaped piece of metal, 6 inches long, and tapering to a point from a breadth of ½ an inch. This is gently inserted into each slit, and the breadth is determined by the distance to which it enters, the divisions on the wedge corresponding to the 200th of an inch difference in breadth, so that the unit of breadth is 0.05 inch. Now suppose light to enter at E, to pass through the lens, and to be refracted by the 2 prisms at P. A pure spectrum, showing Fraunhofer's lines, is formed at AB, but only that part is allowed to pass which falls on the 3 slits X, Y, Z. The rest is stopped by the shutters. Suppose that the portion falling on X belongs to the red part of the spectrum, then, of the white light entering at E, only the red will come through the slit X. If we were to admit red light at X, it would be refracted to E, by the principle in optics, that the course of any ray may be reversed. If, instead of red light, we were to admit white light at X, still only red light would come to E, for all other light would be either more or less refracted, and would not reach the slit at E. Applying the eye at the slit E, we should see the prism P uniformly illuminated with red light, of the kind corresponding to the part of the spectrum which falls on the slit X. When light is admitted at E, let the slit Y correspond to another portion of the spectrum, say the green. Then, if white light is admitted at Y, the prism, as seen by an eye at E, will be uniformly illuminated with green light, and if white light be admitted at X and Y simultaneously, the color seen at E will be a compound of red and green, the proportions depending on the breadth of the slits and the intensity of the light which enters them. The third slit Z enables us to combine any three kinds of light in any given proportions, so that an eye at E shall see the face of the prism at P uniformly illuminated with the color resulting from the combination of the three. The position of these three rays in the spectrum is found by admitting the light at E, and comparing the position of the slits with the position of the principal fixed lines, and the breadth of the slits is determined by means of the wedge. At the same time, white light is admitted through BC to the mirror of black glass at M, whence it is reflected to E, past the edge of the prism at P, so that the eye at E sees through the lens a field consisting of two portions, separated by the edge of the prism, that on the left hand being compounded of three colors of the spectrum refracted by the prism, while that on the right hand is white light reflected from the mirror. By adjusting the slits properly, these two portions of the field may be made equal, both in color and brightness, so that the edge of the prism becomes almost invisible. In making experiments, the instrument was placed on a table in a room moderately lighted, with the end AB turned towards a large board covered with white paper, and placed in the open air, so as to be uniformly illuminated by the sun. In this way the three slits and the mirror M were all illuminated with white light of the same intensity, and all were affected in the same ratio by any change of illumination, so that if the two halves of the field were rendered equal when the sun was under a cloud, they were found nearly correct when the sun again appeared. No experiments, however, were considered good unless the sun remained uniformly bright during the whole series of experiments. After each set of experiments, light was admitted at E, and the position of the fixed lines D and F of the spectrum was read off on the scale at AB. It was found that after the instrument had been some time in use these positions were invariable, showing that the eye hole, the prisms, and the scale might be considered as rigidly connected. Section VI. Method of determining the wavelength corresponding to any point of the spectrum on the scale AB. Two plane surfaces of glass were kept apart by two parallel strips of goldbeater's leaf, so as to enclose a stratum of air of nearly uniform thickness. Light reflected from this stratum of air was admitted at E, and the spectrum formed by it was examined at AB by means of a lens. This spectrum consists of a large number of bright bands, separated by dark spaces at nearly uniform intervals, these intervals, however, being considerably larger as we approach the violet end of the spectrum. The reason of these alternations of brightness is easily explained. By the theory of Newton's rings, the light reflected from a stratum of air consists of two parts, one of which has traversed a path longer than that of the other, by an interval depending on the thickness of the stratum and the angle of incidence. Whenever the interval of retardation is an exact multiple of a wavelength, these two portions of light destroy each other by interference, and when the interval is an odd number of half wavelengths, the resultant light is a maximum. In the ordinary case of Newton's rings, these alternations depend upon the varying thickness of the stratum, while in this case a pencil of rays of different wavelengths, but all experiencing the same retardation, is analyzed into a spectrum, in which the rays are arranged in order of their respective wavelengths. Every ray whose wavelength is an exact submultiple of the retardation will be destroyed by interference, and its place will appear dark in the spectrum, and there will be as many dark bands seen as there are rays whose wavelengths fulfill this condition. If, then, we observe the positions of the dark bands on the scale AB, the wavelengths corresponding to these positions will be a series of submultiples of the retardation. Let us call the first dark band visible on the red side of the spectrum 0, and let us number them in order 1, 2, 3, and C, towards the violet end. Let n be the number of undulations corresponding to the band 0 which are contained in the retardation R, then if n be the number of any other band, n plus n will be the number of the corresponding wavelengths in the retardation, or in symbols. Now observe the position of two of Fraunhofer's fixed lines with respect to the dark bands, and let n1, n2 be their positions expressed in the number of bands, whole or fractional, reckoning from 0. Let lambda 1, lambda 2 be the wavelengths of these fixed lines as determined by Fraunhofer, then whence, and having thus found n and r, we may find the wavelength corresponding to the dark band n from the formula. In my experiments the line D corresponded with the 7th dark band, and F was between the 15th and 16th, so that N2 equals 15.7. Here then for D, and for F, whence we find there were 22 bands visible, corresponding to 22 different positions on the scale AB, as determined the 4th of August 1859. Table I. 16 equidistant points on the scale were chosen for standard colors in the experiments to be described. The following table gives the reading on the scale AB, the value of n plus n, and the calculated wavelength for each of these. Table 2. Having thus selected 16 distinct points of the spectrum on which to operate, and determined their wavelengths and apparent colors, I proceeded to ascertain the mathematical relations between these colors in order to lay them down on Newton's diagram. For this purpose I selected 3 of these as points of reference, namely, those at 24, 44, and 68 of the scale. I chose these points because they are well separated from each other on the scale, and because the color of the spectrum at these points does not appear to the eye to vary very rapidly, either in hue or brightness, in passing from one point to another. Hence a small error of position will not make so serious an alteration of color at these points, as if we had taken them at places of rapid variation, and we may regard the amount of the illumination produced by the light entering through the slits in these positions as sensibly proportional to the breadth of the slits. 24 corresponds to a bright scarlet about 1/3 of the distance from C to D, 44 is a green very near the line E, and 68 is a blue about 1/3 of the distance from F to G. Section 7. Method of observation. The instrument is turned with the end AB towards a board, covered with white paper, and illuminated by sunlight. The operator sits at the end AB, to move the sliders, and adjust the slits, and the observer sits at the end E, which is shaded from any bright light. The operator then places the slits so that their centers correspond to the 3 standard colors, and adjusts their breadths till the observer sees the prism illuminated with pure white light of the same intensity with that reflected by the mirror M. In order to do this, the observer must tell the operator what difference he observes in the 2 halves of the illuminated field, and the operator must alter the breadth of the slits accordingly, always keeping the center of each slit at the proper point of the scale. The observer may call for more or less red, blue or green, and then the operator must increase or diminish the width of the slits X, Y, and Z respectively. If the variable field is darker or lighter than the constant field, the operator must widen or narrow all the slits in the same proportion. When the variable part of the field is nearly adjusted, it often happens that the constant white light from the mirror appears tinged with the complementary color. This is an indication of what is required to make the resemblance of the 2 parts of the field of view perfect. When no difference can be detected between the 2 parts of the field, either in color or in brightness, the observer must look away for some time, to relieve the strain on the eye, and then look again. If the eye thus refreshed still judges the 2 parts of the field to be equal, the observation may be considered complete, and the operator must measure the breadth of each slit by means of the wedge, as before described, and write down the result as a color equation, thus. October 18th, J. This equation means that on the 18th of October the observer J, myself, made an observation in which the breadth of the slit X was 18.5, as measured by the wedge, while its center was at the division, 24, of the scale, that the breadths of Y and Z were 27 and 37, and their positions, 44, and 68. And that the illumination produced by these slits was exactly equal, in my estimation as an observer, to the constant white W. The position of the slit X was then shifted from 24 to 28, and when the proper adjustments were made, I found a second color equation of this form. October 18th, J. Subtracting one equation from the other and remembering that the figures in brackets are merely symbols of position, not of magnitude, we find. Showing that 28 can be made up of 24 and 44 in the proportion of 18.5 to 6. In this way, by combining each color with 2 standard colors, we may produce a white equal to the constant white. The red and yellow colors from 20 to 32 must be combined with green and blue, the greens from 36 to 52 with red and blue, and the blues from 56 to 80 with red and green. The following is a specimen of an actual series of observations made in this way by another observer, K. Table 3. The equations marked with an asterisk are those which involve the 3 standard colors, and since every other equation must be compared with them, they must be often repeated. The following table contains the means of 4 sets of observations by the same observer, K. Table IV. K. Section 8. Determination of the average error in observations of different kinds. In order to estimate the degree of accuracy of these observations, I have taken the differences between the values of the three standard colors as originally observed, and their means as given by the above table. The sum of all the errors of the red, 24, from the means, was 31,1, and the number of observations was 42, which gives the average error 74. The sum of errors in green, 44, was 48,0, and the number of observations 31, giving a mean error 155. The sum of the errors in blue, 68, was 46,9, and the number of observations 35, giving a mean error 116. It appears therefore that in the observations generally, the average error does not exceed 1.5, and therefore the results, if confirmed by several observations, may safely be trusted to that degree of accuracy. The equation between the three standard colors was repeatedly observed, in order to detect any alteration in the character of the light, or any other change of condition which would prevent the observations from being comparable with one another, and also because this equation is used in the reduction of all the others, and therefore requires to be carefully observed. There are 20 observations of this equation, the mean of which gives as the standard equation. We may use the 20 observations of this equation as a means of determining the relations between the errors in the different colors, and thus of estimating the accuracy of the observer in distinguishing colors. The following table gives the result of these operations, where it stands for 24, G for 44, and B for 68. Table V, mean errors in the standard equation. The first column gives the mean difference between the observed value of each of the colors and the mean of all the observations. The second column shows the average error of the observed differences between the values of the standards, from the mean value of those differences. The third column shows the average error of the sums of two standards, from the mean of such sums. The fourth column gives the square root of the sum of the squares of the quantities in the first column. I have also given the average error of the sum of B, G and B, from its mean value, and the value of it appears from the first column that the red is more accurately observed than the green and blue. Section X. Relative accuracy in observations of color and of brightness. If the errors in the different colors occurred perfectly independent of each other, then the probable mean error in the sum or difference of any two colors would be the square root of the sum of their squares, as given in the fourth column. It will be seen, however, that the number in the second column is always less, and that in the third always greater, than that in the fourth, showing that the errors are not independent of each other, but that positive errors in any color coincide more often with positive than with negative errors in another color. Now the hue of the resultant depends on the ratios of the components, while its brightness depends on their sum. Since, therefore, the difference of two colors is always more accurately observed than their sum, variations of color are more easily detected than variations in brightness, and the eye appears to be a more accurate judge of the identity of color of the two parts of the field than of their equal illumination. The same conclusion may be drawn from the value of the mean error of the sum of the three standards, which is 267, while the square root of the sum of the squares of the errors is 176. Section X. Reduction of the observations. By eliminating W from the equations of page 428 by means of the standard equation, we obtain equations involving each of the 14 selected colors of the spectrum, along with the three standard colors, and by transposing the selected color to one side of the equation, we obtain its value in terms of the three standards. If any of the terms of these equations are negative, the equation has no physical interpretation as it stands, but by transposing the negative term to the other side it becomes positive, and then the equation may be verified. The following table contains the values of the 14 selected tints in terms of the standards. To avoid repetition, the symbols of the standard colors are placed at the head of each column. Table VI. From these equations we may lay down a chart of the spectrum on Newton's diagram by the following method. Take any 3 points, A, B, C, and let A represent the standard color, 24, B, 44, and C, 68. Then, to find the position of any other color, say, 20, divide AC in P so that, 18,6, AP equals, 28, PC, and then divide BP in Q so that, 18,6 plus 28, PQ equals, 0,4, QB. At the point Q the color corresponding to, 20, must be placed. In this way the diagram of Fig. 4, Plate VI, page 444, has been constructed from the observations of all the colors. Section 11. The spectrum as laid down on Newton's diagram. The curve on which these points lie has this striking feature, that two portions of it are nearly, if not quite, straight lines. One of these portions extends from 24 to 46, and the other from 48 to 64. The color, 20, and those beyond, 64, are not far from the line joining 24 and 68. The spectrum, therefore, as exhibited in Newton's diagram, forms two sides of a triangle, with doubtful fragments of the third side. Now if three colors in Newton's diagram lie in a straight line, the middle one is a compound of the two others. Hence all the colors of the spectrum may be compounded of those which lie at the angles of this triangle. These correspond to the following colors. Table 7. All the other colors of the spectrum may be produced by combinations of these, and since all natural colors are compounded of the colors of the spectrum, they may be compounded of these three primary colors. I have strong reason to believe that these are the three primary colors corresponding to three modes of sensation in the organ of vision, on which the whole system of color, as seen by the normal eye, depends. Section 12. Results found by a second observer. We may now consider the results of three series of observations made by myself, J, as observer, in order to determine the relation of one observer to another in the perception of color. The standard colors are connected by the following equation, as determined by 6 observations. The average errors in these observations were Table 8, showing that in this case, also, the power of distinguishing color is more to be depended on than that of distinguishing degrees of illumination. The average error in the other observations from the means was 64 for red, 76 for green, and 102 for blue. Table IX. Observations by J, October 1859. Section 13. Comparison of results by Newton's diagram. The relations of the colors, as given by these observations, are laid down in Fig. 5, Plate V, page 444. It appears from this diagram that the positions of the colors lie nearly in a straight line from 24 to 44, and from 48 to 60. The colors beyond 60 are crowded together, as in the other diagram, and the observations are not yet sufficiently accurate to distinguish their relative positions accurately. The color, 20, at the red end of the spectrum is further from the line joining 24 and 68 than in the other diagram, but I have not obtained satisfactory observations of these extreme colors. It will be observed that 32, 36, and 40 are placed further to the right in Fig. 5 than in Fig. 4, showing that the second observer, J, sees more green in these colors than the first, K, also that 48, 52, 56, and 60 are much further up in Fig. 5, showing that to the second observer they appear more blue and less green. These differences were well seen in making an observation. When the instrument was adjusted to suit the first observer, K, then, if the selected color were 32, 36, or 40, the second, J, on looking into the instrument, saw it too green, but if 48, 52, 56, or 60 were the selected color, then, if right to the first observer, it appeared too blue to the second. If the instrument were adjusted to suit the second observer, then, in the first case, the other saw red, and in the second green, showing that there was a real difference in the eyes of these two individuals, producing constant and measurable differences in the apparent color of objects. Section 14. Comparison by curves of intensity of the primaries. Figs. 6 and 7, Plate V, page 444, are intended to indicate the intensities of the three standard colors at different points of the spectrum. The curve marked H indicates the intensity of the red or 24, G, that of green or 44, and B, that of blue or 68. The curve marked S has its ordinates equal to the sum of the ordinates of the other three curves. The intensities are found by dividing every color equation by the coefficient of the color on the left-hand side. Fig. 6 represents the results of observations by K, and Fig. 7 represents those of J. It will be observed that the ordinates in Fig. 7 are smaller between 48 and 56 than in Fig. 6. This indicates the feeble intensity of certain kinds of light as seen by the eyes of J, which made it impossible to get observations of the color 52 at all without making the slit so wide as to include all between 48 and 56. This blindness of my eyes to the parts of the spectrum between the fixed lines E and F appears to be confined to the region surrounding the axis of vision, as the field of view, when adjusted for my eyes looking directly at the color, is decidedly out of adjustment when I view it by indirect vision, turning the axis of my eye towards some other point. The prism then appears greener and brighter than the mirror, showing that the parts of my eye at a distance from the axis are more sensitive to this blue-green light than the parts close to the axis. It is to be noticed that this insensibility is not to all light of a green or blue color, but to light of a definite refrangibility. If I had a species of color blindness rendering me totally or partially insensible to that element of color which most nearly corresponds with the light in question, then the light from the mirror, as well as that from the prism, would appear to me deficient in that color, and I should still consider them chromatically identical, or if there were any difference, it would be the same for all colors nearly the same in appearance, such as those just beyond the line F, which appear to me quite bright. We must also observe that the peculiarity is confined to a certain portion of the retina, which is known to be of a yellow color, and which is the seat of several ocular phenomena observed by Perkinge and Wheatstone, and of the sheaf or brushes seen by Haidinger in polarized light, and also that though, of the two observers whose results are given here, one is much more affected with this peculiarity than the other, both are less sensible to the light between E and F than to that on either side, and other observers, whose results are not here given, confirm this. Section 15. Explanation of the differences between the two observers. I think, therefore, that the yellow spot at the foramen central of Soemring will be found to be the cause of this phenomenon, and that it absorbs the rays between E and F, and would, if placed in the path of the incident light, produce a corresponding dark band in the spectrum formed by a prism. The reason why white light does not appear yellow in consequence, is that this absorbing action is constant, and we reckon as white the mean of all the colors we are accustomed to see. This may be proved by wearing spectacles of any strong color for some time, when we shall find that we judge white objects to be white, in spite of the rays which enter the eye being colored. Now ordinary white light is a mixture of all kinds of light, including that between E and F, which is partially absorbed. If, therefore, we compound an artificial white containing the absorbed ray as one of its three components, it will be much more altered by the absorption than the ordinary light, which contains many rays of nearly the same color, which are not absorbed. On the other hand, if the artificial light do not contain the absorbed ray, it will be less altered than the ordinary light which contains it. Hence the greater the absorption the less green will those colors appear which are near the absorbed part, such as 48, 52, 56, and the more green will the colors appear which are not near it, such as 3, 32, 36, 40. And these are the chief differences between Fig. 4 and Fig. 5. I first observed this peculiarity of my eyes when observing the spectrum formed by a very long vertical slit. I saw an elongated dark spot running up and down in the blue, as if confined in a groove, and following the motion of the eye as it moved up or down the spectrum, but refusing to pass out of the blue into other colors. By increasing the breadth of the spectrum, the dark portion was found to correspond to the foramen central, and to be visible only when the eye is turned towards the blue-green between E and F. The spot may be well seen by first looking at a yellow paper, and then at a blue one, when the spot will be distinctly seen for a short time, but it soon disappears when the eye gets accustomed to the blue. I have been the more careful in stating this peculiarity of my eyes, as I have reason to believe that it affects most persons, especially those who can see Heidinger's brushes easily. Such persons, in comparing their vision with that of others, may be led to think themselves affected with partial color blindness, whereas their color vision may be of the ordinary kind, but the rays which reach their sense of sight may be more or less altered in their proportions by passing through the media of the eye. The existence of real, though partial color blindness will make itself apparent, in a series of observations, by the discrepancy between the observed values and the means being greater in certain colors than in others. Section 16. General conclusions. Neither of the observers whose results are given here show any indications of color blindness, and when the differences arising from the absorption of the rays between E and F are put out of account, they agree in proving that there are three colors in the spectrum, red, green, and blue, by the mixtures of which colors chromatically identical with the other colors of the spectrum may be produced. The exact position of the red and blue is not yet ascertained, that of the green is from E towards F. The orange and yellow of the spectrum are chromatically equivalent to mixtures of red and green. They are neither richer nor paler than the corresponding mixtures, and the only difference is that the mixture may be resolved by a prism, whereas the color in the spectrum cannot be so resolved. This result seems to put an end to the pretension of yellow to be considered a primary element of color. In the same way, the colors from the primary green to blue are chromatically identical with mixtures of these, and the extreme ends of the spectrum are probably equivalent to mixtures of red and blue, but they are so feeble in illumination that experiments on the same plan with the rest can give no result, but they must be examined by some special method. When observations have been obtained from a greater number of individuals, including those whose vision is dichromatic, the chart of the spectrum may be laid down independently of accidental differences, and a more complete discussion of the laws of the sensation of color attempted. Postscript. Received May 8, read May 24, 1860. Since sending the above paper to the Royal Society, I have obtained some observations of the color of the spectrum by persons whose vision is dichromic, and who are therefore said to be color blind. The instrument used in making these observations was similar in principle to that formerly described, except that, in order to render it portable, the rays are reflected back through the prisms, nearly in their original direction, thus rendering one of the limbs of the instrument unnecessary, and allowing the other to be shortened considerably on account of the greater angular dispersion. The principle of reflecting light, so as to pass twice through the same prism, was employed by me in an instrument for combining colors made in 1856, and a reflecting instrument for observing the spectrum has been constructed independently by M. Porro. Light from a sheet of paper illuminated by sunlight is admitted at the slits X, Y, Z, Fig. 8, Plate 7, page 444, falls on the prisms P and P, angles equals 45 degrees, then on a concave silvered glass, S, radius 34 inches. The light, after reflection, passes again through the prisms P and P, and is reflected by a small mirror, E, to the slit E, where the eye is placed to receive the light compounded of the colors corresponding to the positions and breadths of the slits X, Y, and Z. At the same time, another portion of the light from the illuminated paper enters the instrument at BC, is reflected at the mirror M, passes through the lens L, is reflected at the mirror M, passes close to the edge of the prism P, and is reflected along with the colored light at E, to the eye slit at E. In this way the compound color is compared with a constant white light in optical juxtaposition with it. The mirror M is made of silvered glass, that at M, is made of glass roughened and blackened at the back, to reduce the intensity of the constant light to a convenient value for the experiments. This instrument gives a spectrum in which the lines are very distinct, and the length of the spectrum from it to H is 3 feet 6 inches. The outside measure of the box is 3 feet 6 inches, by 11 inches by 4 inches, and it can be carried about, and set up in any position, without readjustment. It was made by Messrs. Smith and Hamage of Aberdeen. In obtaining observations from color-blind persons, 2 slits only are required to produce a mixture chromatically equivalent to white, and at one point of the spectrum the color of the pure rays appears identical with white. This point is near the line F, a little on the less refrangible side. From this point to the more refrangible end of the spectrum appears to them blue. The colors on the less refrangible side appear to them all of the same quality, but of different degrees of brightness, and when any of them are made sufficiently bright, they are called yellow. It is convenient to use the term yellow in speaking of the colors from red to green inclusive, since it will be found that a dichromic person in speaking of red, green, orange, and brown, refers to different degrees of brightness or purity of a single color, and not to different colors perceived by him. This color we may agree to call yellow, though it is not probable that the sensation of it is like that of yellow as perceived by us. Of the 3 standard colors which I formerly assumed, the red appears to them yellow, but so feeble that there is not enough in the whole red division of the spectrum to form an equivalent to make up the standard white. The green at E appears a good yellow, and the blue from F towards G appears a good blue. I have therefore taken these as standard colors for reducing dichromic observations. The 3 standard colors will be referred to as 104, 88, and 68, these being the positions of the red, green, and blue on the scale of the new instrument. Mr. James Simpson, formerly student of natural philosophy in my class, has furnished me with 33 observations taken in good sunlight. 10 of these were between the 2 standard colors, and give the following result. The mean errors of these observations were as follows. The fact that the mean error of the sum was so much greater than the mean error of the difference indicates that in this case, as in all others that I have examined, observations of equality of tint can be depended on much more than observations of equality of illumination or brightness. From 6 observations of my own, made at the same time, I have deduced the trichromic equation. If we suppose that the light which reached the organ of vision was the same in both cases, we may combine these equations by subtraction, and so find where D is that color, the absence of the sensation of which constitutes the defect of the dichromic eye. The sensation which I have in addition to those of the dichromic eye is therefore similar to the full red, 104, but different from it, in that the red, 104, has 7/7 of green, 88, in it which must be removed, and 4/3 of blue, 68, substituted. This agrees pretty well with the color which Mr. Pohl describes as neutral to him, though crimson to others. It must be remembered, however, that different persons of ordinary vision require different proportions of the standard colors, probably owing to differences in the absorptive powers of the media of the eye, and that the above equation, too, if observed by K, would have been. And the value of D, as deduced from these observers, would have been. In which the defective sensation is much nearer to the red of the spectrum. It is probably a color to which the extreme red of the spectrum tends, and which differs from the extreme red only in not containing that small proportion of yellow light which renders it visible to the color blind. From other observations by Mr. Simpson the following results have been deduced. Table. In the table on the left side, 99.2 plus, means the whole of the spectrum beyond 99.2 on the scale, and 57 means the whole beyond 57 on the scale. The position of the fixed lines with reference to the scale was as follows. The values of the standard colors in different parts of the spectrum are given on the right side of the above table, and are represented by the curves of Fig. 9, Plate 7, page 444, where the left-hand curve represents the intensity of the yellow element, and the right-hand curve that of the blue element of color as it appears to the color blind. The appearance of the spectrum to the color blind is as follows. From A to E the color is pure, yellow, very faint up to D, and reaching a maximum between D and E. From E to 1/3 beyond F towards G the color is mixed, varying from yellow to blue, and becoming neutral or white at a point near F. In this part of the spectrum, the total intensity, as given by the dotted line, is decidedly less than on either side of it, and near the line F, the retina close to the yellow spot is less sensible to light than the parts further from the axis of the eye. This peculiarity of the light near F is even more marked in the color blind than in the ordinary eye. Beyond F the blue element comes to a maximum between F and G, and then diminishes towards H, the spectrum from this maximum to the end being pure blue. In Fig. 10, Plate 7, page 444, these results are represented in a different manner. The point D, corresponding to the sensation wanting in the color blind, is taken as the origin of coordinates. The yellow element of color is represented by distances measured horizontally to the right from D, and the blue element by distances measured vertically from the horizontal line through D. The numerals indicate the different colors of the spectrum according to the scale shown in Fig. 9, and the coordinates of each point indicate the composition of the corresponding color. The triangle of colors is reduced, in the case of dichromic vision, to a straight line B, Y, and the proportions of blue and yellow in each color are indicated by the ratios in which this line is cut by the line from D passing through the position of that color. The results given above were all obtained with the light of white paper, placed in clear sunshine. I have obtained similar results, when the sun was hidden, by using the light of uniformly illuminated clouds, but I do not consider these observations sufficiently free from disturbing circumstances to be employed in calculation. It is easy, however, by means of such observations, to verify the most remarkable phenomena of color blindness, as for instance, that the colors from red to green appear to differ only in brightness, and that the brightness may be made identical by changing the width of the slit. That the color near F is a neutral tint, and that the eye in viewing it sees a dark spot in the direction of the axis of vision. That the colors beyond are all blue of different intensities, and that any blue may be combined with any yellow, in such proportions as to form white. These results I have verified by the observations of another color-blind gentleman, who did not obtain sunlight for his observations, and as I have now the means of carrying the requisite apparatus easily, I hope to meet with other color-blind observers, and to obtain their observations under more favorable circumstances. On the comparison of color blind with ordinary vision by means of observations with colored papers. In March 1859 I obtained a set of observations by Mr. Simpson, of the relations between 6 colored papers as seen by him. The experiments were made with the color top in the manner described in my paper in the Transactions of the Royal Society of Edinburgh, Volume 21, Part 2, page 286, and the color equations were arranged so as to be equated to 0, as in those given in the Philosophical Magazine, July, 1857. The colors were vermilion, Y, ultramarine, U, emerald green, G, ivory black, B, snow white, W, and pale chrome yellow, Y. These 6 colors afford 15 color-blind equations, since 4 colors enter into each equation. 14 of these were observed by Mr. Simpson, and from these I deduced 3 equations, giving the relation of the 3 standards, Y, U, G, to the other colors, according to his kind of vision. From these 3 equations I then deduced 15 equations, admitting of comparison with the observed equations, and necessarily consistent in themselves. The comparison of these equations furnishes a test of the truth of the theory that the color blind see by means of 2 color sensations, and that therefore every color may be expressed in terms of 2 given colors, just as in ordinary vision it may be expressed in terms of 3 given colors. The one set of equations are each the result of a single observation. The other set are deduced from 3 equations in accordance with this theory, and the 2 sets agree to within an average error equals 2, 1. Table B. But, according to our theory, color-blind vision is not only dichromic, but the 2 elements of color are identical with 2 of the 3 elements of color as seen by the ordinary eye, so that it differs from ordinary vision only in not perceiving a particular color, the relation of which to known colors may be numerically defined. This color may be expressed under the form where V, U, and G are the standard colors used in the experiments, and D is the color which is visible to the ordinary eye, but invisible to the colorblind. If we know the value of D, we may always change an ordinary color equation into a color-blind equation by subtracting from it ND, N being chosen so that one of the standard colors is eliminated, and adding N of black. In September 1856 I deduced, from 36 observations of my own, the chromatic relations of the same set of 6 colored papers. These observations, with a comparison of them with the trichromic theory of vision, are to be found in the Philosophical Magazine for July 1857. The relations of the 6 colors may be deduced from 2 equations. Of W big the most convenient form is the value of D, as deduced from a comparison of these equations with the color-blind equations, is by making D the same thing as black, B, and eliminating W and Y respectively from the 2 ordinary color equations by means of D, we obtain 3 color-blind equations, calculated from the ordinary equations and consistent with them, supposing that the color, D, is black to the color-blind. The following table is a comparison of the color-blind equations deduced from Mr. Simpson's observations alone, with those deduced from my observations and the value of D. Tablec. The average error here is 1/9, smaller than the average error of the visual color-blind observations, showing that the theory of color blindness being the want of a certain color sensation which is one of the 3 ordinary color sensations, agrees with observation to within the limits of error. In Fig. 11, Plate 7, page 444, I have laid down the chromatic relations of these colors according to Newton's method. V, vermilion, U, ultramarine, and G, emerald green, are assumed as standard colors, and placed at the angles of an equilateral triangle. The position of W, white, and Y, pale chrome yellow, with respect to these are laid down from equations 17 and 18, deduced from my own observations. The positions of the defective color, of white, and of yellow, as deduced from Mr. Simpson's equations alone, are given at D, W, and Y. The positions of these points, as deduced from a combination of these equations with my own, are given at D, W, and Y. The difference of these positions from those of D, W, and Y shows the amount of discrepancy between observation and theory. It will be observed that D is situated near V, vermilion, but that a line from D to W cuts UY at C near to VD is therefore a red color, not scarlet, but further from yellow. It may be called crimson, and may be imitated by a mixture of 86 vermilion and 14 ultramarine. This compound color will be of the same hue as D. But since C lies between P and W, C must be regarded as D diluted with a certain amount of white, and therefore D must be imagined to be like C in hue, but without the intermixture of white which is unavoidable in actual pigments, and which reduces the purity of the tint. Lines drawn from D through W and Y, the color-blind positions of white and yellow, pass through W and Y, their positions in ordinary vision. The reason why they do not coincide with W and Y is that the white and yellow papers are much brighter than the colors corresponding to the points W and Y of the triangle Y, U, G, and therefore lines from D, which represent them in intensity as well as in quality, must be longer than DW and DY in the proportion of their brightness. Volume 1 Plate VI, I. Fig. 1, Fig. 2, Fig. 3, Fig. 4, Fig. 5, Fig. 6, Fig. 7, Volume 1 Plate 7, 2, Fig. 8, Fig. 9, Fig. 10, Fig. 11, Optics, Book 1 Part 2, Prop. 7. Lectiones Optico, Part 2, Section 1, pp. 100 to 105, and Optics, Book 1 Part 2, Prop. 11. Optics, Book 1 Part 2, Prop. 4. Optics, Book 1 Part 2, Props. 4, 5, 6. Asterisk 7th and 8th letters to Oldenburg. Young's Lectures on Natural Philosophy, Kellen's edition, page 345, or quarto, 1807, volume 1 page 441. See also Young in Philosophical Transactions, 1801, or Works in Quarto, volume 2, page 617. Transactions of the Royal Society of Edinburgh, volume 12, page 123. Poggendorf's Annalen, Band LXXXVII. Philosophical Magazine, 1852, December. Ibid. Band LXXXIX. Philosophical Magazine, 1854, April. Ibid. Band XCIV. Transactions of the Royal Society of Edinburgh, volume 21, part 2, page 286. Asterisk see the report of the British Association for 1856, page 12. Philosophical Transactions, 1859, part 1 page 329. Lecture at the Royal Institution of Great Britain. May 17, 1861. 22. On the theory of three primary colors. The speaker commenced by showing that our power of vision depends entirely on our being able to distinguish the intensity and quality of colors. The forms of visible objects are indicated to us only by differences in color or brightness between them and surrounding objects. To classify and arrange these colors, to ascertain the physical conditions on which the differences of colored rays depend, and to trace, as far as we are able, the physiological process by which these different rays excite in us various sensations of color, we must avail ourselves of the united experience of painters, opticians, and physiologists. The speaker then proceeded to state the results obtained by these three classes of inquirers, to explain their apparent inconsistency by means of Young's theory of primary colors, and to describe the tests to which he had subjected that theory. Painters have studied the relations of colors, in order to imitate them by means of pigments. As there are only a limited number of colored substances adapted for painting, while the number of tints in nature is infinite, painters are obliged to produce the tints they require by mixing their pigments in proper proportions. This leads them to regard these tints as actually compounded of other colors, corresponding to the pure pigments in the mixture. It is found that by using three pigments only, we can produce all colors lying within certain limits of intensity and purity. For instance, if we take carmine, red, chrome yellow, and ultramarine, blue, we get by mixing the carmine and the chrome, all varieties of orange, passing through scarlet to crimson on the one side, and to yellow on the other. By mixing chrome and ultramarine we get all hues of green, and by mixing ultramarine with carmine, we get all hues of purple, from violet to mauve and crimson. Now these are all the strong colors that we ever see or can imagine. All others are like these, only less pure in tint. Our three colors can be mixed so as to form a neutral gray, and if this gray be mixed with any of the hues produced by mixing two colors only, all the tints of that hue will be exhibited, from the pure color to neutral gray. If we could assume that the color of a mixture of different kinds of paint is a true mixture of the colors of the pigments, and in the same proportion, then an analysis of color might be made with the same ease as a chemical analysis of a mixture of substances. The color of a mixture of pigments, however, is often very different from a true mixture of the colors of the pure pigments. It is found to depend on the size of the particles, a finely ground pigment producing more effect than one coarsely ground. It has also been shown by Professor Helmholtz that when light falls on a mixture of pigments, part of it is acted on by one pigment only, and part of it by another, while a third portion is acted on by both pigments in succession before it is sent back to the eye. The two parts reflected directly from the pure pigments enter the eye together, and form a true mixture of colors, but the third portion, which has suffered absorption from both pigments, is often so considerable as to give its own character to the resulting tint. This is the explanation of the green tint produced by mixing most blue and yellow pigments. In studying the mixture of colors, we must avoid these sources of error, either by mixing the rays of light themselves, or by combining the impressions of colors within the eye by the rotation of colored papers on a disc. The speaker then stated what the opticians had discovered about color. White light, according to Newton, consists of a great number of different kinds of colored light which can be separated by a prism. Newton divided these into 7 classes, but we now recognize many thousand distinct kinds of light in the spectrum, none of which can be shown to be a compound of more elementary rays. If we accept the theory that light is an undulation, then, as there are undulations of every different period from the one end of the spectrum to the other, there are an infinite number of possible kinds of light, no one of which can be regarded as compounded of any others. Physical optics does not lead us to any theory of 3 primary colors, but leaves us in possession of an infinite number of pure rays with an infinitely more infinite number of compound beams of light, each containing any proportions of any number of the pure rays. These beams of light, passing through the transparent parts of the eye, fall on a sensitive membrane, and we become aware of various colors. We know that the color we see depends on the nature of the light, but the opticians say there are an infinite number of kinds of light, while the painters, and all who pay attention to what they see, tell us that they can account for all actual colors by supposing them mixtures of 3 primary colors. The speaker then next drew attention to the physiological difficulties in accounting for the perception of color. Some have supposed that the different kinds of light are distinguished by the time of their vibration. There are about 447 billions of vibrations of red light in a second, and 577 billions of vibrations of green light in the same time. It is certainly not by any mental process of which we are conscious that we distinguish between these infinitesimal portions of time, and it is difficult to conceive any mechanism by which the vibrations could be counted so that we should become conscious of the results, especially when many rays of different periods of vibration act on the same part of the eye at once. Besides, all the evidence we have on the nature of nervous action goes to prove that whatever be the nature of the agent which excites a nerve, the sensation will differ only in being more or less acute. By acting on a nerve in various ways, we may produce the faintest sensation or the most violent pain, but if the intensity of the sensation is the same, its quality must be the same. Now, we may perceive by our eyes a faint red light which may be made stronger and stronger till our eyes are dazzled. We may then perform the same experiment with a green light or a blue light. We shall thus see that our sensation of color may differ in other ways, besides in being stronger or fainter. The sensation of color, therefore, cannot be due to one nerve only. The speaker then proceeded to state the theory of Dr. Thomas Young, as the only theory which completely reconciles these difficulties in accounting for the perception of color. Young supposes that the eye is provided with 3 distinct sets of nervous fibers, each set extending over the whole sensitive surface of the eye. Each of these 3 systems of nerves, when excited, gives us a different sensation. One of them, which gives us the sensation we call red, is excited most by the red rays, but also by the orange and yellow, and slightly by the violet. Another is acted on by the green rays, but also by the orange and yellow and part of the blue, while the third is acted on by the blue and violet rays. If we could excite one of these sets of nerves without acting on the others, we should have the pure sensation corresponding to that set of nerves. This would be truly a primary color, whether the nerve were excited by pure or by compound light, or even by the action of pressure or disease. If such experiments could be made, we should be able to see the primary colors separately, and to describe their appearance by reference to the scale of colors in the spectrum. But we have no direct consciousness of the contrivances of our own bodies, and we never feel any sensation which is not infinitely complex, so that we can never know directly how many sensations are combined when we see a color. Still less can we isolate one or more sensations by artificial means, so that in general when a ray enters the eye, though it should be one of the pure rays of the spectrum, it may excite more than one of the 3 sets of nerves, and thus produce a compound sensation. The terms simple and compound, therefore, as applied to color sensation, have by no means the same meaning as they have when applied to a ray of light. The speaker then stated some of the consequences of Young's theory, and described the tests to which he had subjected it. First, there are 3 primary colors. Second, every color is either a primary color, or a mixture of primary colors. Third, 4 colors may always be arranged in one of 2 ways. Either one of them is a mixture of the other 3, or a mixture of 2 of them can be found, identical with a mixture of the other 2. Fourth, these results may be stated in the form of color equations, giving the numerical value of the amount of each color entering into any mixture. By means of the color top asterisk, such equations can be obtained for colored papers, and they may be obtained with a degree of accuracy showing that the color judgment of the eye may be rendered very perfect. The speaker had tested in this way more than 100 different pigments and mixtures, and had found the results agree with the theory of 3 primaries in every case. He had also examined all the colors of the spectrum with the same result. The experiments with pigments do not indicate what colors are to be considered as primary, but experiments on the prismatic spectrum show that all the colors of the spectrum, and therefore all the colors in nature, are equivalent to mixtures of 3 colors of the spectrum itself, namely, red, green, near the line E, and blue, near the line G. Yellow was found to be a mixture of red and green. The speaker, assuming red, green, and blue as primary colors, then exhibited them on a screen by means of 3 magic lanterns, before which were placed glass troughs containing respectively sulfocyanide of iron, chloride of copper, and ammoniated copper. A triangle was thus illuminated, so that the pure colors appeared at its angles, while the rest of the triangle contained the various mixtures of the colors as in Young's triangle of color. The graduated intensity of the primary colors in different parts of the spectrum was exhibited by 3 colored images, which, when superposed on the screen, gave an artificial representation of the spectrum. 3 photographs of a colored ribbon taken through the 3 colored solutions respectively, were introduced into the camera, giving images representing the red, the green, and the blue parts separately, as they would be seen by each of Young's 3 sets of nerves separately. When these were superposed, a colored image was seen, which, if the red and green images had been as fully photographed as the blue, would have been a truly colored image of the ribbon. By finding photographic materials more sensitive to the less refrangible rays, the representation of the colors of objects might be greatly improved. The speaker then proceeded to exhibit mixtures of the colors of the pure spectrum. Light from the electric lamp was passed through a narrow slit, a lens and a prism, so as to throw a pure spectrum on a screen containing 3 movable slits, through which 3 distinct portions of the spectrum were suffered to pass. These portions were concentrated by a lens on a screen at a distance, forming a large, uniformly colored image of the prism. When the whole spectrum was allowed to pass, this image was white, as in Newton's experiment of combining the rays of the spectrum. When portions of the spectrum were allowed to pass through the movable slits, the image was uniformly illuminated with a mixture of the corresponding colors. In order to see these colors separately, another lens was placed between the movable slits and the screen. A magnified image of the slits was thus thrown on the screen, each slit showing, by its color and its breadth, the quality and quantity of the color which it suffered to pass. Several colors were thus exhibited, first separately, and then in combination. Red and blue, for instance, produced purple, red and green produced yellow, blue and yellow produced a pale pink, red, blue, and green produced white, and red and a bluish-green near the line F produced a color which appears very different to different eyes. The speaker concluded by stating the peculiarities of colorblind vision, and by showing that the investigation into the theory of color is truly a physiological inquiry, and that it requires the observations and testimony of persons of every kind in order to discover and explain the various peculiarities of vision. Asterisk described in the Trans. of the Royal Society of Edinburgh, Volume 21, and in the Phil. Mag. from the Philosophical Magazine, Volume 21, 23, on Physical Lines of Force. Part 1. The theory of molecular vortices applied to magnetic phenomena. In all phenomena involving attractions or repulsions, or any forces depending on the relative position of bodies, we have to determine the magnitude and direction of the force which would act on a given body, if placed in a given position. In the case of a body acted on by the gravitation of a sphere, this force is inversely as the square of the distance, and in a straight line to the center of the sphere. In the case of two attracting spheres, or of a body not spherical, the magnitude and direction of the force vary according to more complicated laws. In electric and magnetic phenomena, the magnitude and direction of the resultant force at any point is the main subject of investigation. Suppose that the direction of the force at any point is known, then, if we draw a line so that in every part of its course it coincides in direction with the force at that point, this line may be called a line of force, since it indicates the direction of the force in every part of its course. By drawing a sufficient number of lines of force, we may indicate the direction of the force in every part of the space in which it acts. Thus, if we strew iron filings on paper near a magnet, each filing will be magnetized by induction, and the consecutive filings will unite by their opposite poles, so as to form fibers, and these fibers will indicate the direction of the lines of force. The beautiful illustration of the presence of magnetic force afforded by this experiment naturally tends to make us think of the lines of force as something real, and as indicating something more than the mere resultant of two forces, whose seat of action is at a distance, and which do not exist there at all until a magnet is placed in that part of the field. We are dissatisfied with the explanation founded on the hypothesis of attractive and repellent forces directed towards the magnetic poles, even though we may have satisfied ourselves that the phenomenon is in strict accordance with that hypothesis, and we cannot help thinking that in every place where we find these lines of force, some physical state or action must exist in sufficient energy to produce the actual phenomena. My object in this paper is to clear the way for speculation in this direction, by investigating the mechanical results of certain states of tension and motion in a medium, and comparing these with the observed phenomena of magnetism and electricity. By pointing out the mechanical consequences of such hypotheses, I hope to be of some use to those who consider the phenomena as due to the action of a medium, but are in doubt as to the relation of this hypothesis to the experimental laws already established, which have generally been expressed in the language of other hypotheses. I have in a former paper endeavored to lay before the mind of the geometer a clear conception of the relation of the lines of force to the space in which they are traced. By making use of the conception of currents in a fluid, I showed how to draw lines of force, which should indicate by their number the amount of force, so that each line may be called a unit line of force. See Faraday's Researches, 3122, and I have investigated the path of the lines where they pass from one medium to another. In the same paper I have found the geometrical significance of the electrotonic state, and have shown how to deduce the mathematical relations between the electrotonic state, magnetism, electric currents, and the electromotive force, using mechanical illustrations to assist the imagination, but not to account for the phenomena. I propose now to examine magnetic phenomena from a mechanical point of view, and to determine what tensions in, or motions of, a medium are capable of producing the mechanical phenomena observed. If, by the same hypothesis, we can connect the phenomena of magnetic attraction with electromagnetic phenomena and with those of induced currents, we shall have found a theory which, if not true, can only be proved to be erroneous by experiments which will greatly enlarge our knowledge of this part of physics. The mechanical conditions of a medium under magnetic influence have been variously conceived of as currents, undulations, or states of displacement or strain, or of pressure or stress. Currents, issuing from the North Pole and entering the South Pole of a magnet, or circulating round an electric current, have the advantage of representing correctly the geometrical arrangement of the lines of force, if we could account on mechanical principles for the phenomena of attraction, or for the currents themselves, or explain their continued existence. Undulations issuing from a center would, according to the calculations of Professor Challis, produce an effect similar to attraction in the direction of the center, but admitting this to be true, we know that two series of undulations traversing the same space do not combine into one resultant as two attractions do, but produce an effect depending on relations of phase as well as intensity, and if allowed to proceed, they diverge from each other without any mutual action. In fact, the mathematical laws of attractions are not analogous in any respect to those of undulations, while they have remarkable analogies with those of currents, of the conduction of heat and electricity, and of elastic bodies. In the Cambridge and Dublin Mathematical Journal for January 1847, Professor William Thomson has given a mechanical representation of electric, magnetic, and galvanic forces, by means of the displacements of the particles of an elastic solid in a state of strain. In this representation we must make the angular displacement at every point of the solid proportional to the magnetic force at the corresponding point of the magnetic field, the direction of the axis of rotation of the displacement corresponding to the direction of the magnetic force. The absolute displacement of any particle will then correspond in magnitude and direction to that which I have identified with the electrotonic state, and the relative displacement of any particle, considered with reference to the particle in its immediate neighborhood, will correspond in magnitude and direction to the quantity of electric current passing through the corresponding point of the magneto-electric field. The author of this method of representation does not attempt to explain the origin of the observed forces by the effects due to these strains in the elastic solid, but makes use of the mathematical analogies of the two problems to assist the imagination in the study of both. We come now to consider the magnetic influence as existing in the form of some kind of pressure or tension, or, more generally, of stress in the medium. Stress is action and reaction between the consecutive parts of a body, and consists in general of pressures or tensions different in different directions at the same point of the medium. The necessary relations among these forces have been investigated by mathematicians, and it has been shown that the most general type of a stress consists of a combination of three principal pressures or tensions, in directions at right angles to each other. When two of the principal pressures are equal, the third becomes an axis of symmetry, either of greatest or least pressure, the pressures at right angles to this axis being all equal. When the three principal pressures are equal, the pressure is equal in every direction, and there results a stress having no determinate axis of direction, of which we have an example in simple hydrostatic pressure. The general type of a stress is not suitable as a representation of a magnetic force, because a line of magnetic force has direction and intensity, but has no third quality indicating any difference between the sides of the line, which would be analogous to that observed in the case of polarized light. We must therefore represent the magnetic force at a point by a stress having a single axis of greatest or least pressure, and all the pressures at right angles to this axis equal. It may be objected that it is inconsistent to represent a line of force, which is essentially dipolar, by an axis of stress, which is necessarily isotropic, but we know that every phenomenon of action and reaction is isotropic in its results, because the effects of the force on the bodies between which it acts are equal and opposite, while the nature and origin of the force may be dipolar, as in the attraction between a north and a south pole. Let us next consider the mechanical effect of a state of stress symmetrical about an axis. We may resolve it, in all cases, into a simple hydrostatic pressure, combined with a simple pressure or tension along the axis. When the axis is that of greatest pressure, the force along the axis will be a pressure. When the axis is that of least pressure, the force along the axis will be a tension. If we observe the lines of force between two magnets, as indicated by iron filings, we shall see that whenever the lines of force pass from one pole to another, there is attraction between those poles. And where the lines of force from the poles avoid each other and are dispersed into space, the poles repel each other, so that in both cases they are drawn in the direction of the resultant of the lines of force. It appears therefore that the stress in the axis of a line of magnetic force is a tension, like that of a rope. If we calculate the lines of force in the neighborhood of two gravitating bodies, we shall find them the same in direction as those near two magnetic poles of the same name, but we know that the mechanical effect is that of attraction instead of repulsion. The lines of force in this case do not run between the bodies, but avoid each other, and are dispersed over space. In order to produce the effect of attraction, the stress along the lines of gravitating force must be a pressure. Let us now suppose that the phenomena of magnetism depend on the existence of a tension in the direction of the lines of force, combined with a hydrostatic pressure, or in other words, a pressure greater in the equatorial than in the axial direction. The next question is, what mechanical explanation can we give of this inequality of pressures in a fluid or mobile medium? The explanation which most readily occurs to the mind is that the excessive pressure in the equatorial direction arises from the centrifugal force of vortices or eddies in the medium having their axes in directions parallel to the lines of force. This explanation of the cause of the inequality of pressures at once suggests the means of representing the dipolar character of the line of force. Every vortex is essentially dipolar, the two extremities of its axis being distinguished by the direction of its revolution as observed from those points. We also know that when electricity circulates in a conductor, it produces lines of magnetic force passing through the circuit, the direction of the lines depending on the direction of the circulation. Let us suppose that the direction of revolution of our vortices is that in which vitreous electricity must revolve in order to produce lines of force whose direction within the circuit is the same as that of the given lines of force. We shall suppose at present that all the vortices in any one part of the field are revolving in the same direction about axes nearly parallel, but that in passing from one part of the field to another, the direction of the axes, the velocity of rotation, and the density of the substance of the vortices are subject to change. We shall investigate the resultant mechanical effect upon an element of the medium, and from the mathematical expression of this resultant we shall deduce the physical character of its different component parts. Prop. I. If in two fluid systems geometrically similar the velocities and densities at corresponding points are proportional, then the differences of pressure at corresponding points due to the motion will vary in the duplicate ratio of the velocities and the simple ratio of the densities. Let L be the ratio of the linear dimensions, m that of the velocities, n that of the densities, and p that of the pressures due to the motion. Then the ratio of the masses of corresponding portions will be L3n, and the ratio of the velocities acquired in traversing similar parts of the systems will be m, so that L3 million is the ratio of the momenta acquired by similar portions in traversing similar parts of their paths. The ratio of the surfaces is L2, that of the forces acting on them is L2p, and that of the times during which they act is, so that the ratio of the impulse of the forces is, and we have now a. That is, the ratio of the pressures due to the motion, p, is compounded of the ratio of the densities, n, and the duplicate ratio of the velocities, m2, and does not depend on the linear dimensions of the moving systems. In a circular vortex, revolving with uniform angular velocity, if the pressure at the axis is p0, that at the circumference will be where ρ is the density and v the velocity at the circumference. The mean pressure parallel to the axis will be. If a number of such vortices were placed together side by side with their axes parallel, they would form a medium in which there would be a pressure P2 parallel to the axis, and a pressure P1 in any perpendicular direction. If the vortices are circular, and have uniform angular velocity and density throughout, then. If the vortices are not circular, and if the angular velocity and the density are not uniform, but vary according to the same law for all the vortices, where ρ is the mean density, and c is a numerical quantity depending on the distribution of angular velocity and density in the vortex. In future we shall write instead of c ρ, so that where μ is a quantity bearing a constant ratio to the density, and v is the linear velocity at the circumference of each vortex. A medium of this kind, filled with molecular vortices having their axes parallel, differs from an ordinary fluid in having different pressures in different directions. If not prevented by properly arranged pressures, it would tend to expand laterally. In so doing, it would allow the diameter of each vortex to expand and its velocity to diminish in the same proportion. In order that a medium having these inequalities of pressure in different directions should be in equilibrium, certain conditions must be fulfilled, which we must investigate. Prop. 2. If the direction cosines of the axes of the vortices with respect to the axes of x, y, and z be L, m, and n, to find the normal and tangential stresses on the coordinate planes. The actual stress may be resolved into a simple hydrostatic pressure P1 acting in all directions, and a simple tension P1 P2, or acting along the axis of stress. Hence if Pxx, Pyy, and Pzz be the normal stresses parallel to the three axes, considered positive when they tend to increase those axes, and if Pyz, Pzx, and Pxy be the tangential stresses in the three coordinate planes, considered positive when they tend to increase simultaneously the symbols subscribed, then by the resolution of stresses *. If we write, then Prop. 3. To find the resultant force on an element of the medium, arising from the variation of internal stress. We have in general, for the force in the direction of x per unit of volume by the law of equilibrium of stresses. In this case the expression may be written. Remembering that this becomes, the expressions for the forces parallel to the axes of y and z may be written down from analogy. We suppose alpha, beta, gamma to be the components of the force which would act upon that end of a unit magnetic bar which points to the north. Mu represents the magnetic inductive capacity of the medium at any point referred to air as a standard, Ma, Mb, Mg represent the quantity of magnetic induction through unit of area perpendicular to the three axes of x, y, z respectively. The total amount of magnetic induction through a closed surface surrounding the pole of a magnet depends entirely on the strength of that pole, so that if dx dy dz be an element, then which represents the total amount of magnetic induction outwards through the surface of the element dx dy dz, represents the amount of imaginary magnetic matter within the element of the kind which points north. The first term of the value of x, therefore, may be written where alpha is the intensity of the magnetic force, and m is the amount of magnetic matter pointing north in unit of volume. The physical interpretation of this term is that the force urging a north pole in the positive direction of x is the product of the intensity of the magnetic force resolved in that direction, and the strength of the north pole of the magnet. Let the parallel lines from left to right in Fig. 1 represent a field of magnetic force such as that of the Earth, Sn being the direction from south to north. The vortices, according to our hypothesis, will be in the direction shown by the arrows in Fig. 3, that is, in a plane perpendicular to the lines of force, and revolving in the direction of the hands of a watch when observed from S looking towards N. The parts of the vortices above the plane of the paper will be moving towards E, and the parts below that plane towards W. We shall always mark by an arrowhead the direction in which we must look in order to see the vortices rotating in the direction of the hands of a watch. The arrowhead will then indicate the northward direction in the magnetic field, that is, the direction in which that end of a magnet which points to the north would set itself in the field. Now let A be the end of a magnet which points north. Since it repels the north ends of other magnets, the lines of force will be directed from or outwards in all directions. On the north side the line AD will be in the same direction with the lines of the magnetic field, and the velocity of the vortices will be increased. On the south side the line AC will be in the opposite direction, and the velocity of the vortices will be diminished, so that the lines of force are more powerful on the north side of A than on the south side. Fig. 1, Fig. 2, Fig. 3. We have seen that the mechanical effect of the vortices is to produce a tension along their axes, so that the resultant effect on A will be to pull it more powerfully towards D than towards C. That is, A will tend to move to the north. Let B in Fig. 2 represent a south pole. The lines of force belonging to B will tend towards B, and we shall find that the lines of force are rendered stronger towards E than towards F, so that the effect in this case is to urge B towards the south. It appears therefore that, on the hypothesis of molecular vortices, our first term gives a mechanical explanation of the force acting on a north or south pole in the magnetic field. We now proceed to examine the second term. Here alpha 2 plus beta 2 plus gamma 2 is the square of the intensity at any part of the field, and mu is the magnetic inductive capacity at the same place. Any body therefore placed in the field will be urged towards places of stronger magnetic intensity with a force depending partly on its own capacity for magnetic induction, and partly on the rate at which the square of the intensity increases. If the body be placed in a fluid medium, then the medium, as well as the body, will be urged towards places of greater intensity, so that its hydrostatic pressure will be increased in that direction. The resultant effect on a body placed in the medium will be the difference of the actions on the body and on the portion of the medium which it displaces, so that the body will tend to or from places of greatest magnetic intensity, according as it has a greater or less capacity for magnetic induction than the surrounding medium. In Fig. 4, the lines of force are represented as converging and becoming more powerful towards the right, so that the magnetic tension at B is stronger than at A, and the body AB will be urged to the right. If the capacity for magnetic induction is greater in the body than in the surrounding medium, it will move to the right, but if less it will move to the left. Fig. 4, Fig. 5. We may suppose in this case that the lines of force are converging to a magnetic pole, either north or south, on the right hand. In Fig. 5, the lines of force are represented as vertical, and becoming more numerous towards the right. It may be shown that if the force increases towards the right, the lines of force will be curved towards the right. The effect of the magnetic tensions will then be to draw any body towards the right with a force depending on the excess of its inductive capacity over that of the surrounding medium. We may suppose that in this figure the lines of force are those surrounding an electric current perpendicular to the plane of the paper and on the right hand of the figure. These two illustrations will show the mechanical effect on a paramagnetic or diamagnetic body placed in a field of varying magnetic force, whether the increase of force takes place along the lines or transverse to them. The form of the second term of our equation indicates the general law, which is quite independent of the direction of the lines of force, and depends solely on the manner in which the force varies from one part of the field to another. We come now to the third term of the value of x. Here m is, as before, the quantity of magnetic induction through unit of area perpendicular to the axis of y, and is a quantity which would disappear if alpha dx plus beta dy plus gamma dz were a complete differential, that is, if the force acting on a unit north pole was subject to the condition that no work can be done upon the pole in passing round any closed curve. The quantity represents the work done on a north pole in traveling round unit of area in the direction from plus x to plus y parallel to the plane of xy. Now if an electric current whose strength is R is traversing the axis of z, which, we may suppose, points vertically upwards, then, if the axis of x is east and that of y north, a unit north pole will be urged round the axis of z in the direction from x to y, so that in one revolution the work done will be equals 4 pi r. Hence represents the strength of an electric current parallel to z through unit of area, and if we write, then P, Q, R will be the quantity of electric current per unit of area perpendicular to the axes of x, y, and z respectively. The physical interpretation of the third term of x, MBR, is that if MB is the quantity of magnetic induction parallel to y, and R the quantity of electricity flowing in the direction of z, the element will be urged in the direction of x, transversely to the direction of the current and of the lines of force. That is, an ascending current in a field of force magnetized towards the north would tend to move west. To illustrate the action of the molecular vortices, let Sn be the direction of magnetic force in the field, and let C be the section of an ascending magnetic current perpendicular to the paper. The lines of force due to this current will be circles drawn in the opposite direction from that of the hands of a watch, that is, in the direction NWSE. At E the lines of force will be the sum of those of the field and of the current, and at W they will be the difference of the two sets of lines, so that the vortices on the east side of the current will be more powerful than those on the west side. Both sets of vortices have their equatorial parts turned towards C, so that they tend to expand towards C, but those on the east side have the greatest effect, so that the resultant effect on the current is to urge it towards the west. Fig. 6. The fourth term may be interpreted in the same way, and indicates that a current Q in the direction of y, that is, to the north, placed in a magnetic field in which the lines are vertically upwards in the direction of z, will be urged towards the east. The fifth term merely implies that the element will be urged in the direction in which the hydrostatic pressure P1 diminishes. We may now write down the expressions for the components of the resultant force on an element of the medium per unit of volume, thus. The first term of each expression refers to the force acting on magnetic poles. The second term to the action on bodies capable of magnetism by induction. The third and fourth terms to the force acting on electric currents. And the fifth to the effect of simple pressure. Before going further in the general investigation, we shall consider equations 12, 13, 14, in particular cases, corresponding to those simplified cases of the actual phenomena which we seek to obtain in order to determine their laws by experiment. We have found that the quantities P, Q, and R represent the resolved parts of an electric current in the three coordinate directions. Let us suppose in the first instance that there is no electric current, or that P, Q, and R vanish. We have then by 9, whence we learn that is an exact differential of phi, so that mu is proportional to the density of the vortices, and represents the capacity for magnetic induction in the medium. It is equal to 1 in air, or in whatever medium the experiments were made which determine the powers of the magnets, the strengths of the electric currents, and c. Let us suppose mu constant, then, represents the amount of imaginary magnetic matter in unit of volume. That there may be no resultant force on that unit of volume arising from the action represented by the first term of equations, 12, 13, 14, we must have m equals 0, or. Now it may be shown that equation 19, if true within a given space, implies that the forces acting within that space are such as would result from a distribution of centers of force beyond that space, attracting or repelling inversely as the square of the distance. Hence the lines of force in a part of space where mu is uniform, and where there are no electric currents, must be such as would result from the theory of imaginary matter acting at a distance. The assumptions of that theory are unlike those of ours, but the results are identical. Let us first take the case of a single magnetic pole, that is, one end of a long magnet, so long that its other end is too far off to have a perceptible influence on the part of the field we are considering. The conditions then are, that equation, 18, must be fulfilled at the magnetic pole, and, 19, everywhere else. The only solution under these conditions is, where r is the distance from the pole, and m the strength of the pole. The repulsion at any point on a unit pole of the same kind is, in the standard medium mu equals 1, so that the repulsion is simply in that medium, as has been shown by Coulomb. In a medium having a greater value of mu, such as oxygen, solutions of salts of iron, and C, the attraction, on our theory, ought to be less than in air, and in diamagnetic media, such as water, melted bismuth, and C, the attraction between the same magnetic poles ought to be greater than in air. The experiments necessary to demonstrate the difference of attraction of two magnets according to the magnetic or diamagnetic character of the medium in which they are placed, would require great precision, on account of the limited range of magnetic capacity in the fluid media known to us, and the small amount of the difference sought for as compared with the whole attraction. Let us next take the case of an electric current whose quantity is C, flowing through a cylindrical conductor whose radius is r, and whose length is infinite as compared with the size of the field of force considered. Let the axis of the cylinder be that of z, and the direction of the current positive, then within the conductor the quantity of current per unit of area is so that within the conductor, beyond the conductor, in the space round it, if is the perpendicular distance of any point from the axis of the conductor, a unit north pole will experience a force tending to move it round the conductor in the direction of the hands of a watch, if the observer view it in the direction of the current. Let us now consider a current running parallel to the axis of z in the plane of xz at a distance ρ. Let the quantity of the current be C, and let the length of the part considered be L, and its section S, so that is its strength per unit of section. Putting this quantity for ρ in equations 12, 13, 14, we find per unit of volume, and multiplying by Ls, the volume of the conductor considered, we find, showing that the second conductor will be attracted towards the first with a force inversely as the distance. We find in this case also that the amount of attraction depends on the value of mu, but that it varies directly instead of inversely as mu, so that the attraction between two conducting wires will be greater in oxygen than in air, and greater in air than in water. We shall next consider the nature of electric currents and electromotive forces in connection with the theory of molecular vortices. Part 2. The theory of molecular vortices applied to electric currents. We have already shown that all the forces acting between magnets, substances capable of magnetic induction, and electric currents, may be mechanically accounted for on the supposition that the surrounding medium is put into such a state that at every point the pressures are different in different directions, the direction of least pressure being that of the observed lines of force, and the difference of greatest and least pressures being proportional to the square of the intensity of the force at that point. Such a state of stress, if assumed to exist in the medium, and to be arranged according to the known laws regulating lines of force, will act upon the magnets, currents, and C, in the field with precisely the same resultant forces as those calculated on the ordinary hypothesis of direct action at a distance. This is true independently of any particular theory as to the cause of this state of stress, or the mode in which it can be sustained in the medium. We have therefore a satisfactory answer to the question, is there any mechanical hypothesis as to the condition of the medium indicated by lines of force, by which the observed resultant forces may be accounted for? The answer is, the lines of force indicate the direction of minimum pressure at every point of the medium. The second question must be, what is the mechanical cause of this difference of pressure in different directions? We have supposed, in the first part of this paper, that this difference of pressures is caused by molecular vortices, having their axes parallel to the lines of force. We also assumed, perfectly arbitrarily, that the direction of these vortices is such that, on looking along a line of force from south to north, we should see the vortices revolving in the direction of the hands of a watch. We found that the velocity of the circumference of each vortex must be proportional to the intensity of the magnetic force, and that the density of the substance of the vortex must be proportional to the capacity of the medium for magnetic induction. We have as yet given no answers to the questions, how are these vortices set in rotation, and why are they arranged according to the known laws of lines of force about magnets and currents? These questions are certainly of a higher order of difficulty than either of the former, and I wish to separate the suggestions I may offer by way of provisional answer to them, from the mechanical deductions which resolved the first question, and the hypothesis of vortices which gave a probable answer to the second. We have, in fact, now come to inquire into the physical connection of these vortices with electric currents, while we are still in doubt as to the nature of electricity, whether it is one substance, two substances, or not a substance at all, or in what way it differs from matter, and how it is connected with it. We know that the lines of force are affected by electric currents, and we know the distribution of those lines about a current, so that from the force we can determine the amount of the current. Assuming that our explanation of the lines of force by molecular vortices is correct, why does a particular distribution of vortices indicate an electric current? A satisfactory answer to this question would lead us a long way towards that of a very important one: what is an electric current? I have found great difficulty in conceiving of the existence of vortices in a medium, side by side, revolving in the same direction about parallel axes. The contiguous portions of consecutive vortices must be moving in opposite directions, and it is difficult to understand how the motion of one part of the medium can coexist with, and even produce, an opposite motion of a part in contact with it. The only conception which has at all aided me in conceiving of this kind of motion is that of the vortices being separated by a layer of particles, revolving each on its own axis in the opposite direction to that of the vortices, so that the contiguous surfaces of the particles and of the vortices have the same motion. In mechanism, when two wheels are intended to revolve in the same direction, a wheel is placed between them so as to be in gear with both, and this wheel is called an idle wheel. The hypothesis about the vortices which I have to suggest is that a layer of particles, acting as idle wheels, is interposed between each vortex and the next, so that each vortex has a tendency to make the neighboring vortices revolve in the same direction with itself. In mechanism, the idle wheel is generally made to rotate about a fixed axle, but in epicyclic trains and other contrivances, as, for instance, in Siemens's governor for steam engines *, we find idle wheels whose centers are capable of motion. In all these cases the motion of the center is the half-sum of the motions of the circumferences of the wheels between which it is placed. Let us examine the relations which must subsist between the motions of our vortices and those of the layer of particles interposed as idle wheels between them. Prop. IV. To determine the motion of a layer of particles separating two vortices. Let the circumferential velocity of a vortex, multiplied by the three-direction cosines of its axis respectively, be alpha, beta, gamma, as in Prop. 2. Let L, M, N be the direction cosines of the normal to any part of the surface of this vortex, the outside of the surface being regarded positive. Then the components of the velocity of the particles of the vortex at this part of its surface will be. If this portion of the surface be in contact with another vortex whose velocities are alpha, beta, gamma, then a layer of very small particles placed between them will have a velocity which will be the mean of the superficial velocities of the vortices which they separate, so that if u is the velocity of the particles in the direction of x, since the normal to the second vortex is in the opposite direction to that of the first. Prop. V to determine the whole amount of particles transferred across unit of area in the direction of x in unit of time. Let x1, y1, z1 be the coordinates of the center of the first vortex, x2, y2, z2 those of the second, and so on. Let v1, v2, and c be the volumes of the first, second, and c vortices, and v the sum of their volumes. Let ds be an element of the surface separating the first and second vortices, and x, y, z its coordinates. Let ρ be the quantity of particles on every unit of surface. Then if p be the whole quantity of particles transferred across unit of area in unit of time in the direction of x, the whole momentum parallel to x of the particles within the space whose volume is v will be Vp, and we shall have the summation being extended to every surface separating any two vortices within the volume 5. Let us consider the surface separating the first and second vortices. Let an element of this surface be ds, and let its direction cosines be L1, M1, N1 with respect to the first vortex, and L2, M2, N2 with respect to the second. Then we know that the values of alpha, beta, gamma vary with the position of the center of the vortex, so that we may write with similar equations for beta and gamma. The value of u may be written in effecting the summation of sigma u rho ds, We must remember that round any closed surface sigma L ds and all similar terms vanish. Also the terms of the form sigma Ly ds, where L and Y are measured in different directions, also vanish. But that terms of the form sigma Lx ds, where L and x refer to the same axis of coordinates, do not vanish, but are equal to the volume enclosed by the surface. The result is, or dividing by V equals V1 plus V2 plus and C. If we make then equation 33 will be identical with the first of equations 9, which give the relation between the quantity of an electric current and the intensity of the lines of force surrounding it. It appears therefore that, according to our hypothesis, an electric current is represented by the transference of the movable particles interposed between the neighboring vortices. We may conceive that these particles are very small compared with the size of a vortex, and that the mass of all the particles together is inappreciable compared with that of the vortices, and that a great many vortices, with their surrounding particles, are contained in a single complete molecule of the medium. The particles must be conceived to roll without sliding between the vortices which they separate, and not to touch each other, so that, as long as they remain within the same complete molecule, there is no loss of energy by resistance. When, however, there is a general transference of particles in one direction, they must pass from one molecule to another, and in doing so, may experience resistance, so as to waste electrical energy and generate heat. Now let us suppose the vortices arranged in a medium in any arbitrary manner. The quantities will then in general have values, so that there will at first be electrical currents in the medium. These will be opposed by the electrical resistance of the medium, so that, unless they are kept up by a continuous supply of force, they will quickly disappear, and we shall then have that is, alpha dx plus beta dy plus gamma dz will be a complete differential, see equations 15 and 16, so that our hypothesis accounts for the distribution of the lines of force. In plate 8, p. 488, fig. 1, let the vertical circle EE represent an electric current flowing from copper C to zinc Z through the conductor EE, as shown by the arrows. Let the horizontal circle MM represent a line of magnetic force embracing the electric circuit, the north and south directions being indicated by the lines SN and NS. Let the vertical circles V and V represent the molecular vortices of which the line of magnetic force is the axis. V revolves as the hands of a watch, and V, the opposite way. It will appear from this diagram that if V and V were contiguous vortices, particles placed between them would move downwards, and that if the particles were forced downwards by any cause, they would make the vortices revolve as in the figure. We have thus obtained a point of view from which we may regard the relation of an electric current to its lines of force as analogous to the relation of a toothed wheel or rack to wheels which it drives. In the first part of the paper we investigated the relations of the statical forces of the system. We have now considered the connection of the motions of the parts considered as a system of mechanism. It remains that we should investigate the dynamics of the system, and determine the forces necessary to produce given changes in the motions of the different parts. Prop. Vi. To determine the actual energy of a portion of a medium due to the motion of the vortices within it. Let alpha, beta, gamma be the components of the circumferential velocity, as in Prop. 2. Then the actual energy of the vortices in unit of volume will be proportional to the density and to the square of the velocity. As we do not know the distribution of density and velocity in each vortex, we cannot determine the numerical value of the energy directly. But since mu also bears a constant though unknown ratio to the mean density, let us assume that the energy in unit of volume is, where C is a constant to be determined. Let us take the case in which let, then phi1 is the potential at any point due to the magnetic system M1, and phi2 that due to the distribution of magnetism represented by M2. The actual energy of all the vortices is the integration being performed over all space. This may be shown by integration by parts, see Green's Essay on Electricity, page 10, to be equal to. Or since it has been proved, Green's Essay, page 10, that. Now let the magnetic system M1 remain at rest, and let M2 be moved parallel to itself in the direction of x through a space delta x, then, since phi1 depends on M1 only, it will remain as before, so that phi1 M1 will be constant, and since phi2 depends on M2 only, the distribution of phi2 about m2 will remain the same, so that phi2 square meters will be the same as before the change. The only part of E that will be altered is that depending on 2 phi1 square meter, because phi1 becomes on account of the displacement. The variation of actual energy due to the displacement is therefore. But by equation 12, the work done by the mechanical forces on m2 during the motion is. And since our hypothesis is a purely mechanical one, we must have by the conservation of force. That is, the loss of energy of the vortices must be made up by work done in moving magnets, so that the energy of the vortices in unit of volume is, and that of a vortex whose volume is V is. In order to produce or destroy this energy, work must be expended on, or received from, the vortex, either by the tangential action of the layer of particles in contact with it, or by change of form in the vortex. We shall first investigate the tangential action between the vortices and the layer of particles in contact with them. Prop. 7. To find the energy spent upon a vortex in unit of time by the layer of particles which surrounds it. Let P, Q, R be the forces acting on unity of the particles in the three coordinate directions, these quantities being functions of x, y, and z. Since each particle touches two vortices at the extremities of a diameter, the reaction of the particle on the vortices will be equally divided, and will be on each vortex for unity of the particles. But since the superficial density of the particles is, see equation 34, the forces on unit of surface of a vortex will be. Now let ds be an element of the surface of a vortex. Let the direction cosines of the normal be L, M, N. Let the coordinates of the element be x, y, z. Let the component velocities of the surface be u, v, w. Then the work expended on that element of surface will be. Let us begin with the first term, PUDS. P may be written and, remembering that the surface of the vortex is a closed one, so that and we find, and the whole work done on the vortex in unit of time will be. Prop. 8. To find the relations between the alterations of motion of the vortices and the forces P, Q, R which they exert on the layer of particles between them. Let V be the volume of a vortex, then by 46 its energy is. And, comparing this value with that given in equation 50, we find this equation being true for all values of alpha, beta, and gamma. First let beta and gamma vanish, and divide by alpha. We find, similarly, and from these equations we may determine the relation between the alterations of motion and the forces exerted on the layers of particles between the vortices, or, in the language of our hypothesis, the relation between changes in the state of the magnetic field and the electromotive forces thereby brought into play. In a memoir on the dynamical theory of diffraction, Cambridge Philosophical Transactions, Volume X, Part 1, Section 6, Professor Stokes has given a method by which we may solve equations 54 and find P, Q, and R in terms of the quantities on the right hand of those equations. I have pointed out the application of this method to questions in electricity and magnetism. Let us then find three quantities F, G, H from the equations, with the conditions, and differentiating 55 with respect to T, and comparing with 54, we find. We have thus determined three quantities, F, G, H, from which we can find P, Q, and R by considering these latter quantities as the rates at which the former ones vary. In the paper already referred to, I have given reasons for considering the quantities F, G, H as the resolved parts of that which Faraday has conjectured to exist, and has called the electrotonic state. In that paper I have stated the mathematical relations between this electrotonic state and the lines of magnetic force as expressed in equations 55, and also between the electrotonic state and electromotive force as expressed in equations 58. We must now endeavor to interpret them from a mechanical point of view in connection with our hypothesis. We shall in the first place examine the process by which the lines of force are produced by an electric current. Let AB, Plate 8, page 488, Fig. 2, represent a current of electricity in the direction from A to B. Let the large spaces above and below AB represent the vortices, and let the small circles separating the vortices represent the layers of particles placed between them, which in our hypothesis represent electricity. Now let an electric current from left to right commence in AB. The row of vortices GH above AB will be set in motion in the opposite direction to that of a watch. We shall call this direction plus, and that of a watch. We shall suppose the row of vortices KL still at rest, then the layer of particles between these rows will be acted on by the row GH on their lower sides, and will be at rest above. If they are free to move, they will rotate in the negative direction, and will at the same time move from right to left, or in the opposite direction from the current, and so form an induced electric current. If this current is checked by the electrical resistance of the medium, the rotating particles will act upon the row of vortices KL, and make them revolve in the positive direction till they arrive at such a velocity that the motion of the particles is reduced to that of rotation, and the induced current disappears. If, now, the primary current AB be stopped, the vortices in the row GH will be checked, while those of the row KL still continue in rapid motion. The momentum of the vortices beyond the layer of particles PQ will tend to move them from left to right, that is, in the direction of the primary current, but if this motion is resisted by the medium, the motion of the vortices beyond PQ will be gradually destroyed. It appears therefore that the phenomena of induced currents are part of the process of communicating the rotatory velocity of the vortices from one part of the field to another. As an example of the action of the vortices in producing induced currents, let us take the following case. Let B, plate 8, page 488, Fig. 3, be a circular ring, of uniform section, lapped uniformly with covered wire. It may be shown that if an electric current is passed through this wire, a magnet placed within the coil of wire will be strongly affected, but no magnetic effect will be produced on any external point. The effect will be that of a magnet bent round till its two poles are in contact. If the coil is properly made, no effect on a magnet placed outside it can be discovered, whether the current is kept constant or made to vary in strength. But if a conducting wire C be made to embrace the ring any number of times, an electromotive force will act on that wire whenever the current in the coil is made to vary, and if the circuit be closed, there will be an actual current in the wire C. This experiment shows that, in order to produce the electromotive force, it is not necessary that the conducting wire should be placed in a field of magnetic force, or that lines of magnetic force should pass through the substance of the wire or near it. All that is required is that lines of force should pass through the circuit of the conductor, and that these lines of force should vary in quantity during the experiment. In this case the vortices, of which we suppose the lines of magnetic force to consist, are all within the hollow of the ring, and outside the ring all is at rest. If there is no conducting circuit embracing the ring, then, when the primary current is made or broken, there is no action outside the ring, except an instantaneous pressure between the particles and the vortices which they separate. If there is a continuous conducting circuit embracing the ring, then, when the primary current is made, there will be a current in the opposite direction through C, and when it is broken, there will be a current through C in the same direction as the primary current. We may now perceive that induced currents are produced when the electricity yields to the electromotive force. This force, however, still existing when the formation of a sensible current is prevented by the resistance of the circuit. The electromotive force, of which the components are P, Q, R, arises from the action between the vortices and the interposed particles, when the velocity of rotation is altered in any part of the field. It corresponds to the pressure on the axle of a wheel in a machine when the velocity of the driving wheel is increased or diminished. The electrotonic state, whose components are F, G, H, is what the electromotive force would be if the currents, and C, to which the lines of force are due, instead of arriving at their actual state by degrees, had started instantaneously from rest with their actual values. It corresponds to the impulse which would act on the axle of a wheel in a machine if the actual velocity was suddenly given to the driving wheel, the machine being previously at rest. If the machine was suddenly stopped by stopping the driving wheel, each wheel would receive an impulse equal and opposite to that which it received when the machine was set in motion. This impulse may be calculated for any part of a system of mechanism, and may be called the reduced momentum of the machine for that point. In the varied motion of the machine, the actual force on any part arising from the variation of motion may be found by differentiating the reduced momentum with respect to the time, just as we have found that the electromotive force may be deduced from the electrotonic state by the same process. Having found the relation between the velocities of the vortices and the electromotive forces when the centers of the vortices are at rest, we must extend our theory to the case of a fluid medium containing vortices, and subject to all the varieties of fluid motion. If we fix our attention on any one elementary portion of a fluid, we shall find that it not only travels from one place to another, but also changes its form and position, so as to be elongated in certain directions and compressed in others, and at the same time, in the most general case, turned round by a displacement of rotation. These changes of form and position produce changes in the velocity of the molecular vortices, which we must now examine. The alteration of form and position may always be reduced to three simple extensions or compressions in the direction of three rectangular axes, together with three angular rotations about any set of three axes. We shall first consider the effect of three simple extensions or compressions. Prop. Ix. To find the variations of alpha, beta, gamma in the parallelepiped x, y, z when x becomes x plus delta x, y, y plus delta y, and z, z plus delta z, the volume of the figure remaining the same. By Prop. 2, we find for the work done by the vortices against pressure. And by Prop. Vi, we find for the variation of energy. The sum delta W plus delta E must be 0 by the conservation of energy, and delta xyz equals 0, since xyz is constant, so that, in order that this should be true independently of any relations between alpha, beta, and gamma, we must have Prop. X to find the variations of alpha, beta, gamma due to a rotation θ1 about the axis of x from y to z, a rotation θ2 about the axis of y from z to x, and a rotation θ3 about the axis of z from x to y. The axis of beta will move away from the axis of x by an angle θ3, so that beta resolved in the direction of x changes from 0 to b3. The axis of gamma approaches that of x by an angle θ2, so that the resolved part of gamma in direction x changes from 0 to g2. The resolved part of alpha in the direction of x changes by a quantity depending on the second power of the rotations, which may be neglected. The variations of alpha, beta, gamma from this cause are therefore the most general expressions for the distortion of an element produced by the displacement of its different parts depend on the 9 quantities. And these may always be expressed in terms of 9 other quantities, namely, 3 simple extensions or compressions. Along 3 axes properly chosen, x, y, z, the 9 direction cosines of these axes with their 6 connecting equations, which are equivalent to 3 independent quantities, and the 3 rotations θ1, θ2, θ3 about the axes of x, y, z. Let the direction cosines of x, with respect to x, y, z be L1, M1, N1, those of y, L2, M2, N2 and those of z, L3, M3, N3. Then we find, with similar equations for quantities involving delta y and delta z, let alpha, beta, gamma, be the values of alpha, beta, gamma referred to the axes x, y, z, then we shall then have, by substituting the values of alpha, beta, gamma, and comparing with equations 64, we find as the variation of alpha due to the change of form and position of the element. The variations of beta and gamma have similar expressions. Prop. 11. To find the electromotive forces in a moving body. The variation of the velocity of the vortices in a moving element is due to 2 causes: the action of the electromotive forces, and the change of form and position of the element. The whole variation of A is therefore. But since alpha is a function of x, y, z and t, the variation of alpha may be also written. Equating the 2 values of da and dividing by delta t, and remembering that in the motion of an incompressible medium, and that in the absence of free magnetism, we find, putting, and where f, g, and h are the values of the electrotonic components for a fixed point of space, our equation becomes. The expressions for the variations of beta and gamma give us 2 other equations which may be written down from symmetry. The complete solution of the 3 equations is. The first and second terms of each equation indicate the effect of the motion of any body in the magnetic field. The third term refers to changes in the electrotonic state produced by alterations of position or intensity of magnets or currents in the field, and psi is a function of x, y, z, and t, which is indeterminate as far as regards the solution of the original equations, but which may always be determined in any given case from the circumstances of the problem. The physical interpretation of psi is that it is the electric tension at each point of space. The physical meaning of the terms in the expression for the electromotive force depending on the motion of the body may be made simpler by supposing the field of magnetic force uniformly magnetized with intensity alpha in the direction of the axis of x. Then if L, m, n be the direction cosines of any portion of a linear conductor, and s its length, the electromotive force resolved in the direction of the conductor will be, or, that is, the product of ma, the quantity of magnetic induction over unit of area multiplied by the area swept out by the conductor S in unit of time, resolved perpendicular to the direction of the magnetic force. The electromotive force in any part of a conductor due to its motion is therefore measured by the number of lines of magnetic force which it crosses in unit of time, and the total electromotive force in a closed conductor is measured by the change of the number of lines of force which pass through it, and this is true whether the change be produced by the motion of the conductor or by any external cause. In order to understand the mechanism by which the motion of a conductor across lines of magnetic force generates an electromotive force in that conductor, we must remember that in Prop. X we have proved that the change of form of a portion of the medium containing vortices produces a change of the velocity of those vortices, and in particular that an extension of the medium in the direction of the axes of the vortices, combined with a contraction in all directions perpendicular to this, produces an increase of velocity of the vortices, while a shortening of the axis and bulging of the sides produces a diminution of the velocity of the vortices. This change of the velocity of the vortices arises from the internal effects of change of form, and is independent of that produced by external electromotive forces. If, therefore, the change of velocity be prevented or checked, electromotive forces will arise, because each vortex will press on the surrounding particles in the direction in which it tends to alter its motion. Let A, Fig. 4, page 488, represent the section of a vertical wire moving in the direction of the arrow from west to east, across a system of lines of magnetic force running north and south. The curved lines in Fig. 4 represent the lines of fluid motion about the wire being regarded as stationary, and the fluid as having a motion relative to it. It is evident that, from this figure, we can trace the variations of form of an element of the fluid, as the form of the element depends, not on the absolute motion of the whole system, but on the relative motion of its parts. In front of the wire, that is, on its east side, it will be seen that as the wire approaches each portion of the medium, that portion is more and more compressed in the direction from east to west, and extended in the direction from north to south, and since the axes of the vortices lie in the north and south direction, their velocity will continually tend to increase by Prop. X, unless prevented or checked by electromotive forces acting on the circumference of each vortex. We shall consider an electromotive force as positive when the vortices tend to move the interjacent particles upwards perpendicularly to the plane of the paper. The vortices appear to revolve as the hands of a watch when we look at them from south to north, so that each vortex moves upwards on its west side, and downwards on its east side. In front of the wire, therefore, where each vortex is striving to increase its velocity, the electromotive force upwards must be greater on its west than on its east side. There will therefore be a continual increase of upward electromotive force from the remote east, where it is 0, to the front of the moving wire, where the upward force will be strongest. Behind the wire a different action takes place. As the wire moves away from each successive portion of the medium, that portion is extended from east to west, and compressed from north to south, so as to tend to diminish the velocity of the vortices, and therefore to make the upward electromotive force greater on the east than on the west side of each vortex. The upward electromotive force will therefore increase continually from the remote west, where it is 0, to the back of the moving wire, where it will be strongest. It appears, therefore, that a vertical wire moving eastwards will experience an electromotive force tending to produce in it an upward current. If there is no conducting circuit in connection with the ends of the wire, no current will be formed, and the magnetic forces will not be altered. But if such a circuit exists, there will be a current, and the lines of magnetic force and the velocity of the vortices will be altered from their state previous to the motion of the wire. The change in the lines of force is shown in Fig. 5. The vortices in front of the wire, instead of merely producing pressures, actually increase in velocity, while those behind have their velocity diminished, and those at the sides of the wire have the direction of their axes altered, so that the final effect is to produce a force acting on the wire as a resistance to its motion. We may now recapitulate the assumptions we have made, and the results we have obtained. 1. Magneto-electric phenomena are due to the existence of matter under certain conditions of motion or of pressure in every part of the magnetic field, and not to direct action at a distance between the magnets or currents. The substance producing these effects may be a certain part of ordinary matter, or it may be an ether associated with matter. Its density is greatest in iron, and least in diamagnetic substances, but it must be in all cases, except that of iron, very rare, since no other substance has a large ratio of magnetic capacity to what we call a vacuum. 2. The condition of any part of the field, through which lines of magnetic force pass, is one of unequal pressure in different directions, the direction of the lines of force being that of least pressure, so that the lines of force may be considered lines of tension. 3. This inequality of pressure is produced by the existence in the medium of vortices or eddies, having their axes in the direction of the lines of force, and having the direction of rotation determined by that of the lines of force. We have supposed that the direction was that of a watch to a spectator looking from south to north. We might with equal propriety have chosen the reverse direction, as far as known facts are concerned, by supposing resinous electricity instead of vitreous to be positive. The effect of these vortices depends on their density, and on their velocity at the circumference, and is independent of their diameter. The density must be proportional to the capacity of the substance for magnetic induction, that of the vortices in air being 1. The velocity must be very great, in order to produce so powerful effects in so rare a medium. The size of the vortices is indeterminate, but is probably very small as compared with that of a complete molecule of ordinary matter. 4. The vortices are separated from each other by a single layer of round particles, so that a system of cells is formed, the partitions being these layers of particles, and the substance of each cell being capable of rotating as a vortex. 5. The particles forming the layer are in rolling contact with both the vortices which they separate, but do not rub against each other. They are perfectly free to roll between the vortices and so to change their place, provided they keep within one complete molecule of the substance, but in passing from one molecule to another they experience resistance, and generate irregular motions, which constitute heat. These particles, in our theory, play the part of electricity. Their motion of translation constitutes an electric current, their rotation serves to transmit the motion of the vortices from one part of the field to another, and the tangential pressures thus called into play constitute electromotive force. The conception of a particle having its motion connected with that of a vortex by perfect rolling contact may appear somewhat awkward. I do not bring it forward as a mode of connection existing in nature, or even as that which I would willingly assent to as an electrical hypothesis. It is, however, a mode of connection which is mechanically conceivable and easily investigated, and it serves to bring out the actual mechanical connections between the known electromagnetic phenomena, so that I venture to say that anyone who understands the provisional and temporary character of this hypothesis will find himself rather helped than hindered by it in his search after the true interpretation of the phenomena. The action between the vortices and the layers of particles is in part tangential, so that if there were any slipping or differential motion between the parts in contact, there would be a loss of the energy belonging to the lines of force, and a gradual transformation of that energy into heat. Now we know that the lines of force about a magnet are maintained for an indefinite time without any expenditure of energy, so that we must conclude that wherever there is tangential action between different parts of the medium, there is no motion of slipping between those parts. We must therefore conceive that the vortices and particles roll together without slipping, and that the interior strata of each vortex receive their proper velocities from the exterior stratum without slipping, that is, the angular velocity must be the same throughout each vortex. The only process in which electromagnetic energy is lost and transformed into heat is in the passage of electricity from one molecule to another. In all other cases the energy of the vortices can only be diminished when an equivalent quantity of mechanical work is done by magnetic action. 6. The effect of an electric current upon the surrounding medium is to make the vortices in contact with the current revolve so that the parts next to the current move in the same direction as the current. The parts furthest from the current will move in the opposite direction, and if the medium is a conductor of electricity, so that the particles are free to move in any direction, FAF particles touching the outside of these vortices will be moved in a direction contrary to that of the current, so that there will be an induced current in the opposite direction to the primary one. If there were no resistance to the motion of the particles, the induced current would be equal and opposite to the primary one, and would continue as long as the primary current lasted, so that it would prevent all action of the primary current at a distance. If there is a resistance to the induced current, its particles act upon the vortices beyond them, and transmit the motion of rotation to them, till at last all the vortices in the medium are set in motion with such velocities of rotation that the particles between them have no motion except that of rotation, and do not produce currents. In the transmission of the motion from one vortex to another, there arises a force between the particles and the vortices, by which the particles are pressed in one direction and the vortices in the opposite direction. We call the force acting on the particles the electromotive force. The reaction on the vortices is equal and opposite, so that the electromotive force cannot move any part of the medium as a whole, it can only produce currents. When the primary current is stopped, the electromotive forces all act in the opposite direction. 7. When an electric current or a magnet is moved in presence of a conductor, the velocity of rotation of the vortices in any part of the field is altered by that motion. The force by which the proper amount of rotation is transmitted to each vortex constitutes in this case also an electromotive force, and, if permitted, will produce currents. 8. When a conductor is moved in a field of magnetic force, the vortices in it and in its neighborhood are moved out of their places, and are changed in form. The force arising from these changes constitutes the electromotive force on a moving conductor, and is found by calculation to correspond with that determined by experiment. We have now shown in what way electromagnetic phenomena may be imitated by an imaginary system of molecular vortices. Those who have been already inclined to adopt an hypothesis of this kind, will find here the conditions which must be fulfilled in order to give it mathematical coherence, and a comparison, so far satisfactory, between its necessary results and known facts. Those who look in a different direction for the explanation of the facts, may be able to compare this theory with that of the existence of currents flowing freely through bodies, and with that which supposes electricity to act at a distance with a force depending on its velocity, and therefore not subject to the law of conservation of energy. The facts of electromagnetism are so complicated and various, that the explanation of any number of them by several different hypotheses must be interesting, not only to physicists, but to all who desire to understand how much evidence the explanation of phenomena lends to the credibility of a theory, or how far we ought to regard a coincidence in the mathematical expression of two sets of phenomena as an indication that these phenomena are of the same kind. We know that partial coincidences of this kind have been discovered, and the fact that they are only partial is proved by the divergence of the laws of the two sets of phenomena in other respects. We may chance to find, in the higher parts of physics, instances of more complete coincidence, which may require much investigation to detect their ultimate divergence. Note: since the first part of this paper was written, I have seen in Krell's journal for 1859, a paper by Professor Helmholtz on fluid motion, in which he has pointed out that the lines of fluid motion are arranged according to the same laws as the lines of magnetic force, the path of an electric current corresponding to a line of axes of those particles of the fluid which are in a state of rotation. This is an additional instance of a physical analogy, the investigation of which may illustrate both electromagnetism and hydrodynamics. Fig. 1, Fig. 2, Fig. 3, Fig. 4, Fig. 5, Fig. 6, Fig. 7, Fig. 8, Fig. 9, Fig. 10, from the Philosophical Magazine for January and February 1862. Part 3. The theory of molecular vortices applied to statical electricity. In the first part of this paper I have shown how the forces acting between magnets, electric currents, and matter capable of magnetic induction may be accounted for on the hypothesis of the magnetic field being occupied with innumerable vortices of revolving matter, their axes coinciding with the direction of the magnetic force at every point of the field. The centrifugal force of these vortices produces pressures distributed in such a way that the final effect is a force identical in direction and magnitude with that which we observe. In the second part I described the mechanism by which these rotations may be made to coexist, and to be distributed according to the known laws of magnetic lines of force. I conceived the rotating matter to be the substance of certain cells, divided from each other by cell walls composed of particles which are very small compared with the cells, and that it is by the motions of these particles, and their tangential action on the substance in the cells, that the rotation is communicated from one cell to another. I have not attempted to explain this tangential action, but it is necessary to suppose, in order to account for the transmission of rotation from the exterior to the interior parts of each cell, that the substance in the cells possesses elasticity of figure, similar in kind, though different in degree, to that observed in solid bodies. The undulatory theory of light requires us to admit this kind of elasticity in the luminiferous medium, in order to account for transverse vibrations. We need not then be surprised if the magnetoelectric medium possesses the same property. According to our theory, the particles which form the partitions between the cells constitute the matter of electricity. The motion of these particles constitutes an electric current. The tangential force with which the particles are pressed by the matter of the cells is electromotive force, and the pressure of the particles on each other corresponds to the tension or potential of the electricity. If we can now explain the condition of a body with respect to the surrounding medium when it is said to be charged with electricity, and account for the forces acting between electrified bodies, we shall have established a connection between all the principal phenomena of electrical science. We know by experiment that electric tension is the same thing, whether observed in statical or in current electricity, so that an electromotive force produced by magnetism may be made to charge a Leyden jar, as is done by the coil machine. When a difference of tension exists in different parts of any body, the electricity passes, or tends to pass, from places of greater to places of smaller tension. If the body is a conductor, an actual passage of electricity takes place, and if the difference of tensions is kept up, the current continues to flow with a velocity proportional inversely to the resistance, or directly to the conductivity of the body. The electric resistance has a very wide range of values, that of the metals being the smallest, and that of glass being so great that a charge of electricity has been preserved in a glass vessel for years without penetrating the thickness of the glass. Bodies which do not permit a current of electricity to flow through them are called insulators. But though electricity does not flow through them, the electrical effects are propagated through them, and the amount of these effects differs according to the nature of the body, so that equally good insulators may act differently as dielectrics. Here then we have two independent qualities of bodies, one by which they allow of the passage of electricity through them, and the other by which they allow of electrical action being transmitted through them without any electricity being allowed to pass. A conducting body may be compared to a porous membrane which opposes more or less resistance to the passage of a fluid, while a dielectric is like an elastic membrane which may be impervious to the fluid, but transmits the pressure of the fluid on one side to that on the other. As long as electromotive force acts on a conductor, it produces a current which, as it meets with resistance, occasions a continual transformation of electrical energy into heat, which is incapable of being restored again as electrical energy by any reversion of the process. Electromotive force acting on a dielectric produces a state of polarization of its parts similar in distribution to the polarity of the particles of iron under the influence of a magnet *, and, like the magnetic polarization, capable of being described as a state in which every particle has its poles in opposite conditions. In a dielectric under induction, we may conceive that the electricity in each molecule is so displaced that one side is rendered positively, and the other negatively electrical, but that the electricity remains entirely connected with the molecule, and does not pass from one molecule to another. The effect of this action on the whole dielectric mass is to produce a general displacement of the electricity in a certain direction. This displacement does not amount to a current, because when it has attained a certain value it remains constant, but it is the commencement of a current, and its variations constitute currents in the positive or negative direction, according as the displacement is increasing or diminishing. The amount of the displacement depends on the nature of the body, and on the electromotive force, so that if h is the displacement, r the electromotive force, and E a coefficient depending on the nature of the dielectric, and if r is the value of the electric current due to displacement. These relations are independent of any theory about the internal mechanism of dielectrics, but when we find electromotive force producing electric displacement in a dielectric, and when we find the dielectric recovering from its state of electric displacement with an equal electromotive force, we cannot help regarding the phenomena as those of an elastic body, yielding to a pressure, and recovering its form when the pressure is removed. According to our hypothesis, the magnetic medium is divided into cells, separated by partitions formed of a stratum of particles which play the part of electricity. When the electric particles are urged in any direction, they will, by their tangential action on the elastic substance of the cells, distort each cell, and call into play an equal and opposite force arising from the elasticity of the cells. When the force is removed, the cells will recover their form, and the electricity will return to its former position. In the following investigation I have considered the relation between the displacement and the force producing it, on the supposition that the cells are spherical. The actual form of the cells probably does not differ from that of a sphere sufficiently to make much difference in the numerical result. I have deduced from this result the relation between the statical and dynamical measures of electricity, and have shown, by a comparison of the electromagnetic experiments of M.M. Kohlrausch and Weber with the velocity of light as found by M. Fizeau, that the elasticity of the magnetic medium in air is the same as that of the luminiferous medium, if these two coexistent, coextensive, and equally elastic media are not rather one medium. It appears also from Prop. 15, that the attraction between two electrified bodies depends on the value of E2, and that therefore it would be less in turpentine than in air, if the quantity of electricity in each body remains the same. If, however, the potentials of the two bodies were given, the attraction between them would vary inversely as E2, and would be greater in turpentine than in air. Prop. 12. To find the conditions of equilibrium of an elastic sphere whose surface is exposed to normal and tangential forces, the tangential forces being proportional to the sine of the distance from a given point on the sphere. Let the axis of z be the axis of spherical coordinates. Let xi, eta, zeta be the displacements of any particle of the sphere in the directions of x, y, and z. Let pxx, pyy, pzz be the stresses normal to planes perpendicular to the three axes, and let pyz, pzx, pxy be the stresses of distortion in the planes yz, zx, and xy. Let mu be the coefficient of cubic elasticity, so that if. Let m be the coefficient of rigidity, so that. Then we have the following equations of elasticity in an isotropic medium. With similar equations in y and z, and also. In the case of the sphere, let us assume the radius equals alpha, and. Then. The equation of internal equilibrium with respect to z is. Which is satisfied in this case if. The tangential stress on the surface of the sphere, whose radius is at an angular distance theta from the axis in plane xz. In order that t may be proportional to sin theta, the first term must vanish, and therefore. The normal stress on the surface at any point is. Or by. And, 9. 0. Closing parenthesis. The tangential displacement of any point is. The normal displacement is. If we make there will be no normal displacement, and the displacement will be entirely tangential, and we shall have. The whole work done by the superficial forces is. The summation being extended over the surface of the sphere. The energy of elasticity in the substance of the sphere is. The summation being extended to the whole contents of the sphere. We find, as we ought, that these quantities have the same value, namely. We may now suppose that the tangential action on the surface arises from a layer of particles in contact with it, the particles being acted on by their own mutual pressure, and acting on the surfaces of the two cells with which they are in contact. We assume the axis of z to be in the direction of maximum variation of the pressure among the particles, and we have to determine the relation between an electromotive force R acting on the particles in that direction, and the electric displacement h which accompanies it. Prop. 13. To find the relation between electromotive force and electric displacement when a uniform electromotive force R acts parallel to the axis of z. Take any element delta S of the surface, covered with a stratum whose density is ρ, and having its normal inclined theta to the axis of z, then the tangential force upon it will be T being, as before, the tangential force on each side of the surface. Putting as in equation 34, we find the displacement of electricity due to the distortion of the sphere is. And if h is the electric displacement per unit of volume, we shall have. Or so that. Or we may write, provided we assume. Finding E and F from 87 and 90, we get. The ratio of m to mu varies in different substances, but in a medium whose elasticity depends entirely upon forces acting between pairs of particles, this ratio is that of 6 to 5, and in this case, when the resistance to compression is infinitely greater than the resistance to distortion, as in a liquid rendered slightly elastic by gum or jelly, the value of E2 must lie between these limits. It is probable that the substance of our cells is of the former kind, and that we must use the first value of E2, which is that belonging to a hypothetically perfect solid, in which Prop. 14, to correct the equations 9 of electric currents for the effect due to the elasticity of the medium. We have seen that electromotive force and electric displacement are connected by equation 105. Differentiating this equation with respect to t, we find, showing that when the electromotive force varies, the electric displacement also varies. But a variation of displacement is equivalent to a current, and this current must be taken into account in equations 9 and added to R. The three equations then become, where P, Q, R are the electric currents in the directions of X, Y, and Z, alpha, beta, gamma are the components of magnetic intensity, and P, Q, R are the electromotive forces. Now if E be the quantity of free electricity in unit of volume, then the equation of continuity will be, differentiating 112 with respect to X, Y, and Z respectively, and substituting, we find, whence the constant being omitted, because E equals 0 when there are no electromotive forces. Prop. 15. To find the force acting between two electrified bodies. The energy in the medium arising from the electric displacements is, where P, Q, R are the forces, and F, G, H the displacements. Now when there is no motion of the bodies or alteration of forces, it appears from equations 77, that. And we know by 105 that whence integrating by parts throughout all space, and remembering that psi vanishes at an infinite distance. Or by 115. Now let there be two electrified bodies, and let E1 be the distribution of electricity in the first, and psi1 the electric tension due to it, and let E2 be the distribution of electricity in the second body, and psi2 the tension due to it. Then the whole tension at any point will be psi1 plus psi2, and the expansion for U will become. Let the body whose electricity is E1 be moved in any way, the electricity moving along with the body, then since the distribution of tension psi1 moves with the body, the value of psi1 E1 remains the same. Psi2 E2 also remains the same, and Green has shown, Essay on Electricity, page 10, that psi1 E2 equals psi2 E1, so that the work done by moving the body against electric forces. And if E1 is confined to a small body, or, where F is the resistance and Dr the motion, if the body E2 be small, then if R is the distance from E2, equation 123 gives whence or the force is a repulsion varying inversely as the square of the distance. Now let eta1 and eta2 be the same quantities of electricity measured statically, then we know by definition of electrical quantity. And this will be satisfied provided, so that the quantity E previously determined in Prop. 13 is the number by which the electrodynamic measure of any quantity of electricity must be multiplied to obtain its electrostatic measure. That electric current which, circulating round a ring whose area is unity, produces the same effect on a distant magnet as a magnet would produce whose strength is unity and length unity placed perpendicularly to the plane of the ring, is a unit current, and E units of electricity, measured statically, traverse the section of this current in 1 second, these units being such that any two of them, placed at unit of distance, repel each other with unit of force. We may suppose either that E units of positive electricity move in the positive direction through the wire, or that E units of negative electricity move in the negative direction, or, thirdly, that E units of positive electricity move in the positive direction, while E units of negative electricity move in the negative direction at the same time. The last is the supposition on which MM. Weber and Kohlrausch proceed, who have found the unit of length being the millimeter, and that of time being 1 second, whence Prop. 16, to find the rate of propagation of transverse vibrations through the elastic medium of which the cells are composed, on the supposition that its elasticity is due entirely to forces acting between pairs of particles. By the ordinary method of investigation we know that where m is the coefficient of transverse elasticity, and ρ is the density. By referring to the equations of Part 1, it will be seen that if ρ is the density of the matter of the vortices, and μ is the coefficient of magnetic induction. Whence, and by, 108. In air or vacuum μ equals 1, and therefore the velocity of light in air, as determined by m physio, is 70,843 leagues per second, 25 leagues to a degree, which gives the velocity of transverse undulations in our hypothetical medium, calculated from the electromagnetic experiments of MM. Kohlrausch and Weber agrees so exactly with the velocity of light calculated from the optical experiments of M. Physio, that we can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Prop. 17. To find the electric capacity of a Leyden jar composed of any given dielectric placed between two conducting surfaces. Let the electric tensions or potentials of the two surfaces be psi1 and psi2. Let S be the area of each surface, and theta the distance between them, and let E and E be the quantities of electricity on each surface, then the capacity. Within the dielectric we have the variation of psi perpendicular to the surface. Beyond either surface this variation is zero. Hence by 115, applied at the surface, the electricity on unit of area I sand we deduce the whole capacity of the apparatus. So that the quantity of electricity required to bring the one surface to a given tension varies directly as the surface, inversely as the thickness, and inversely as the square of E. Now the coefficient of induction of dielectrics is deduced from the capacity of induction apparatus formed of them, so that if D is that coefficient, D varies inversely as E2, and is unity for air. Hence, where V and V1 are the velocities of light in air and in the medium. Now if I is the index of refraction, and so that the inductive power of a dielectric varies directly as the square of the index of refraction, and inversely as the magnetic inductive power. In dense media, however, the optical, electric, and magnetic phenomena may be modified in different degrees by the particles of gross matter, and their mode of arrangement may influence these phenomena differently in different directions. The axes of optical, electric, and magnetic properties will probably coincide, but on account of the unknown and probably complicated nature of the reactions of the heavy particles on the ethereal medium, it may be impossible to discover any general numerical relations between the optical, electric, and magnetic ratios of these axes. It seems probable, however, that the value of E, for any given axis, depends upon the velocity of light whose vibrations are parallel to that axis, or whose plane of polarization is perpendicular to that axis. In a uniaxial crystal, the axial value of E will depend on the velocity of the extraordinary ray, and the equatorial value will depend on that of the ordinary ray. In positive crystals, the axial value of E will be the least and in negative the greatest. The value of D1, which varies inversely as E2 will, coeteris paribus, be greatest for the axial direction in positive crystals, and for the equatorial direction in negative crystals, such as Iceland spar. If a spherical portion of a crystal, radius equals alpha, be suspended in a field of electric force which would act on unit of electricity with force equals 1, and if D1 and D2 be the coefficients of dielectric induction along the two axes in the plane of rotation, then if theta be the inclination of the axis to the electric force, the moment tending to turn the sphere will being the axis of greatest dielectric induction, D1, will tend to become parallel to the lines of electric force. PAETIV. The theory of molecular YORTICES applied to the action of magnetism on polarized light. The connection between the distribution of lines of magnetic force and that of electric currents may be completely expressed by saying that the work done on a unit of imaginary magnetic matter, when carried round any closed curve, is proportional to the quantity of electricity which passes through the closed curve. The mathematical form of this law may be expressed as in equations, which I here repeat, where alpha, beta, gamma are the rectangular components of magnetic intensity, and P, Q, R are the rectangular components of steady electric currents. The same mathematical connection is found between other sets of phenomena in physical science. 1. If alpha, beta, gamma represent displacements, velocities, or forces, then P, Q, R will be rotatory displacements, velocities of rotation, or moments of couples producing rotation, in the elementary portions of the mass. 2. If alpha, beta, gamma represent rotatory displacements in a uniform and continuous substance, then P, Q, R represent the relative linear displacement of a particle with respect to those in its immediate neighborhood. See a paper by Professor W. Thompson on a mechanical representation of electric, magnetic, and galvanic forces, Camb, and Dublin Math. Journal, January 1847. 3. If alpha, beta, gamma represent the rotatory velocities of vortices whose centers are fixed, then P, Q, R represent the velocities with which loose particles placed between them would be carried along. See the second part of this paper, Phil. Mag. April, 1861, page 469. It appears from all these instances that the connection between magnetism and electricity has the same mathematical form as that between certain pairs of phenomena, of which one has a linear and the other a rotatory character. Professor Challis conceives magnetism to consist in currents of a fluid whose direction corresponds with that of the lines of magnetic force, and electric currents, on this theory, are accompanied by, if not dependent on, a rotatory motion of the fluid about the axis of the current. Professor Helmholtz has investigated the motion of an incompressible fluid, and has conceived lines drawn so as to correspond at every point with the instantaneous axis of rotation of the fluid there. He has pointed out that the lines of fluid motion are arranged according to the same laws with respect to the lines of rotation, as those by which the lines of magnetic force are arranged with respect to electric currents. On the other hand, in this paper I have regarded magnetism as a phenomenon of rotation, and electric currents as consisting of the actual translation of particles, thus assuming the inverse of the relation between the two sets of phenomena. Now it seems natural to suppose that all the direct effects of any cause which is itself of a longitudinal character, must be themselves longitudinal, and that the direct effects of a rotatory cause must be themselves rotatory. A motion of translation along an axis cannot produce a rotation about that axis unless it meets with some special mechanism, like that of a screw, which connects a motion in a given direction along the axis with a rotation in a given direction round it, and a motion of rotation, though it may produce tension along the axis, cannot of itself produce a current in one direction along the axis rather than the other. Electric currents are known to produce effects of transference in the direction of the current. They transfer the electrical state from one body to another, and they transfer the elements of electrolytes in opposite directions, but they do not cause the plane of polarization of light to rotate when the light traverses the axis of the current. On the other hand, the magnetic state is not characterized by any strictly longitudinal phenomenon. The north and south poles differ only in their names, and these names might be exchanged without altering the statement of any magnetic phenomenon, whereas the positive and negative poles of a battery are completely distinguished by the different elements of water which are evolved there. The magnetic state, however, is characterized by a well-marked rotatory phenomenon discovered by Faraday, the rotation of the plane of polarized light when transmitted along the lines of magnetic force. When a transparent diamagnetic substance has a ray of plane polarized light passed through it, and if lines of magnetic force are then produced in the substance by the action of a magnet or of an electric current, the plane of polarization of the transmitted light is found to be changed, and to be turned through an angle depending on the intensity of the magnetizing force within the substance. The direction of this rotation in diamagnetic substances is the same as that in which positive electricity must circulate round the substance in order to produce the actual magnetizing force within it. Or if we suppose the horizontal part of terrestrial magnetism to be the magnetizing force acting on the substance, the plane of polarization would be turned in the direction of the Earth's true rotation, that is, from west upwards to east. In paramagnetic substances, M. Verde has found that the plane of polarization is turned in the opposite direction, that is, in the direction in which negative electricity would flow if the magnetization were affected by a helix surrounding the substance. In both cases, the absolute direction of the rotation is the same, whether the light passes from north to south or from south to north, a fact which distinguishes this phenomenon from the rotation produced by quartz, turpentine, and C, in which the absolute direction of rotation is reversed when that of the light is reversed. The rotation in the latter case, whether related to an axis, as in quartz, or not so related, as in fluids, indicates a relation between the direction of the ray and the direction of rotation, which is similar in its formal expression to that between the longitudinal and rotatory motions of a right-handed or a left-handed screw, and it indicates some property of the substance the mathematical form of which exhibits right-handed or left-handed relations, such as are known to appear in the external forms of crystals having these properties. In the magnetic rotation no such relation appears, but the direction of rotation is directly connected with that of the magnetic lines, in a way which seems to indicate that magnetism is really a phenomenon of rotation. The transference of electrolytes in fixed directions by the electric current, and the rotation of polarized light in fixed directions by magnetic force, are the facts the consideration of which has induced me to regard magnetism as a phenomenon of rotation, and electric currents as phenomena of translation, instead of following out the analogy pointed out by Helmholtz, or adopting the theory propounded by Professor Challis. The theory that electric currents are linear, and magnetic forces rotatory phenomena, agrees so far with that of Ampere and Weber, and the hypothesis that the magnetic rotations exist wherever magnetic force extends, that the centrifugal force of these rotations accounts for magnetic attractions, and that the inertia of the vortices accounts for induced currents, is supported by the opinion of Professor W. Thomson. In fact, the whole theory of molecular vortices developed in this paper has been suggested to me by observing the direction in which those investigators who study the action of media are looking for the explanation of electromagnetic phenomena. Professor Thomson has pointed out that the cause of the magnetic action on light must be a real rotation going on in the magnetic field. A right-handed circularly polarized ray of light is found to travel with a different velocity according as it passes from north to south, or from south to north, along a line of magnetic force. Now, whatever theory we adopt about the direction of vibrations in plane polarized light, the geometrical arrangement of the parts of the medium during the passage of a right-handed circularly polarized ray is exactly the same whether the ray is moving north or south. The only difference is that the particles describe their circles in opposite directions. Since, therefore, the configuration is the same in the two cases, the forces acting between particles must be the same in both, and the motions due to these forces must be equal in velocity if the medium was originally at rest, but if the medium be in a state of rotation, either as a whole or in molecular vortices, the circular vibrations of light may differ in velocity according as their direction is similar or contrary to that of the vortices. We have now to investigate whether the hypothesis developed in this paper that magnetic force is due to the centrifugal force of small vortices, and that these vortices consist of the same matter the vibrations of which constitute light leads to any conclusions as to the effect of magnetism on polarized light. We suppose transverse vibrations to be transmitted through a magnetized medium. How will the propagation of these vibrations be affected by the circumstance that portions of that medium are in a state of rotation? In the following investigation, I have found that the only effect which the rotation of the vortices will have on the light will be to make the plane of polarization rotate in the same direction as the vortices, through an angle proportional a. to the thickness of the substance, b. to the resolved part of the magnetic force parallel to the ray, c. to the index of refraction of the ray, d. inversely to the square of the wavelength in air, e. to the mean radius of the vortices, f. to the capacity for magnetic induction. A and B have been fully investigated by M. Verde, who has shown that the rotation is strictly proportional to the thickness and to the magnetizing force, and that, when the ray is inclined to the magnetizing force, the rotation is as the cosine of that inclination. D has been supposed to give the true relation between the rotation of different rays, but it is probable that C must be taken into account in an accurate statement of the phenomena. The rotation varies, not exactly inversely as the square of the wavelength, but a little faster, so that for the highly refrangible rays the rotation is greater than that given by this law, but more nearly as the index of refraction divided by the square of the wavelength. The relation, E, between the amount of rotation and the size of the vortices shows that different substances may differ in rotating power independently of any observable difference in other respects. We know nothing of the absolute size of the vortices, and on our hypothesis the optical phenomena are probably the only data for determining their relative size in different substances. On our theory, the direction of the rotation of the plane of polarization depends on that of the mean moment of momenta, or angular momentum, of the molecular vortices, and since M. Verde has discovered that magnetic substances have an effect on light opposite to that of diamagnetic substances, it follows that the molecular rotation must be opposite in the two classes of substances. We can no longer, therefore, consider diamagnetic bodies as being those whose coefficient of magnetic induction is less than that of space empty of gross matter. We must admit the diamagnetic state to be the opposite of the paramagnetic, and that the vortices, or at least the influential majority of them, in diamagnetic substances, revolve in the direction in which positive electricity revolves in the magnetizing bobbin, while in paramagnetic substances they revolve in the opposite direction. This result agrees so far with that part of the theory of M. Weber which refers to the paramagnetic and diamagnetic conditions. M. Weber supposes the electricity in paramagnetic bodies to revolve the same way as the surrounding helix, while in diamagnetic bodies it revolves the opposite way. Now if we regard negative or resinous electricity as a substance the absence of which constitutes positive or vitreous electricity, the results will be those actually observed. This will be true independently of any other hypothesis than that of M. Weber about magnetism and diamagnetism, and does not require us to admit either M. Weber's theory of the mutual action of electric particles in motion, or our theory of cells and cell walls. I am inclined to believe that iron differs from other substances in the manner of its action as well as in the intensity of its magnetism, and I think its behavior may be explained on our hypothesis of molecular vortices, by supposing that the particles of the iron itself are set in rotation by the tangential action of the vortices, in an opposite direction to their own. These large heavy particles would thus be revolving exactly as we have supposed the infinitely small particles constituting electricity to revolve, but without being free like them to change their place and form currents. The whole energy of rotation of the magnetized field would thus be greatly increased, as we know it to be, but the angular momentum of the iron particles would be opposite to that of the ethereal cells and immensely greater, so that the total angular momentum of the substance will be in the direction of rotation of the iron, or the reverse of that of the vortices. Since, however, the angular momentum depends on the absolute size of the revolving portions of the substance, it may depend on the state of aggregation or chemical arrangement of the elements, as well as on the ultimate nature of the components of the substance. Other phenomena in nature seem to lead to the conclusion that all substances are made up of a number of parts, finite in size, the particles composing these parts being themselves capable of internal motion. Prop. 18. To find the angular momentum of a vortex. The angular momentum of any material system about an axis is the sum of the products of the mass, dm, of each particle multiplied by twice the area it describes about that axis in unit of time, or if A is the angular momentum about the axis of x. As we do not know the distribution of density within the vortex, we shall determine the relation between the angular momentum and the energy of the vortex which was found in Prop. Vi. Since the time of revolution is the same throughout the vortex, the mean angular velocity omega will be uniform and equals, where alpha is the velocity at the circumference, and r the radius. Then, and the energy whence, for the axis of x, with similar expressions for the other axes, v being the volume, and r the radius of the vortex. Prop. 19. To determine the conditions of undulatory motion in a medium containing vortices, the vibrations being perpendicular to the direction of propagation. Let the waves be plane waves propagated in the direction of 2, and let the axis of x and y be taken in the directions of greatest and least elasticity in the plane xy. Let x and y represent the displacement parallel to these axes, which will be the same throughout the same wave surface, and therefore we shall have x and y functions of z and t only. Let x be the tangential stress on unit of area parallel to xy, tending to move the part next the origin in the direction of x. Let y be the corresponding tangential stress in the direction of y. Let k1 and k2 be the coefficients of elasticity with respect to these two kinds of tangential stress. Then, if the medium is at rest. Now let us suppose vortices in the medium whose velocities are represented as usual by the symbols alpha, beta, gamma, and let us suppose that the value of alpha is increasing at the rate on account of the action of the tangential stresses alone, there being no electromotive force in the field. The angular momentum in the stratum whose area is unity, and thickness dz, is therefore increasing at the rate, and if the part of the force y which produces this effect is y, then the moment of y is yds, so that the complete value of y when the vortices are in a state of varied motion is. Similarly, the whole force acting upon a stratum whose thickness is dz and area unity, is in the direction of x, and in direction of y. The mass of the stratum is ρ dz, so that we have as the equations of motion Now the changes of velocity are produced by the motion of the medium containing the vortices, which distorts and twists every element of its mass, so that we must refer to prop x. To determine these quantities in terms of the motion, we find there at equation 68. Since delta x and delta y are functions of z and t only, we may write this equation. And in like manner. So that if we now put we may write the equations of motion. These equations may be satisfied by the values provided. And, multiplying the last two equations together, we find an equation quadratic with respect to m2, the solution of which is these values of m2 being put in the equations will each give a ratio of a and b, which being substituted in equations 149 will satisfy the original equations 148. The most general undulation of such a medium is therefore compounded of two elliptic undulations of different eccentricities traveling with different velocities and rotating in opposite directions. The results may be more easily explained in the case in which A equals B. Then, let us suppose that the value of A is unity for both vibrations, then we shall have the first terms of x and y represent a circular vibration in the negative direction, and the second term a circular vibration in the positive direction, the positive having the greatest velocity of propagation. Combining the terms, we may write where and these are the equations of an undulation consisting of a plane vibration whose periodic time is and wavelength propagated in the direction of z with a velocity while the plane of the vibration revolves about the axis of z in the positive direction so as to complete a revolution. When now let us suppose c too small, then we may write and remembering that we find here r is the radius of the vortices, an unknown quantity, ρ is the density of the luminiferous medium in the body, which is also unknown. But if we adopt the theory of Fresnel, and make S the density in space devoid of gross matter, then where I is the index of refraction, on the theory of McCulloch and Newman. In all bodies, mu is the coefficient of magnetic induction, which is unity in empty space or in air. Gamma is the velocity of the vortices at their circumference estimated in the ordinary units. Its value is unknown, but it is proportional to the intensity of the magnetic force. Let Z be the magnetic intensity of the field, measured as in the case of terrestrial magnetism, then the intrinsic energy in air per unit of volume I sphere AS is the density of the magnetic medium in air, which we have reason to believe the same as that of the luminiferous medium. We therefore put lambda is the wavelength of the undulation in the substance. Now if delta be the wavelength for the same ray in air, and I the index of refraction of that ray in the body. Also v, the velocity of light in the substance, is related to v, the velocity of light in air, by the equation. Hence if z be the thickness of the substance through which the ray passes, the angle through which the plane of polarization will be turned will be in degrees. Or, by what we have now calculated. In this expression all the quantities are known by experiment except r, the radius of the vortices in the body, and s, the density of the luminiferous medium in air. The experiments of M. Verde supply all that is wanted except the determination of Z in absolute measure, and this would also be known for all his experiments, if the value of the galvanometer deflection for a semi-rotation of the testing bobbin in a known magnetic field, such as that due to terrestrial magnetism at Paris, were once for all determined. See a paper on Faraday's lines of force, Cambridge Philosophical Transactions, Volume X. Part 1. Page 155 of this volume. See Faraday's Researches, 3252. Rankin's Applied Mechanics, Art, 106. Rankin's Applied Mechanics, Art, 116. See Goodeve's Elements of Mechanism, page 118. Cambridge Philosophical Transactions, Volume 10 Part 1 Art, 3. On Faraday's Lines of Force, pp. 205 to 209 of this volume. The angular momentum of the system of vortices depends on their average diameter, so that if the diameter was sensible, we might expect that a magnet would behave as if it contained a revolving body within it, and that the existence of this rotation might be detected by experiments on the free rotation of a magnet. I have made experiments to investigate this question, but have not yet fully tried the apparatus. Phil. Mag. March, 1861, pp. 451 to 466 of this volume. Phil. Mag. April and May, 1861, pp. 467 to 488 of this volume. Asterisk by Professor W. Thompson. Faraday, Experimental Researches, Series 11. Asterisk see Professor Mossotti, Discussion Analytica, Memorie della Soc. Italiana, Modena, Volume 24, Part 2, page 49. Phil. Mag. April, 1861, page 471 of this volume. Asterisk see Rankin, on Elasticity, Ocamp, and Dub. Math. Journ. 1851. Phil. Mag. March, 1861, page 462 of this volume. Phil. Mag. May, 1861, page 482 of this volume. Auslegungen der König. Sächsischen Gesellschaft, Volume 3, 1857. Page 260. Comtes Rendus, Volume 29, 1849. Page 90. In Galbraithen and Horton's Manual of Astronomy, M. Fizeau's result is stated at 169,944 geographical miles of 1,000 fathoms, which gives 193,118 statute miles. The value deduced from aberration is 192,000 miles. Phil. Mag. May, 1861, page 462 of this volume. Phil. Mag. December, 1860, January and February, 1861. Krell, Journal, Volume LV, 1858, page 25. Asterisk Faraday, Experimental Researches, 951 to 954, and 2216-2220. Ibid, Series 19. Comtes Rendus, Volume XLE, page 529, Volume X Liv, page 1209. Asterisk see Nihol's Cyclopedia, Art. Magnetism, Dynamical Relations of, edition 1860, Proceedings of Royal Society, June 1856 and June 1861, and Phil. Mag. 1857. Annales de Chimie et de Physique, Sir. 3, Volume XLI, page 370, Volume XLE, page 37. Asterisk Taylor's Scientific Memories, Volume versus page 477. Asterisk Phil. Mag. April, 1861, page 472 of this volume. Phil. Mag. May, 1861, page 481 of this volume. Annales de Chimie et de Physique, Sir. 3, Volume XLI, page 370. From the London, Edinburgh, and Dublin Philosophical Magazine and Journal of Science. Volume 27, 4th Series. 24, on reciprocal figures and diagrams of forces. Reciprocal figures are such that the properties of the first relative to the second are the same as those of the second relative to the first. Thus inverse figures and polar reciprocals are instances of two different kinds of reciprocity. The kind of reciprocity which we have here to do with has reference to figures consisting of straight lines joining a system of points, and forming closed rectilinear figures, and it consists in the directions of all lines in the one figure having a constant relation to those of the lines in the other figure which correspond to them. In plane figures, corresponding lines may be either parallel, perpendicular, or at any constant angle. Lines meeting in a point in one figure form a closed polygon in the other. In figures in space, the lines in one figure are perpendicular to planes in the other, and the planes corresponding to lines which meet in a point form a closed polyhedron. The conditions of reciprocity may be considered from a purely geometrical point of view, but the chief importance arises from the fact that either of the figures being considered as a system of points acted on by forces along the lines of connection, the other figure is a diagram of forces, in which these forces are represented in plane figures by lines, and in solid figures by the areas of planes. The properties of the triangle and polygon of forces have been long known, and the diagram of forces has been used in the case of the funicular polygon, but I am not aware of any more general statement of the method of drawing diagrams of forces before Professor Rankin applied it to frames, roofs, and see, in his Applied Mechanics, page 137, and see. The polyhedron of forces, or the equilibrium of forces perpendicular and proportional to the areas of the faces of a polyhedron, has, I believe, been enunciated independently at various times, but the application to frame is given by Professor Rankin in the Philosophical Magazine, February 1864. I propose to treat the question geometrically, as reciprocal figures are subject to certain conditions besides those belonging to diagrams of forces. On reciprocal plane figures. Definition. Two plane figures are reciprocal when they consist of an equal number of lines, so that corresponding lines in the two figures are parallel, and corresponding lines which converge to a point in one figure form a closed polygon in the other. Note: if corresponding lines in the two figures, instead of being parallel are at right angles or any other angle, they may be made parallel by turning one of the figures round in its own plane. Since every polygon in one figure has three or more sides, every point in the other figure must have three or more lines converging to it, and since every line in the one figure has two and only two extremities to which lines converge, every line in the other figure must belong to two, and only two closed polygons. The simplest plane figure fulfilling these conditions is that formed by the 6 lines which join 4 points in pairs. The reciprocal figure consists of 6 lines parallel respectively to these, the points in the one figure corresponding to triangles in the other. General relation between the numbers of points, lines, and polygons in reciprocal figures. The effect of drawing a line, one of whose extremities is a point connected with the system of lines already drawn, is either to introduce one new point into the system, or to complete one new polygon, or to divide a polygon into two parts, according as it is drawn to an isolated point, or a point already connected with the system. Hence the sum of points and polygons in the system is increased by 1 for every new line. But the simplest figure consists of 4 points, 4 polygons, and 6 lines. Hence the sum of the points and polygons must always exceed the number of lines by 2. Note: this is the same relation which connects the numbers of summits, faces, and edges of polyhedra. Conditions of indeterminateness and impossibility in drawing reciprocal diagrams. Taking any line parallel to one of the lines of the figure for a base, every new point is to be determined by the intersection of two new lines. Calling S the number of points or summits, E the number of lines or edges, and F the number of polygons or faces, the assumption of the first line determines 2 points, and the remaining S2 points are determined by 2, S2, lines. Hence if every point may be determined. If E be less, the form of the figure will be in some respects indeterminate, and if E be greater, the construction of the figure will be impossible, unless certain conditions among the directions of the lines are fulfilled. These are the conditions of drawing any diagram in which the directions of the lines are arbitrarily given, but when one diagram is already drawn in which E is greater than 2s3, the directions of the lines will not be altogether arbitrary, but will be subject to E, 2s3, conditions. Now if E, S, F, be the values of E, S, and F in the reciprocal diagram. Hence if S equals F, E equals 2I2, and there will be one condition connecting the directions of the lines of the original diagram, and this condition will ensure the possibility of constructing the reciprocal diagram. If so that the construction of the reciprocal diagram will be possible, but indeterminate to the extent of S, F variables. If S less than F, the construction of the reciprocal diagram will be impossible unless S, F conditions be fulfilled in the original diagram. If any number of the points of the figure are so connected among themselves as to form an equal number of closed polygons, the conditions of constructing the reciprocal figure must be found by considering these points separately, and then examining their connection with the rest. Let us now consider a few cases of reciprocal figures in detail. The simplest case is that of the figure formed by the 6 lines connecting 4 points in a plane. If we now draw the 6 lines connecting the centers of the 4 circles which pass through 3 out of the 4 points, we shall have a reciprocal figure, the corresponding lines in the two figures being at right angles. Fig. 1. The reciprocal figure formed in this way is definite in size and position, but any figure similar to it and placed in any position is still reciprocal to the original figure. If the reciprocal figures are lettered as in Fig. 1, we shall have the relation. In figures 2 and 2, we have a pair of reciprocal figures in which the lines are more numerous, but the construction very easy. There are 7 points in each figure corresponding to 7 polygons in the other. Fig. 2. Fig. 2. The 4 points of triple concourse of lines ABC, BDE, Hill, LJK correspond to 4 triangles, ABC, BDE, Hill, LJK. The 3 points of quadruple concourse ADFH, CEGK, IFGJ correspond to 3 quadrilaterals, ADFH, CEGK, IFGJ. The 5 triangles ADB, EBC, GJK, 1JL, HIF correspond to 5 points of triple concourse, ADB, EBC, GJK, IJL, HIF. The quadrilateral DEGF corresponds to the point of quadruple concourse DEGF. The pentagon ACKLH corresponds to the meeting of the 5 lines ACHLH. In drawing the reciprocal of Fig. 2, it is best to begin with a point of triple concourse. The reciprocal triangle of this point being drawn determines 3 lines of the new figure. If the other extremities of any of the lines meeting in this point are points of triple concourse, we may in the same way determine more lines, 2 at a time. In drawing these lines, we have only to remember that those lines which in the first figure form a polygon start from one point in the reciprocal figure. In this way we may proceed as long as we can always determine all the lines except 2 of each successive polygon. The case represented in Figs. 3 and 3 is an instance of a pair of reciprocal figures fulfilling the conditions of possibility and determinateness, but presenting a slight difficulty in drawing by the foregoing rule. Each figure has here 8 points and 8 polygons, but after we have drawn the lines S, N, O, K, R, we cannot proceed with the figure simply by drawing the last 2 lines of polygons, because the next polygons to be drawn are quadrilaterals, and we have only one side of each given. The easiest way to proceed is to produce a bed till they form a quadrilateral, then to draw a subsidiary figure similar to TLMPQ, with a bed similarly situated, and then to reduce the latter figure to such a scale and position that A, B, C, D coincide in both figures. Fig. 3. Fig. 3. In figures 4 and IV, the condition that the number of polygons is equal to the number of points is not fulfilled. In Fig. 4, there are 5 points and 6 triangles. In Fig. IV, there are 6 points, 2 triangles, and 3 quadrilaterals. Hence if Fig. 4, id given, Fig. IV, is indeterminate to the extent of one variable, besides the elements of scale and position. In fact, when we have drawn ABC and indicated the directions of P, Q, R, we may fix on any point of P as one of the angles of XYZ and complete the triangle XYZ. The size of XYZ is therefore indeterminate. Conversely, if Fig. IV is given, Fig. 4 cannot be constructed unless one condition be fulfilled. That condition is that P, Q, and R meet in a point. When this is fulfilled, it follows by geometry that the points of concourse of A and X, B and Y, and C and Z lie in one straight line W, which is parallel to W in Fig. 4. The condition may also be expressed by saying that Fig. IV must be a perspective projection of a polyhedron whose quadrilateral faces are planes. The planes of these faces intersect at the concourse of P, Q, R, and those of the triangular faces intersect in the line W. Fig. IV, Fig. 4, Figs. 5, and V represent another case of the same kind. In Fig. 5, we have 6 points and 8 triangles. Fig. V is therefore capable of 2 degrees of variability, and is subject to 2 conditions. The conditions are that the 4 intersections of corresponding sides of opposite quadrilaterals in Fig. V shall lie in one straight line, parallel to the line joining the opposite points of Fig. 5, which correspond to these quadrilaterals. There are 3 such lines marked X, Y, Z, and 4 points of intersection lie on each line. Fig. V. Fig. 5. We may express this condition also by saying that Fig. V must be a perspective projection of a plane-sided polyhedron, the intersections of opposite planes being the lines X, Y, Z. In Fig. 6, let ABCD be a portion of a polygon bounded by other polygons of which the edges are PQRST, one or more of these edges meeting each angle of the polygon. In Fig. Vi, let ABCD be lines parallel to ABCD and meeting in a point, and let these be terminated by the lines PQRST parallel to PQRST, one or more of these lines completing each sector of Fig. Vi. In Fig. 6, draw Y through the intersections of AC and PQ, and in Fig. Vi, draw Y through the intersections of A, P and C, Q. Then the figures of 6 lines ABCPQY and ABCPQY will be reciprocal, and Y will be parallel to Y. Draw X parallel to X, and through the intersections of Texas and CE draw Z, and in Fig. Y, draw Z through the intersections of CX and A, then CDETX and CDETXZ will be reciprocal, and Z will be parallel to Z. Then through the intersections of A and YZ draw W, and through those of A and EZ draw W. And since ACEYZW and ACZW are reciprocal, W will be parallel to W. Fig. 6. Fig. Y. By going round the remaining sides of the polygon absidy in the same way, we should find by the intersections of lines another point, the line joining which with the intersection of A would be parallel to W, and therefore we should have 3 points in one line, namely, the intersection of Y and Z, the point determined by a similar process carried on the other part of the circumference of the polygon, and the intersection of A and E, and we should find similar conditions for every pair of sides of every polygon. Now the conditions of the figure 6 being a perspective projection of a plane-sided polyhedron are exactly the same. For A being the intersection of the faces AP and AB, and C that of BC and QC, the intersection AC will be a point in the intersection of the faces AP and CQ. Similarly, the intersection PQ will be another point in it, so that Y is the line of intersection of the faces AP and CQ. In the same way Z is the intersection of ET and CQ, so that the intersection of Y and Z is a point in the intersection of AP and ET. Another such point can be determined by going round the remaining sides of the polygon, and these 2 points, together with the intersections of the lines A, must all be in one straight line, namely, the intersection of the faces AP and ET. Hence the conditions of the possibility of reciprocity in plane figures are the same as those of each figure being the perspective projection of a plane-sided polyhedron. When the number of points is in every part of the figure equal to or less than the number of polygons, this condition is fulfilled of itself. When the number of points exceeds the number of polygons, there will be an impossible case, unless certain conditions are fulfilled so that certain sets of intersections lie in straight lines. Application to statics. The doctrine of reciprocal figures may be treated in a purely geometrical manner, but it may be much more clearly understood by considering it as a method of calculating the forces among a system of points in equilibrium. For, if forces represented in magnitude by the lines of a figure be made to act between the extremities of the corresponding lines of the reciprocal figure, then the points of the reciprocal figure will all be in equilibrium under the action of these forces. For the forces which meet in any point are parallel and proportional to the sides of a polygon in the other figure. If the points between which the forces are to act are known, the problem of determining the relations among the magnitudes of the forces so as to produce equilibrium will be indeterminate, determinate, or impossible, according as the construction of the reciprocal figure is so. Reciprocal figures are mechanically reciprocal. That is, either may be taken as representing a system of points, and the other as representing the magnitudes of the forces acting between them. In figures like 1, 2 and 2, 3 and 3, in which the equation is true, the forces are determinate in their ratios, so that one being given, the rest may be found. When E greater than 2's 2, as in figs. 4 and 5, the forces are indeterminate, so that more than one must be known to determine the rest, or else certain relations among them must be given, such as those arising from the elasticity of the parts of a frame. When E less than 2's 2, the determination of the forces is impossible except under certain conditions. Unless these be fulfilled, as in figs. IV and V, no forces along the lines of the figure can keep its points in equilibrium, and the figure, considered as a frame, may be said to be loose. When the conditions are fulfilled, the pieces of the frame can support forces, but in such a way that a small disfigurement of the frame may produce infinitely great forces in some of the pieces, or may throw the frame into a loose condition at once. The conditions, however, of the possibility of determining the ratios of the forces in a frame are not coextensive with those of finding a figure perfectly reciprocal to the frame. The condition of determinate forces is the condition of reciprocal figures is that every line belongs to 2 polygons only, and in Fig. 7, we have 6 points connected by 10 lines in such a way that the forces are all determinate, but since the line L is a side of 3 triangles, we cannot draw a reciprocal figure, for we should have to draw a straight line L with 3 ends. If we attempt to draw the reciprocal figure as in Fig. 7, we shall find that, in order to represent the reciprocals of all the lines of Fig. 7, and fix their relations, we must repeat two of them, as H and E by H, and E, so as to form a parallelogram. Fig. 7 is then a complete representation of the relations of the force which would produce equilibrium in Fig. 7, but it is redundant by the repetition of H and E, and the two figures are not reciprocal. Fig. 7. Fig. 7. On reciprocal figures in three dimensions. Definition. Figures in three dimensions are reciprocal when they can be so placed that every line in the one figure is perpendicular to a plane face of the other, and every point of concourse of lines in the one figure is represented by a closed polyhedron with plane faces. The simplest case is that of 5 points in space with their 10 connecting lines, forming 10 triangular faces enclosing 5 tetrahedrons. By joining the 5 points which are the centers of the spheres circumscribing these 5 tetrahedrons, we have a reciprocal figure of the kind described by Professor Rankin in the Philosophical Magazine, February 1864, and forces proportional to the areas of the triangles of one figure, if applied along the corresponding lines of connection of the other figure, will keep its points in equilibrium. In order to have perfect reciprocity between two figures, each figure must be made up of a number of closed polyhedra having plane faces of separation, and such that each face belongs to two and only two polyhedra, corresponding to the extremities of the reciprocal line in the other figure. Every line in the figure is the intersection of 3 or more plane faces, because the plane face in the reciprocal figure is bounded by 3 or more straight lines. Let S be the number of points or summits, E the number of lines or edges, F the number of faces, and C the number of polyhedra or cells. Then if about one of the summits in which polyhedra meet, and sigma edges and eta faces, we describe a polyhedral cell, it will have 5 faces and sigma summits and eta edges, and we shall have S, the number of summits, will be decreased by 1 and increased by sigma. C, the number of cells, will be increased by 1. F, the number of faces, will be increased by phi. E, the number of edges, will be increased by eta. So that E plus C, S plus F, will be increased by eta plus 1, sigma plus phi 1, which is 0, or this quantity is constant. Now in the figure of 5 points already discussed, E equals 10, C equals 5, S equals 5, F equals 10. So that generally, in figures made up of seals in the way described, the condition of a reciprocal figure being indeterminate, determinate, or impossible except in particular cases, is. This condition is sufficient to determine the possibility of finding a system of forces along the edges which will keep the summits in equilibrium, but it is manifest that the mechanical problem may be solved, though the reciprocal figure cannot be constructed owing to the condition of all the sides of a face lying in a plane not being fulfilled, or owing to a face belonging to more than 2 cells. Hence the mechanical interest of reciprocal figures in space rapidly diminishes with their complexity. Diagrams of forces in which the forces are represented by lines may be always constructed in space as well as in a plane, but in general some of the lines must be repeated. Thus in the figure of 5 points, each point is the meeting place of 4 lines. The forces in these lines may be represented by 5 gauche quadrilaterals, that is, quadrilaterals not in one plane, and one of these being chosen, the other 4 may be applied to its sides and to each other so as to form 5 sides of a gauche hexahedron. The 6th side, that opposite the original quadrilateral, will be a parallelogram, the opposite sides of which are repetitions of the same line. We have thus a complete but redundant diagram of forces consisting of 8 points joined by 12 lines, 2 pairs of the lines being repetitions. This is a more convenient though less elegant construction of a diagram of forces, and it never becomes geometrically impossible as long as the problem is mechanically possible, however complicated the original figure may be. From the Royal Society Transactions, Volume CLV 25, A Dynamical Theory of the Electromagnetic Field. Received October 27, read December 8, 1864. Part 1. Introductory. 1. The most obvious mechanical phenomenon in electrical and magnetical experiments is the mutual action by which bodies in certain states set each other in motion while still at a sensible distance from each other. The first step, therefore, in reducing these phenomena into scientific form, is to ascertain the magnitude and direction of the force acting between the bodies, and when it is found that this force depends in a certain way upon the relative position of the bodies and on their electric or magnetic condition, It seems at first sight natural to explain the facts by assuming the existence of something either at rest or in motion in each body, constituting its electric or magnetic state, and capable of acting at a distance according to mathematical laws. In this way, mathematical theories of statical electricity, of magnetism, of the mechanical action between conductors carrying currents, and of the induction of currents have been formed. In these theories, the force acting between the two bodies is treated with reference only to the condition of the bodies and their relative position, and without any express consideration of the surrounding medium. These theories assume, more or less explicitly, the existence of substances the particles of which have the property of acting on one another at a distance by attraction or repulsion. The most complete development of a theory of this kind is that of M. W. Weber**, who has made the same theory include electrostatic and electromagnetic phenomena. In doing so, however, he has found it necessary to assume that the force between two electric particles depends on their relative velocity, as well as on their distance. This theory, as developed by M. W. Weber and C. Newman, is exceedingly ingenious and wonderfully comprehensive in its application to the phenomena of statical electricity, electromagnetic attractions, induction of currents and diamagnetic phenomena, and it comes to us with the more authority, as it has served to guide the speculations of one who has made so great an advance in the practical part of electric science, both by introducing a consistent system of units in electrical measurement, and by actually determining electrical quantities with an accuracy hitherto unknown. 2. The mechanical difficulties, however, which are involved in the assumption of particles acting at a distance with forces which depend on their velocities are such as to prevent me from considering this theory as an ultimate one, though it may have been, and may yet be useful in leading to the coordination of phenomena. I have therefore preferred to seek an explanation of the fact in another direction, by supposing them to be produced by actions which go on in the surrounding medium as well as in the excited bodies, and endeavoring to explain the action between distant bodies without assuming the existence of forces capable of acting directly at sensible distances. 3. The theory I propose may therefore be called a theory of the electromagnetic field, because it has to do with the space in the neighborhood of the electric or magnetic bodies, and it may be called a dynamical theory, because it assumes that in that space there is matter in motion, by which the observed electromagnetic phenomena are produced. 4. The electromagnetic field is that part of space which contains and surrounds bodies in electric or magnetic conditions. It may be filled with any kind of matter, or we may endeavor to render it empty of all gross matter, as in the ease of Geissler's tubes and other so-called vacua. There is always, however, enough of matter left to receive and transmit the undulations of light and heat, and it is because the transmission of these radiations is not greatly altered when transparent bodies of measurable density are substituted for the so-called vacuum, that we are obliged to admit that the undulations are those of an ethereal substance, and not of the gross matter, the presence of which merely modifies in some way the motion of the ether. We have therefore some reason to believe, from the phenomena of light and heat, that there is an ethereal medium filling space and permeating bodies, capable of being set in motion and of transmitting that motion from one part to another, and of communicating that motion to gross matter so as to heat it and affect it in various ways. 5. Now the energy communicated to the body in heating it must have formerly existed in the moving medium, for the undulations had left the source of heat some time before they reached the body, and during that time the energy must have been half in the form of motion of the medium and half in the form of elastic resilience. From these considerations Professor W. Thomson has argued that the medium must have a density capable of comparison with that of gross matter, and has even assigned an inferior limit to that density. 6. We may therefore receive, as a datum derived from a branch of science independent of that with which we have to deal, the existence of a pervading medium, of small but real density, capable of being set in motion, and of transmitting motion from one part to another with great, but not infinite, velocity. Hence the parts of this medium must be so connected that the motion of one part depends in some way on the motion of the rest, and at the same time these connections must be capable of a certain kind of elastic yielding, since the communication of motion is not instantaneous, but occupies time. The medium is therefore capable of receiving and storing up two kinds of energy, namely, the actual energy depending on the motions of its parts, and potential energy, consisting of the work which the medium will do in recovering from displacement in virtue of its elasticity. The propagation of undulations consists in the continual transformation of one of these forms of energy into the other alternately, and at any instant the amount of energy in the whole medium is equally divided, so that half is energy of motion, and half is elastic resilience. 7. A medium having such a constitution may be capable of other kinds of motion and displacement than those which produce the phenomena of light and heat, and some of these may be of such a kind that they may be evidenced to our senses by the phenomena they produce. 8. Now we know that the luminiferous medium is in certain cases acted on by magnetism, for Faraday discovered that when a plane polarized ray traverses a transparent diamagnetic medium in the direction of the lines of magnetic force produced by magnets or currents in the neighborhood, the plane of polarization is caused to rotate. This rotation is always in the direction in which positive electricity must be carried round the diamagnetic body in order to produce the actual magnetization of the field. M. Verde has since discovered that if a paramagnetic body, such as solution of perchloride of iron in ether, be substituted for the diamagnetic body, the rotation is in the opposite direction. Now Professor W. Thomson has pointed out that no distribution of forces acting between the parts of a medium whose only motion is that of the luminous vibrations, is sufficient to account for the phenomena, but that we must admit the existence of a motion in the medium depending on the magnetization, in addition to the vibratory motion which constitutes light. It is true that the rotation by magnetism of the plane of polarization has been observed only in media of considerable density, but the properties of the magnetic field are not so much altered by the substitution of one medium for another, or for a vacuum, as to allow us to suppose that the dense medium does anything more than merely modify the motion of the ether. We have therefore warrantable grounds for inquiring whether there may not be a motion of the ethereal medium going on wherever magnetic effects are observed, and we have some reason to suppose that this motion is one of rotation, having the direction of the magnetic force as its axis. 9. We may now consider another phenomenon observed in the electromagnetic field. When a body is moved across the lines of magnetic force, it experiences what is called an electromotive force. The two extremities of the body tend to become oppositely electrified, and an electric current tends to flow through the body. When the electromotive force is sufficiently powerful, and is made to act on certain compound bodies, it decomposes them, and causes one of their components to pass towards one extremity of the body, and the other in the opposite direction. Here we have evidence of a force causing an electric current in spite of resistance, electrifying the extremities of a body in opposite ways, a condition which is sustained only by the action of the electromotive force, and which, as soon as that force is removed, tends, with an equal and opposite force, to produce a countercurrent through the body and to restore the original electrical state of the body, and finally, if strong enough, tearing to pieces chemical compounds and carrying their components in opposite directions, while their natural tendency is to combine, and to combine with a force which can generate an electromotive force in the reverse direction. This, then, is a force acting on a body caused by its motion through the electromagnetic field, or by changes occurring in that field itself, and the effect of the force is either to produce a current and heat the body, or to decompose the body, or, when it can do neither, to put the body in a state of electric polarization, a state of constraint in which opposite extremities are oppositely electrified, and from which the body tends to relieve itself as soon as the disturbing force is removed. 10. According to the theory which I propose to explain, this electromotive force is the force called into play during the communication of motion from one part of the medium to another, and it is by means of this force that the motion of one part causes motion in another part. When electromotive force acts on a conducting circuit, it produces a current, which, as it meets with resistance, occasions a continual transformation of electrical energy into heat, which is incapable of being restored again to the form of electrical energy by any reversal of the process. 11. But when electromotive force acts on a dielectric, it produces a state of polarization of its parts similar in distribution to the polarity of the parts of a mass of iron under the influence of a magnet, and like the magnetic polarization, capable of being described as a state in which every particle has its opposite poles and opposite conditions. In a dielectric under the action of electromotive force, we may conceive that the electricity in each molecule is so displaced that one side is rendered positively and the other negatively electrical, but that the electricity remains entirely connected with the molecule, and does not pass from one molecule to another. The effect of this action on the whole dielectric mass is to produce a general displacement of electricity in a certain direction. This displacement does not amount to a current, because when it has attained to a certain value it remains constant, but it is the commencement of a current, and its variations constitute currents in the positive or the negative direction according as the displacement is increasing or decreasing. In the interior of the dielectric there is no indication of electrification, because the electrification of the surface of any molecule is neutralized by the opposite electrification of the surface of the molecules in contact with it. But at the bounding surface of the dielectric, where the electrification is not neutralized, we find the phenomena which indicate positive or negative electrification. The relation between the electromotive force and the amount of electric displacement it produces depends on the nature of the dielectric, the same electromotive force producing generally a greater electric displacement in solid dielectrics, such as glass or sulfur, than in air. 12. Here, then, we perceive another effect of electromotive force, namely, electric displacement, which according to our theory is a kind of elastic yielding to the action of the force, similar to that which takes place in structures and machines owing to the want of perfect rigidity of the connections. 13. The practical investigation of the inductive capacity of dielectrics is rendered difficult on account of two disturbing phenomena. The first is the conductivity of the dielectric, which, though in many cases exceedingly small, is not altogether insensible. The second is the phenomenon called electric absorption *, in virtue of which, when the dielectric is exposed to electromotive force, the electric displacement gradually increases, and when the electromotive force is removed, the dielectric does not instantly return to its primitive state, but only discharges a portion of its electrification, and when left to itself gradually acquires electrification on its surface, as the interior gradually becomes depolarized. Almost all solid dielectrics exhibit this phenomenon, which gives rise to the residual charge in the Leyden jar, and to several phenomena of electric cables described by Mr. F. Jenkin. 14. We have here two other kinds of yielding besides the yielding of the perfect dielectric, which we have compared to a perfectly elastic body. The yielding due to conductivity may be compared to that of a viscous fluid, that is to say, a fluid having great internal friction, or a soft solid on which the smallest force produces a permanent alteration of figure increasing with the time during which the force acts. The yielding due to electric absorption may be compared to that of a cellular elastic body containing a thick fluid in its cavities. Such a body, when subjected to pressure, is compressed by degrees on account of the gradual yielding of the thick fluid, and when the pressure is removed it does not at once recover its figure, because the elasticity of the substance of the body has gradually to overcome the tenacity of the fluid before it can regain complete equilibrium. Several solid bodies in which no such structure as we have supposed can be found, seem to possess a mechanical property of this kind, and it seems probable that the same substances, if dielectrics, may possess the analogous electrical property, and if magnetic, may have corresponding properties relating to the acquisition, retention, and loss of magnetic polarity. 15. It appears therefore that certain phenomena in electricity and magnetism led to the same conclusion as those of optics, namely, that there is an ethereal medium pervading all bodies, and modified only in degree by their presence, that the parts of this medium are capable of being set in motion by electric currents and magnets, that this motion is communicated from one part of the medium to another by forces arising from the connections of those parts, that under the action of these forces there is a certain yielding depending on the elasticity of these connections, and that therefore energy in two different forms may exist in the medium, the one form being the actual energy of motion of its parts, and the other being the potential energy stored up in the connections, in virtue of their elasticity. 16. Thus, then, we are led to the conception of a complicated mechanism capable of a vast variety of motion, but at the same time so connected that the motion of one part depends, according to definite relations, on the motion of other parts, these motions being communicated by forces arising from the relative displacement of the connected parts, in virtue of their elasticity. Such a mechanism must be subject to the general laws of dynamics, and we ought to be able to work out all the consequences of its motion, provided we know the form of the relation between the motions of the parts. 17. We know that when an electric current is established in a conducting circuit, the neighboring part of the field is characterized by certain magnetic properties, and that if two circuits are in the field, the magnetic properties of the field due to the two currents are combined. Thus each part of the field is in connection with both currents, and the two currents are put in connection with each other in virtue of their connection with the magnetization of the field. The first result of this connection that I propose to examine is the induction of one current by another, and by the motion of conductors in the field. The second result, which is deduced from this, is the mechanical action between conductors carrying currents. The phenomenon of the induction of currents has been deduced from their mechanical action by Helmholtz and Thomson. I have followed the reverse order, and deduced the mechanical action from the laws of induction. I have then described experimental methods of determining the quantities L, M, N, on which these phenomena depend. 18. I then apply the phenomena of induction and attraction of currents to the exploration of the electromagnetic field, and the laying down systems of lines of magnetic force which indicate its magnetic properties. By exploring the same field with a magnet, I show the distribution of its equipotential magnetic surfaces, cutting the lines of force at right angles. In order to bring these results within the power of symbolical calculation, I then express them in the form of the general equations of the electromagnetic field. These equations express a. The relation between electric displacement, true conduction, and the total current, compounded of both. b. The relation between the lines of magnetic force and the inductive coefficients of a circuit, as already deduced from the laws of induction. c. The relation between the strength of a current and its magnetic effects, according to the electromagnetic system of measurement. d. The value of the electromotive force in a body, as arising from the motion of the body in the field, the alteration of the field itself, and the variation of electric potential from one part of the field to another. e. The relation between electric displacement and the electromotive force which produces it. f. The relation between an electric current and the electromotive force which produces it. g. The relation between the amount of free electricity at any point and the electric displacements in the neighborhood. h. The relation between the increase or diminution of free electricity and the electric currents in the neighborhood. There are 20 of these equations in all, involving 20 variable quantities. 19. I then express in terms of these quantities the intrinsic energy of the electromagnetic field as depending partly on its magnetic and partly on its electric polarization at every point. From this I determine the mechanical force acting, first, on a movable conductor carrying an electric current, 2 Ndly, on a magnetic pole, 3 Rdly, on an electrified body. The last result, namely, the mechanical force acting on an electrified body, gives rise to an independent method of electrical measurement founded on its electrostatic effects. The relation between the units employed in the two methods is shown to depend on what I have called the electric elasticity of the medium, and to be a velocity, which has been experimentally determined by M.M. Weber and Kohlrausch. I then show how to calculate the electrostatic capacity of a condenser, and the specific inductive capacity of a dielectric. The case of a condenser composed of parallel layers of substances of different electric resistances and inductive capacities is next examined, and it is shown that the phenomenon called electric absorption will generally occur, that is, the condenser, when suddenly discharged, will after a short time show signs of a residual charge. 20. The general equations are next applied to the case of a magnetic disturbance propagated through a non-conducting field, and it is shown that the only disturbances which can be so propagated are those which are transverse to the direction of propagation, and that the velocity of propagation is the velocity v, found from experiments such as those of Weber, which expresses the number of electrostatic units of electricity which are contained in one electromagnetic unit. This velocity is so nearly that of light, that it seems we have strong reason to conclude that light itself, including radiant heat, and other radiations if any, is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field according to electromagnetic laws. If so, the agreement between the elasticity of the medium as calculated from the rapid alternations of luminous vibrations, and as found by the slow processes of electrical experiments, shows how perfect and regular the elastic properties of the medium must be when not encumbered with any matter denser than air. If the same character of the elasticity is retained in dense transparent bodies, it appears that the square of the index of refraction is equal to the product of the specific dielectric capacity and the specific magnetic capacity. Conducting media are shown to absorb such radiations rapidly, and therefore to be generally opaque. The conception of the propagation of transverse magnetic disturbances to the exclusion of normal ones is distinctly set forth by Professor Faraday * in his Thoughts on Ray Vibrations. The electromagnetic theory of light, as proposed by him, is the same in substance as that which I have begun to develop in this paper, except that in 1846 there were no data to calculate the velocity of propagation. 21. The general equations are then applied to the calculation of the coefficients of mutual induction of two circular currents and the coefficient of self-induction in a coil. The want of uniformity of the current in the different parts of the section of a wire at the commencement of the current is investigated, I believe for the first time, and the consequent correction of the coefficient of self-induction is found. These results are applied to the calculation of the self-induction of the coil used in the experiments of the Committee of the British Association on Standards of Electric Resistance, and the value compared with that deduced from the experiments. Part 2. On electromagnetic induction, electromagnetic momentum of a current. 22. We may begin by considering the state of the field in the neighborhood of an electric current. We know that magnetic forces are excited in the field, their direction and magnitude depending according to known laws upon the form of the conductor carrying the current. When the strength of the current is increased, all the magnetic effects are increased in the same proportion. Now, if the magnetic state of the field depends on motions of the medium, a certain force must be exerted in order to increase or diminish these motions, and when the motions are excited they continue, so that the effect of the connection between the current and the electromagnetic field surrounding it is to endow the current with a kind of momentum, just as the connection between the driving point of a machine and a flywheel endows the driving point with an additional momentum, which may be called the momentum of the flywheel reduced to the driving point. The unbalanced force acting on the driving point increases this momentum, and is measured by the rate of its increase. In the case of electric currents, the resistance to sudden increase or diminution of strength produces effects exactly like those of momentum, but the amount of this momentum depends on the shape of the conductor and the relative position of its different parts. Mutual action of two currents. 23. If there are two electric currents in the field, the magnetic force at any point is that compounded of the forces due to each current separately, and since the two currents are in connection with every point of the field, they will be in connection with each other, so that any increase or diminution of the one will produce a force acting with or contrary to the other. Dynamical illustration of reduced momentum. 24. As a dynamical illustration, let us suppose a body C so connected with two independent driving points A and B that its velocity is p times that of A together with q times that of B. Let u be the velocity of A, v that of B, and w that of C, and let delta x, delta y, delta z be their simultaneous displacements, then by the general equation of dynamics *, where x and y are the forces acting at A and B. But, and substituting, and remembering that delta x and delta y are independent, we may call Cp2u plus Cpqv the momentum of C referred to A, and Cpqu plus Cq2v its momentum referred to B. Then we may say that the effect of the force x is to increase the momentum of C referred to A, and that of y to increase its momentum referred to B. If there are many bodies connected with A and B in a similar way but with different values of P and Q, we may treat the question in the same way by assuming where the summation is extended to all the bodies with the proper values of C, P, and Q. Then the momentum of the system referred to A is, and referred to B, and we shall have, where x and y are the external forces acting on A and B. 25. To make the illustration more complete we have only to suppose that the motion of A is resisted by a force proportional to its velocity, which we may call ρ, and that of B by a similar force, which we may call SV, R and S being coefficients of resistance. Then if she and eta are the forces on A and B. If the velocity of A be increased at the rate, then in order to prevent B from moving a force, must be applied to it. This effect on B, due to an increase of the velocity of A, corresponds to the electromotive force on one circuit arising from an increase in the strength of a neighboring circuit. This dynamical illustration is to be considered merely as assisting the reader to understand what is meant in mechanics by reduced momentum. The facts of the induction of currents as depending on the variations of the quantity called electromagnetic momentum, or electrotonic state, rest on the experiments of Faraday *, Felice, and C. Coefficients of induction for two circuits. 26. In the electromagnetic field the values of L, M, N depend on the distribution of the magnetic effects due to the two circuits, and this distribution depends only on the form and relative position of the circuits. Hence L, M, N are quantities depending on the form and relative position of the circuits, and are subject to variation with the motion of the conductors. It will be presently seen that L, M, N are geometrical quantities of the nature of lines, that is, of one dimension in space. L depends on the form of the first conductor, which we shall call A, N on that of the second, which we shall call B, and M on the relative position of A and B. 27. Let she be the electromotive force acting on A, x the strength of the current, and R the resistance, then Rx will be the resisting force. In steady currents the electromotive force just balances the resisting force, but in variable currents the resultant force Rx is expended in increasing the electromagnetic momentum, using the word momentum merely to express that which is generated by a force acting during a time, that is, a velocity existing in a body. In the case of electric currents, the force in action is not ordinary mechanical force, at least we are not as yet able to measure it as common force, but we call it electromotive force, and the body moved is not merely the electricity in the conductor, but something outside the conductor, and capable of being affected by other conductors in the neighborhood carrying currents. In this it resembles rather the reduced momentum of a driving point of a machine is influenced by its mechanical connections, than that of a simple moving body like a cannonball, or water in a tube. Electromagnetic relations of two conducting circuits. 28. In the case of two conducting circuits, A and B, we shall assume that the electromagnetic momentum belonging to A is, and that belonging to B, where L, M, N correspond to the same quantities in the dynamical illustration, except that they are supposed to be capable of variation when the conductors A or B are moved. Then the equation of the current X inner will be, and that of Y in B, where She and Eta are the electromotive forces, X and Y the currents, and R and S the resistances in A and B respectively. Induction of one current by another. 29. Case first. Let there be no electromotive force on except that which arises from the action of A, and let the current of it increase from 0 to the value X, then whence, that is, a quantity of electricity Y, being the total induced current, will flow through B when X rises from 0 to X. This is induction by variation of the current in the primary conductor. When M is positive, the induced current due to increase of the primary current is negative. Induction by motion of conductor. 30. Case second. Let X remain constant, and let M change from M to M, then. So that if M is increased, which it will be by the primary and secondary circuits approaching each other, there will be a negative induced current, the total quantity of electricity passed through B being Y. This is induction by the relative motion of the primary and secondary conductors. Equation of work and energy. 31. To form the equation between work done and energy produced, multiply 1 by X and 2 by Y, and add. Here She X is the work done in unit of time by the electromotive force She acting on the current X and maintaining it, and Eta Y is the work done by the electromotive force Eta. Hence the left-hand side of the equation represents the work done by the electromotive forces in unit of time. Heat produced by the current. 32. On the other side of the equation we have, first, which represents the work done in overcoming the resistance of the circuits in unit of time. This is converted into heat. The remaining terms represent work not converted into heat. They may be written. Intrinsic energy of the currents. 33. If L, M, N are constant, the whole work of the electromotive forces which is not spent against resistance will be devoted to the development of the currents. The whole intrinsic energy of the currents is therefore. This energy exists in a form imperceptible to our senses, probably as actual motion, the seat of this motion being not merely the conducting circuits, but the space surrounding them. Mechanical action between conductors. 34. The remaining terms represent the work done in unit of time arising from the variations of L, M, and N, or, what is the same thing, alterations in the form and position of the conducting circuits A and B. Now if work is done when a body is moved, it must arise from ordinary mechanical force acting on the body while it is moved. Hence this part of the expression shows that there is a mechanical force urging every part of the conductors themselves in that direction in which L, M, and N will be most increased. The existence of the electromagnetic force between conductors carrying currents is therefore a direct consequence of the joint and independent action of each current on the electromagnetic field. If A and B are allowed to approach a distance ds, so as to increase M from M to M, while the currents are X and Y then the work done will be. And the force in the direction of ds will be. And this will be an attraction if X and Y are of the same sign, and if M is increased as A and B approach. It appears, therefore, that if we admit that the unresisted part of electromotive force goes on as long as it acts, generating a self-persistent state of the current, which we may call, from mechanical analogy, its electromagnetic momentum, and that this momentum depends on circumstances external to the conductor, then both induction of currents and electromagnetic attractions may be proved by mechanical reasoning. What I have called electromagnetic momentum is the same quantity which is called by Faraday the electrotonic state of the circuit, every change of which involves the action of an electromotive force, just as change of momentum involves the action of mechanical force. If, therefore, the phenomena described by Faraday in the 9th series of his experimental researches were the only known facts about electric currents, the laws of Ampere relating to the attraction of conductors carrying currents, as well as those of Faraday about the mutual induction of currents, might be deduced by mechanical reasoning. In order to bring these results within the range of experimental verification, I shall next investigate the case of a single current, of two currents, and of the 6 currents in the electric balance, so as to enable the experimenter to determine the values of L, M, N. Case of a single circuit. 35. The equation of the current X in a circuit whose resistance is R, and whose coefficient of self-induction is L, acted on by an external electromotive force Xi, is. When Xi is constant, the solution is of the form, where A is the value of the current at the commencement, and B is its final value. The total quantity of electricity which passes in time t, where t is great, is. The value of the integral of x2 with respect to the time is. The actual current changes gradually from the initial value A to the final value B, but the values of the integrals of x and x2 are the same as if a steady current of intensity, A plus B, were to flow for a time, and were then succeeded by the steady current B. The time is generally so minute a fraction of a second, that the effects on the galvanometer and dynamometer may be calculated as if the impulse were instantaneous. If the circuit consists of a battery and a coil, then, when the circuit is first completed, the effects are the same as if the current had only half its final strength during the time. This diminution of the current, due to induction, is sometimes called the counter current. 36. If an additional resistance R is suddenly thrown into the circuit, as by breaking contact, so as to force the current to pass through a thin wire of resistance R, then the original current is, and the final current is. The current of induction is then and continues for a time. This current is greater than that which the battery can maintain in the two wires R, and may be sufficient to ignite the thin wire R. When contact is broken by separating the wires in air, this additional resistance is given by the interposed air, and since the electromotive force across the new resistance is very great, a spark will be forced across. If the electromotive force is of the form E sin pt, as in the case of a coil revolving in the magnetic field, then where ρ2 equals R2 plus L2 P2, and tan case of TiVo circuits. 37. Let R be the primary circuit and S the secondary circuit, then we have a case similar to that of the induction coil. The equations of currents are those marked A and B, and we may here assume L, M, N as constant because there is no motion of the conductors. The equations then become. To find the total quantity of electricity which passes, we have only to integrate these equations with respect to t. Then if x0, y0 be the strengths of the currents at time 0, and x1, y1 at time t, and if x, y be the quantities of electricity passed through each circuit during time t. When the circuit R is completed, then the total currents up to time t, when t is great, are found by making. Then, the value of the total counter current in R is therefore independent of the secondary circuit, and the induction current in the secondary circuit depends only on M, the coefficient of induction between the coils, S the resistance of the secondary coil, and X1 the final strength of the current in R. When the electromotive force Xi ceases to act, there is an extra current in the primary circuit, and a positive induced current in the secondary circuit, whose values are equal and opposite to those produced on making contact. 38. All questions relating to the total quantity of transient currents, as measured by the impulse given to the magnet of the galvanometer, may be solved in this way without the necessity of a complete solution of the equations. The heating effect of the current, and the impulse it gives to the suspended coil of Weber's dynamometer, depend on the square of the current at every instant during the short time it lasts. Hence we must obtain the solution of the equations, and from the solution we may find the effects both on the galvanometer and dynamometer, and we may then make use of the method of Weber for estimating the intensity and duration of a current uniform while it lasts, which would produce the same effects. 39. Let N1, N2 be the roots of the equation. And let the primary coil be acted on by a constant electromotive force Rc, so that C is the constant current it could maintain, then the complete solution of the equations for making contact is. From these we obtain for calculating the impulse on the dynamometer. The effects of the current in the secondary coil on the galvanometer and dynamometer are the same as those of a uniform current. For a time, 40, the equation between work and energy may be easily verified. The work done by the electromotive force is work done in overcoming resistance and producing heat. Energy remaining in the system. 41. If the circuit R is suddenly and completely interrupted while carrying a current C, then the equation of the current in the secondary coil would be: this current begins with a value and gradually disappears. The total quantity of electricity is, and the value of the effects on the galvanometer and dynamometer are equal to those of a uniform current for a time. The heating effect is therefore greater than that of the current on making contact. 42. If an electromotive force of the form Xi equals E cos point acts on the circuit R, then, if the circuit S is removed, the value of X will be where, and. The effect of the presence of the circuit S in the neighborhood is to alter the value of A and A, to that which they would be if R became and L became. Hence the effect of the presence of the circuit S is to increase the apparent resistance and diminish the apparent self-induction of the circuit R on the determination of coefficients of induction by the electric balance. 43. The electric balance consists of 6 conductors joining 4 points, A, C, D, E, 2 and 2. One pair, AC, of these points is connected through the battery B. The opposite pair, D, is connected through the galvanometer G. Then if the resistances of the 4 remaining conductors are represented by P, Q, R, S, and the currents in them by X, Z, Y, and Y plus Z, the current through G will be 2. Let the potentials at the 4 points be A, C, D, E, then the conditions of steady currents may be found from the equations. Solving these equations for Z, we find: in this expression F is the electromotive force of the battery, Z the current through the galvanometer when it has become steady. P, Q, R, S the resistances in the 4 arms. B that of the battery and electrodes, and G that of the galvanometer. 44. If PS equals QR, then Z equals 0, and there will be no steady current, but a transient current through the galvanometer may be produced on making or breaking circuit on account of induction, and the indications of the galvanometer may be used to determine the coefficients of induction, provided we understand the actions which take place. We shall suppose PS equals QR, so that the current Z vanishes when sufficient time is allowed, and let the induction coefficients between P, Q, R, S be given by the following table, the coefficient of induction of P on itself being P, between P and Q, H, and so on. Let G be the coefficient of induction of the galvanometer on itself, and let it be out of the reach of the inductive influence of P, Q, R, S, as it must be in order to avoid direct action of P, Q, R, S on the needle. Let X, Y, Z be the integrals of X, Y, Z with respect to T. At making contact X, Y, Z are 0. After a time Z disappears, and X and Y reach constant values. The equations for each conductor will therefore be. Solving these equations for Z, we find, 45. Now let the deflection of the galvanometer by the instantaneous current whose intensity is Z be alpha. Let the permanent deflection produced by making the ratio of PS to QR, rho instead of unity, be theta. Also let the time of vibration of the galvanometer needle from rest to rest be T. Then calling the quantity, we find, in determining tau by experiment, it is best to make the alteration of resistance in one of the arms by means of the arrangement described by Mr. Jenkin in the report of the British Association for 1863, by which any value of P from 1 to 101 can be accurately measured. We observe, alpha, the greatest deflection due to the impulse of induction when the galvanometer is in circuit, when the connections are made, and when the resistances are so adjusted as to give no permanent current. We then observe, beta, the greatest deflection produced by the permanent current when the resistance of one of the arms is increased in the ratio of 1 to rho, the galvanometer not being in circuit till a little while after the connection is made with the battery. In order to eliminate the effects of resistance of the air, it is best to vary rho till beta equals 2 alpha nearly, then. If all the arms of the balance except P consist of resistance coils of very line wire of no great length and doubled before being coiled, the induction coefficients belonging to these coils will be insensible, and tau will be reduced to. The electric balance therefore affords the means of measuring the self-induction of any circuit whose resistance is known. 46. It may also be used to determine the coefficient of induction between two circuits, as for instance, that between P and S which we have called M, but it would be more convenient to measure this by directly measuring the current, as in 37, without using the balance. We may also ascertain the equality of by there being no current of induction, and thus, when we know the value of P, we may determine that of Q by a more perfect method than the comparison of deflections. Exploration of the electromagnetic field. 47. Let us now suppose the primary circuit A to be of invariable form, and let us explore the electromagnetic field by means of the secondary circuit B, which we shall suppose to be variable in form and position. We may begin by supposing B to consist of a short straight conductor with its extremities sliding on two parallel conducting rails, which are put in connection at some distance from the sliding piece. Then, if sliding the movable conductor in a given direction increases the value of M, a negative electromotive force will act in the circuit B, tending to produce a negative current in B during the motion of the sliding piece. If a current be kept up in the circuit B, then the sliding piece will itself tend to move in that direction, which causes M to increase. At every point of the field there will always be a certain direction such that a conductor moved in that direction does not experience any electromotive force in whatever direction its extremities are turned. A conductor carrying a current will experience no mechanical force urging it in that direction or the opposite. This direction is called the direction of the line of magnetic force through that point. Motion of a conductor across such a line produces electromotive force in a direction perpendicular to the line and to the direction of motion, and the conductor carrying a current is urged in a direction perpendicular to the line and to the direction of the current. 48. We may next suppose B to consist of a very small plane circuit capable of being placed in any position and of having its plane turned in any direction. The value of M will be greatest when the plane of the circuit is perpendicular to the line of magnetic force. Hence if a current is maintained in B it will tend to set itself in this position, and will of itself indicate, like a magnet, the direction of the magnetic force. On lines of magnetic force. 49. Let any surface be drawn, cutting the lines of magnetic force, and on this surface let any system of lines be drawn at small intervals, so as to lie side by side without cutting each other. Next, let any line be drawn on the surface cutting all these lines, and let a second line be drawn near it, its distance from the first being such that the value of M for each of the small spaces enclosed between these two lines and the lines of the first system is equal to unity. In this way let more lines be drawn so as to form a second system, so that the value of M for every reticulation formed by the intersection of the two systems of lines is unity. Finally, from every point of intersection of these reticulations let a line be drawn through the field, always coinciding in direction with the direction of magnetic force. 50. In this way the whole field will be filled with lines of magnetic force at regular intervals, and the properties of the electromagnetic field will be completely expressed by them. 4. First, if any closed curve be drawn in the field, the value of M for that curve will be expressed by the number of lines of force which pass through that closed curve. 2 NDLY. If this curve be a conducting circuit and be moved through the field, an electromotive force will act in it, represented by the rate of decrease of the number of lines passing through the curve. 3 RDLY. If a current be maintained in the circuit, the conductor will be acted on by forces tending to move it so as to increase the number of lines passing through it, and the amount of work done by these forces is equal to the current in the circuit multiplied by the number of additional lines. 40H. If a small plane circuit be placed in the field, and be free to turn, it will place its plane perpendicular to the lines of force. A small magnet will place itself with its axis in the direction of the lines of force. 5 THLY. If a long uniformly magnetized bar is placed in the field, each pole will be acted on by a force in the direction of the lines of force. The number of lines of force passing through unit of area is equal to the force acting on a unit pole multiplied by a coefficient depending on the magnetic nature of the medium, and called the coefficient of magnetic induction. In fluids and isotropic solids the value of this coefficient μ is the same in whatever direction the lines of force pass through the substance, but in crystallized, strained, and organized solids the value of mu may depend on the direction of the lines of force with respect to the axes of crystallization, strain, or growth. In all bodies mu is affected by temperature, and in iron it appears to diminish as the intensity of the magnetization increases. On magnetic equipotential surfaces. 51. If we explore the field with a uniformly magnetized bar, so long that one of its poles is in a very weak part of the magnetic field, then the magnetic forces will perform work on the other pole as it moves about the field. If we start from a given point, and move this pole from it to any other point, the work performed will be independent of the path of the pole between the 2 points, provided that no electric current passes between the different paths pursued by the pole. Hence, when there are no electric currents but only magnets in the field, we may draw a series of surfaces such that the work done in passing from one to another shall be constant whatever be the path pursued between them. Such surfaces are called equipotential surfaces, and in ordinary cases are perpendicular to the lines of magnetic force. If these surfaces are so drawn that, when a unit pole passes from any one to the next in order, unity of work is done, then the work done in any motion of a magnetic pole will be measured by the strength of the pole multiplied by the number of surfaces which it has passed through in the positive direction. 52. If there are circuits carrying electric currents in the field, then there will still be equipotential surfaces in the parts of the field external to the conductors carrying the currents, but the work done on a unit pole in passing from one to another will depend on the number of times which the path of the pole circulates round any of these currents. Hence the potential in each surface will have a series of values in arithmetical progression, differing by the work done in passing completely round one of the currents in the field. The equipotential surfaces will not be continuous closed surfaces, but some of them will be limited sheets, terminating in the electric circuit as the common edge or boundary. The number of these will be equal to the amount of work done on a unit pole in going round the current, and this by the ordinary measurement equals 4 pg, where gamma is the value of the current. These surfaces, therefore, are connected with the electric current as soap bubbles are connected with a ring in M. Plato's experiments. Every current gamma has 4 pg surfaces attached to it. These surfaces have the current for the common edge, and meet it at equal angles. The form of the surfaces in other parts depends on the presence of other currents and magnets, as well as on the shape of the circuit to which they belong. Part 3. General equations of the electromagnetic field. 53. Let us assume 3 rectangular directions in space as the axes of x, y, and z, and let all quantities having direction be expressed by their components in these 3 directions. Electrical currents, P, Q, R. 54. An electrical current consists in the transmission of electricity from one part of a body to another. Let the quantity of electricity transmitted in unit of time across unit of area perpendicular to the axis of x be called P, then P is the component of the current at that place in the direction of x. We shall use the letters P, Q, R to denote the components of the current per unit of area in the directions of x, y, z. Electrical displacements, F, G, H. 55. Electrical displacement consists in the opposite electrification of the sides of a molecule or particle of a body which may or may not be accompanied with transmission through the body. Let the quantity of electricity which would appear on the faces dy, dz of an element dx, dy, dz cut from the body be F, dy, dz, then F is the component of electric displacement parallel to x. We shall use F, G, H to denote the electric displacements parallel to x, y, z respectively. The variations of the electrical displacement must be added to the currents P, Q, R to get the total motion of electricity, which we may call P, Q, R, so that electromotive force, P, Q, R. 56. Let P, Q, R represent the components of the electromotive force at any point. Then P represents the difference of potential per unit of length in a conductor placed in the direction of x at the given point. We may suppose an indefinitely short wire placed parallel to x at a given point and touched, during the action of the force P, by 2 small conductors, which are then insulated and removed from the influence of the electromotive force. The value of P might then be ascertained by measuring the charge of the conductors. Thus if L be the length of the wire, the difference of potential at its ends will be place, and if C be the capacity of each of the small conductors, the charge on each will be corporal, since the capacities of moderately large conductors, measured on the electromagnetic system, are exceedingly small. Ordinary electromotive forces arising from electromagnetic actions could hardly be measured in this way. In practice, such measurements are always made with long conductors, forming closed or nearly closed circuits. Electromagnetic momentum, F, G, H. 57, let F, G, H represent the components of electromagnetic momentum at any point of the field, due to any system of magnets or currents. Then F is the total impulse of the electromotive force in the direction of X that would be generated by the removal of these magnets or currents from the field, that is, if P be the electromotive force at any instant during the removal of the system. Hence the part of the electromotive force which depends on the motion of magnets or currents in the field, or their alteration of intensity, is electromagnetic momentum of a circuit. 58, let S be the length of the circuit, then if we integrate round the circuit, we shall get the total electromagnetic momentum of the circuit, or the number of lines of magnetic force which pass through it, the variations of which measure the total electromotive force in the circuit. This electromagnetic momentum is the same thing to which Professor Faraday has applied the name of the electrotonic state. If the circuit be the boundary of the elementary area DIDS, then its electromagnetic momentum is. And this is the number of lines of magnetic force which pass through the area dy dz. Magnetic force, alpha, beta, gamma. 59, let alpha, beta, gamma represent the force acting on a unit magnetic pole placed at the given point resolved in the directions of x, y, and z. Coefficient of magnetic induction, mu. 60, let mu be the ratio of the magnetic induction in a given medium to that in air under an equal magnetizing force, then the number of lines of force in unit of area perpendicular to x will be ma. Mu is a quantity depending on the nature of the medium, its temperature, the amount of magnetization already produced, and in crystalline bodies varying with the direction. 61. Expressing the electric momentum of small circuits perpendicular to the three axes in this notation, we obtain the following. Equations of magnetic force. Equations of currents. 62. It is known from experiment that the motion of a magnetic pole in the electromagnetic field in a closed circuit cannot generate work unless the circuit which the pole describes passes round an electric current. Hence, except in the space occupied by the electric currents. A complete differential of phi, the magnetic potential. The quantity phi may be susceptible of an indefinite number of distinct values, according to the number of times that the exploring point passes round electric currents in its course, the difference between successive values of phi corresponding to a passage completely round a current of strength c being 4 pi c. Hence if there is no electric current, but if there is a current P. Similarly, we may call these the equations of current. Electromotive force in a circuit. 63. Let She be the electromotive force acting round the circuit A, then, where ds is the element of length, and the integration is performed round the circuit. Let the forces in the field be those due to the circuits A and B, then the electromagnetic momentum of R is where U and V are the currents in A and B, and hence, if there is no motion of the circuit A, where psi is a function of x, y, z, and t, which is indeterminate as far as regards the solution of the above equations, because the terms depending on it will disappear on integrating round the circuit. The quantity psi can always, however, be determined in any particular case when we know the actual conditions of the question. The physical interpretation of psi is that it represents the electric potential at each point of space. Electromotive force on a moving conductor. 64. Let a short straight conductor of length a, parallel to the axis of x, move with a velocity whose components are, and let its extremities slide along two parallel conductors with a velocity. Let us find the alteration of the electromagnetic momentum of the circuit of which this arrangement forms a part. In unit of time, the moving conductor has traveled distances along the directions of the three axes, and at the same time the lengths of the parallel conductors included in the circuit have each been increased by. Hence the quantity will be increased by the following increments. The total increment will therefore be, or, by the equations of magnetic force, 8. If P is the electromotive force in the moving conductor parallel to x referred to unit of length, then the actual electromotive force is par. And since this is measured by the decrement of the electromagnetic momentum of the circuit, the electromotive force due to motion will be 65. The complete equations of electromotive force on a moving conductor may now be written as follows. Equations of electromotive force. The first term on the right-hand side of each equation represents the electromotive force arising from the motion of the conductor itself. This electromotive force is perpendicular to the direction of motion and to the lines of magnetic force, and if a parallelogram be drawn whose sides represent in direction and magnitude the velocity of the conductor and the magnetic induction at that point of the field, then the area of the parallelogram will represent the electromotive force due to the motion of the conductor, and the direction of the force is perpendicular to the plane of the parallelogram. The second term in each equation indicates the effect of changes in the position or strength of magnets or currents in the field. The third term shows the effect of the electric potential psi. It has no effect in causing a circulating current in a closed circuit. It indicates the existence of a force urging the electricity to or from certain definite points in the field. Electric elasticity. 66. When an electromotive force acts on a dielectric, it puts every part of the dielectric into a polarized condition, in which its opposite sides are oppositely electrified. The amount of this electrification depends on the electromotive force and on the nature of the substance, and, in solids having a structure defined by axes, on the direction of the electromotive force with respect to these axes. In isotropic substances, if K is the ratio of the electromotive force to the electric displacement, we may write the equations of electric elasticity. Electric resistance. 67. When an electromotive force acts on a conductor, it produces a current of electricity through it. This effect is additional to the electric displacement already considered. In solids of complex structure, the relation between the electromotive force and the current depends on the direction through the solid. In isotropic substances, which alone we shall here consider, if ρ is the specific resistance referred to unit of volume, we may write the equations of electric resistance. Electric quantity. 68. Let E represent the quantity of free positive electricity contained in unit of volume at any part of the field. Then, since this arises from the electrification of the different parts of the field not neutralizing each other, we may write the equation of free electricity. 69. If the medium conducts electricity, then we shall have another condition, which may be called, as in hydrodynamics, the equation of continuity. 70. In these equations of the electromagnetic field we have assumed 20 variable quantities, namely, between these 20 quantities we have found 20 equations, viz. These equations are therefore sufficient to determine all the quantities which occur in them, provided we know the conditions of the problem. In many questions, however, only a few of the equations are required. Intrinsic energy of the electromagnetic field. 71. We have seen, 33, that the intrinsic energy of any system of currents is found by multiplying half the current in each circuit into its electromagnetic momentum. This is equivalent to finding the integral over all the space occupied by currents, where P, Q, R are the components of currents, and F, G, H the components of electromagnetic momentum. Substituting the values of P, Q, R, from the equations of currents, C, this becomes integrating by parts, and remembering that alpha, beta, gamma vanish at an infinite distance, the expression becomes where the integration is to be extended over all space. Referring to the equations of magnetic force, B, page 556, this becomes where alpha, beta, gamma are the components of magnetic intensity or the force on a unit magnetic pole, and μ, mb, mg are the components of the quantity of magnetic induction, or the number of lines of force in unit of area. In isotropic media the value of μ is the same in all directions, and we may express the result more simply by saying that the intrinsic energy of any part of the magnetic field arising from its magnetization is per unit of volume, where I is the magnetic intensity. 72. Energy may be stored up in the field in a different way, namely, by the action of electromotive force in producing electric displacement. The work done by a variable electromotive force, P, in producing a variable displacement, F, is got by integrating from P equals 0 to the given value of P. Since P equals Kf, equation, E, this quantity becomes. Hence the intrinsic energy of any part of the field, as existing in the form of electric displacement, is. The total energy existing in the field is therefore. The first term of this expression depends on the magnetization of the field, and is explained on our theory by actual motion of some kind. The second term depends on the electric polarization of the field, and is explained on our theory by strain of some kind in an elastic medium. 73. I have on a former occasion attempted to describe a particular kind of motion and a particular kind of strain, so arranged as to account for the phenomena. In the present paper I avoid any hypothesis of this kind, and in using such words as electric momentum and electric elasticity in reference to the known phenomena of the induction of currents and the polarization of dielectrics, I wish merely to direct the mind of the reader to mechanical phenomena which will assist him in understanding the electrical ones. All such phrases in the present paper are to be considered as illustrative, not as explanatory. 74. In speaking of the energy of the field, however, I wish to be understood literally. All energy is the same as mechanical energy, whether it exists in the form of motion or in that of elasticity, or in any other form. The energy in electromagnetic phenomena is mechanical energy. The only question is, where does it reside? On the old theories it resides in the electrified bodies, conducting circuits, and magnets, in the form of an unknown quality called potential energy, or the power of producing certain effects at a distance. On our theory it resides in the electromagnetic field, in the space surrounding the electrified and magnetic bodies, as well as in those bodies themselves, and is in two different forms, which may be described without hypothesis as magnetic polarization and electric polarization, or, according to a very probable hypothesis, as the motion and the strain of one and the same medium. 75. The conclusions arrived at in the present paper are independent of this hypothesis, being deduced from experimental facts of three kinds. 1. The induction of electric currents by the increase or diminution of neighboring currents according to the changes in the lines of force passing through the circuit. 2. The distribution of magnetic intensity according to the variations of a magnetic potential. 3. The induction, or influence, of statical electricity through dielectrics. We may now proceed to demonstrate from these principles the existence and laws of the mechanical forces which act upon electric currents, magnets, and electrified bodies placed in the electromagnetic field. Part 4. Mechanical actions in the field. Mechanical force on a movable conductor. 76. We have shown, sections 34 and 35, that the work done by the electromagnetic forces in aiding the motion of a conductor is equal to the product of the current in the conductor multiplied by the increment of the electromagnetic momentum due to the motion. Let a short straight conductor of length A move parallel to itself in the direction of x, with its extremities on two parallel conductors. Then the increment of the electromagnetic momentum due to the motion of A will be that due to the lengthening of the circuit by increasing the length of the parallel conductors will be the total increment is, which is by the equations of magnetic force, B, page 556. Let x be the force acting along the direction of x per unit of length of the conductor, then the work done is ZA delta x. Let C be the current in the conductor, and let P, Q, R be its components, then. Or, similarly, these are the equations which determine the mechanical force acting on a conductor carrying a current. The force is perpendicular to the current and to the lines of force, and is measured by the area of the parallelogram formed by lines parallel to the current and lines of force, and proportional to their intensities. Mechanical force on a magnet. 77. In any part of the field not traversed by electric currents, the distribution of magnetic intensity may be represented by the differential coefficients of a function which may be called the magnetic potential. When there are no currents in the field, this quantity has a single value for each point. When there are currents, the potential has a series of values at each point, but its differential coefficients have only one value, namely. Substituting these values of alpha, beta, gamma in the expression, equation 38, for the intrinsic energy of the field, and integrating by parts, it becomes. The expression indicates the number of lines of magnetic force which have their origin within the space V. Now a magnetic pole is known to us only as the origin or termination of lines of magnetic force, and a unit pole is one which has 4 pi lines belonging to it, since it produces unit of magnetic intensity at unit of distance over a sphere whose surface is 4 pi. Hence if m is the amount of free positive magnetism in unit of volume, the above expression may be written 4 pi m, and the expression for the energy of the field becomes. If there are two magnetic poles m1 and m2 producing potentials phi1 and phi2 in the field, then if m2 is moved a distance dx, and is urged in that direction by a force x, then the work done is x dx, and the decrease of energy in the field is. And these must be equal by the principle of conservation of energy. Since the distribution phi1 is determined by m1, and phi2 by m2, the quantities phi1 meter 1 and phi2 square meters will remain constant. It can be shown also, as Green has proved, essay, page 10, that so that a magnetic pole is urged in the direction of the lines of magnetic force with a force equal to the product of the strength of the pole and the magnetic intensity. 78. If a single magnetic pole, that is, one pole of a very long magnet, be placed in the field, the only solution of phi is where m1 is the strength of the pole, and r the distance from it. The repulsion between two poles of strength m1 and m2 is in air or any medium in which mu equals 1. This is simply, but in other media the force acting between two given magnetic poles is inversely proportional to the coefficient of magnetic induction for the medium. This may be explained by the magnetization of the medium induced by the action of the poles. Mechanical force on an electrified body. 79. If there is no motion or change of strength of currents or magnets in the field, the electromotive force is entirely due to variation of electric potential, and we shall have, section 65. Integrating by parts the expression, I, for the energy due to electric displacement, and remembering that P, Q, R vanish at an infinite distance, it becomes, or by the equation of free electricity, G, page 561. By the same demonstration as was used in the case of the mechanical action on a magnet, it may be shown that the mechanical force on a small body containing a quantity E2 of free electricity placed in a field whose potential arising from other electrified bodies is psi1, has for components. So that an electrified body is urged in the direction of the electromotive force with a force equal to the product of the quantity of free electricity and the electromotive force. If the electrification of the field arises from the presence of a small electrified body containing E1 of free electricity, the only solution of psi1 is where r is the distance from the electrified body. The repulsion between two electrified bodies E1, E2 is therefore measurement of electrostatic effects. 80. The quantities with which we have had to do have been hitherto expressed in terms of the electromagnetic system of measurement, which is founded on the mechanical action between currents. The electrostatic system of measurement is founded on the mechanical action between electrified bodies, and is independent of, and incompatible with, the electromagnetic system, so that the units of the different kinds of quantity have different values according to the system we adopt, and to pass from the one system to the other, a reduction of all the quantities is required. According to the electrostatic system, the repulsion between two small bodies charged with quantities eta1, eta2 of electricity is where r is the distance between them. Let the relation of the two systems be such that one electromagnetic unit of electricity contains V electrostatic units, then eta1 equals VE1 and eta2 equals VE2, and this repulsion becomes whence K, the coefficient of electric elasticity, in the medium in which the experiments are made, i.e., common air, is related to V, the number of electrostatic units in one electromagnetic unit, by the equation. The quantity V may be determined by experiment in several ways. According to the experiments of M.M. Weber and Kohlrausch. 81. It appears from this investigation, that if we assume that the medium which constitutes the electromagnetic field is, when dielectric, capable of receiving in every part of it an electric polarization, in which the opposite sides of every element into which we may conceive the medium divided are oppositely electrified, and if we also assume that this polarization or electric displacement is proportional to the electromotive force which produces or maintains it, then we can show that electrified bodies in a dielectric medium will act on one another with forces obeying the same laws as are established by experiment. The energy, by the expenditure of which electrical attractions and repulsions are produced, we suppose to be stored up in the dielectric medium which surrounds the electrified bodies, and not on the surface of those bodies themselves, which on our theory are merely the bounding surfaces of the air or other dielectric in which the true springs of action are to be sought. Note on the attraction of gravitation. 82. After tracing to the action of the surrounding medium both the magnetic and the electric attractions and repulsions, and finding them to depend on the inverse square of the distance, we are naturally led to inquire whether the attraction of gravitation, which follows the same law of the distance, is not also traceable to the action of a surrounding medium. Gravitation differs from magnetism and electricity in this, that the bodies concerned are all of the same kind, instead of being of opposite signs, like magnetic poles and electrified bodies, and that the force between these bodies is an attraction and not a repulsion, as is the case between like electric and magnetic bodies. The lines of gravitating force near two dense bodies are exactly of the same form as the lines of magnetic force near two poles of the same name, but whereas the poles are repelled, the bodies are attracted. Let E be the intrinsic energy of the field surrounding two gravitating bodies M1, M2, and let E be the intrinsic energy of the field surrounding two magnetic poles, M1, M2, equal in numerical value to M1, M2, and let X be the gravitating force acting during the displacement delta X, and X, the magnetic force. Now X and X are equal in numerical value, but of opposite signs, so that or, where alpha, beta, gamma are the components of magnetic intensity. If R be the resultant gravitating force, and R, the resultant magnetic force at a corresponding part of the field. Hence, the intrinsic energy of the field of gravitation must therefore be less wherever there is a resultant gravitating force. As energy is essentially positive, it is impossible for any part of space to have negative intrinsic energy. Hence those parts of space in which there is no resultant force, such as the points of equilibrium in the space between the different bodies of a system, and within the substance of each body, must have an intrinsic energy per unit of volume greater than where R is the greatest possible value of the intensity of gravitating force in any part of the universe. The assumption, therefore, that gravitation arises from the action of the surrounding medium in the way pointed out, leads to the conclusion that every part of this medium possesses, when undisturbed, an enormous intrinsic energy, and that the presence of dense bodies influences the medium so as to diminish this energy wherever there is a resultant attraction. As I am unable to understand in what way a medium can possess such properties, I cannot go any further in this direction in searching for the cause of gravitation. Part 5. Theory of condensers. Capacity of a condenser. 83. The simplest form of condenser consists of a uniform layer of insulating matter bounded by two conducting surfaces, and its capacity is measured by the quantity of electricity on either surface when the difference of potentials is unity. Let S be the area of either surface, or the thickness of the dielectric, and K its coefficient of electric elasticity. Then on one side of the condenser the potential is psi1 and on the other side psi1 plus 1, and within its substance. Since and therefore F is 0 outside the condenser, the quantity of electricity on its first surface equals SF, and on the second plus SF. The capacity of the condenser is therefore in electromagnetic measure. Specific capacity of electric induction, D. 84. If the dielectric of the condenser be air, then its capacity in electrostatic measure is, neglecting corrections arising from the conditions to be fulfilled at the edges. If the dielectric have a capacity whose ratio to that of air is D, then the capacity of the condenser will be hence. Where K0 is the value of K in air, which is taken for unity. Electric absorption. 85. When the dielectric of which the condenser is formed is not a perfect insulator, the phenomena of conduction are combined with those of electric displacement. The condenser, when left charged, gradually loses its charge, and in some cases, after being discharged completely, it gradually acquires a new charge of the same sign as the original charge, and this finally disappears. These phenomena have been described by Professor Faraday, Experimental Researches, Series 11, and by Mr. F. Jenkin, Report of Committee of Board of Trade on Submarine Cables, and may be classed under the name of electric absorption. 86. We shall take the case of a condenser composed of any number of parallel layers of different materials. If a constant difference of potentials between its extreme surfaces is kept up for a sufficient time till a condition of permanent steady flow of electricity is established, then each bounding surface will have a charge of electricity depending on the nature of the substances on each side of it. If the extreme surfaces be now discharged, these internal charges will gradually be dissipated, and a certain charge may reappear on the extreme surfaces if they are insulated, or, if they are connected by a conductor, a certain quantity of electricity may be urged through the conductor during the re-establishment of equilibrium. Let the thickness of the several layers of the condenser be alpha 1, alpha 2, and C. Let the values of K for these layers be respectively K1, K2, K3, and let where K is the electric elasticity of air, and alpha is the thickness of an equivalent condenser of air. Let the resistances of the layers be respectively R1, R2, and C. And let R1 plus R2 plus and C equals R be the resistance of the whole condenser, to a steady current through it per unit of surface. Let the electric displacement in each layer be F1, F2, and C. Let the electric current in each layer be P1, P2, and C. Let the potential on the first surface be psi1, and the electricity per unit of surface E1. Let the corresponding quantities at the boundary of the first and second surface be psi2 and E2, and so on. Then by equations, G, and, H. But by equations, E, and, F. After the electromotive force has been kept up for a sufficient time, the current becomes the same in each layer, and where psi is the total difference of potentials between the extreme layers. We have then, and, these are the quantities of electricity on the different surfaces. 87. Now let the condenser be discharged by connecting the extreme surfaces through a perfect conductor so that their potentials are instantly rendered equal, then the electricity on the extreme surfaces will be altered, but that on the internal surfaces will not have time to escape. The total difference of potentials is now. Whence if E1 is what E1 becomes at the instant of discharge. The instantaneous discharge is therefore the quantity which would be discharged by a condenser of air of the equivalent thickness A, and it is unaffected by the want of perfect insulation. 88. Now let us suppose the connection between the extreme surfaces broken, and the condenser left to itself, and let us consider the gradual dissipation of the internal charges. Let psi be the difference of potential of the extreme surfaces at any time t, then. But. Hence and by referring to the values of E1, E2 and C, we find. So that we find for the difference of extreme potentials at any time. 89. It appears from this result that if all the layers are made of the same substance, psi will be 0 always. If they are of different substances, the order in which they are placed is indifferent, and the effect will be the same whether each substance consists of one layer, or is divided into any number of thin layers and arranged in any order among thin layers of the other substances. Any substance, therefore, the parts of which are not mathematically homogeneous, though they may be apparently so, may exhibit phenomena of absorption. Also, since the order of magnitude of the coefficients is the same as that of the indices, the value of can never change sign, but must start from 0, become positive, and finally disappear. 90. Let NS next consider the total amount of electricity which would pass from the first surface to the second, if the condenser, after being thoroughly saturated by the current and then discharged, has its extreme surfaces connected by a conductor of resistance R. Let P be the current in this conductor, then, during the discharge. Integrating with respect to the time, and calling Q1, Q2, Q the quantities of electricity which traverse the different conductors. The quantities of electricity on the several surfaces will be. And since at last all these quantities vanish, we find. Whence or a quantity essentially positive, so that, when the primary electrification is in one direction, the secondary discharge is always in the same direction as the primary discharge. Part 6. ELECTROMAUNETIC Theory of Light. 91. At the commencement of this paper we made use of the optical hypothesis of an elastic medium through which the vibrations of light are propagated, in order to show that we have warrantable grounds for seeking, in the same medium, the cause of other phenomena as well as those of light. We then examined electromagnetic phenomena, seeking for their explanation in the properties of the field which surrounds the electrified or magnetic bodies. In this way we arrived at certain equations expressing certain properties of the electromagnetic field. We now proceed to investigate whether these properties of that which constitutes the electromagnetic field, deduced from electromagnetic phenomena alone, are sufficient to explain the propagation of light through the same substance. 92. Let us suppose that a plane wave whose direction cosines are L, M, N is propagated through the field with a velocity v, then all the electromagnetic functions will be functions of the equations of magnetic force, B, page 556, will become. If we multiply these equations respectively by L, M, N, and add, we find. Which shows that the direction of the magnetization must be in the plane of the wave. 93. If we combine the equations of magnetic force, B, with those of electric currents, C, and put for brevity. If the medium in the field is a perfect dielectric, there is no true conduction, and the currents P, Q, R, are only variations in the electric displacement, or, by the equations of total currents, A. But these electric displacements are caused by electromotive forces, and by the equations of electric elasticity, E. These electromotive forces are due to the variations either of the electromagnetic or the electrostatic functions, as there is no motion of conductors in the field, so that the equations of electromotive force, D, are 94. Combining these equations, we obtain the following. If we differentiate the third of these equations with respect to y, and the second with respect to z, and subtract, j and psi disappear, and by remembering the equations, B, of magnetic force, the results may be written. 95. If we assume that alpha, beta, gamma are functions of lux plus my plus nz, Vt equals W, the first equation becomes. Or, the other equations give the same value for V, so that the wave is propagated in either direction with a velocity V. This wave consists entirely of magnetic disturbances, the direction of magnetization being in the plane of the wave. No magnetic disturbance whose direction of magnetization is not in the plane of the wave can be propagated as a plane wave at all. Hence magnetic disturbances propagated through the electromagnetic field agree with light in this, that the disturbance at any point is transverse to the direction of propagation, and such waves may have all the properties of polarized light. 96. The only medium in which experiments have been made to determine the value of K is air, in which mu equals 1, and therefore, by equation 46. By the electromagnetic experiments of M.M. Weber and Kohlrausch *. V equals 310,740,000 meters per second. Is the number of electrostatic units in one electromagnetic unit of electricity, and this, according to our result, should be equal to the velocity of light in air or vacuum. The velocity of light in air, by M. Fizeau's experiments, is, according to the more accurate experiments of M. Foucault, the velocity of light in the space surrounding the Earth, deduced from the coefficient of aberration and the received value of the radius of the Earth's orbit, is 97, hence the velocity of light deduced from experiment agrees sufficiently well with the value of V deduced from the only set of experiments we as yet possess. The value of versus was determined by measuring the electromotive force with which a condenser of known capacity was charged, and then discharging the condenser through a galvanometer, so as to measure the quantity of electricity in it in electromagnetic measure. The only use made of light in the experiment was to see the instruments. The value of V found by M. Foucault was obtained by determining the angle through which a revolving mirror turned, while the light reflected from it went and returned along a measured course. No use whatever was made of electricity or magnetism. The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. 98. Let us now go back upon the equations in 94, in which the quantities J and psi occur, to see whether any other kind of disturbance can be propagated through the medium depending on these quantities which disappeared from the final equations. If we determine chi from the equation, and f, g, h, from the equations, then, and the equations in 94, become of the form. Differentiating the three equations with respect to x, y, and z, and adding, we find that, and that. Hence the disturbances indicated by f, g, f, are propagated with the velocity through the field, and since the resultant of these disturbances is in the plane of the wave. 99. The remaining part of the total disturbances f, g, h being the part depending on chi, is subject to no condition except that expressed in the equation. If we perform the operation nabla-2 on this equation, it becomes, since the medium is a perfect insulator, E, the free electricity, is immovable, and therefore is a function of x, y, z, and the value of J is either constant or zero, or uniformly increasing or diminishing with the time, so that no disturbance depending on J can be propagated as a wave. 100. The equations of the electromagnetic field, deduced from purely experimental evidence, show that transversal vibrations only can be propagated. If we were to go beyond our experimental knowledge and to assign a definite density to a substance which we should call the electric fluid, and select either vitreous or resinous electricity as the representative of that fluid, then we might have normal vibrations propagated with a velocity depending on this density. We have, however, no evidence as to the density of electricity, as we do not even know whether to consider vitreous electricity as a substance or as the absence of a substance. Hence electromagnetic science leads to exactly the same conclusions as optical science with respect to the direction of the disturbances which can be propagated through the field. Both affirm the propagation of transverse vibrations, and both give the same velocity of propagation. On the other hand, both sciences are at a loss when called on to affirm or deny the existence of normal vibrations. Relation between the index of refraction and the electromagnetic character of the substance. 101. The velocity of light in a medium, according to the undulatory theory, is where I is the index of refraction and V0 is the velocity in vacuum. The velocity, according to the electromagnetic theory, is where, by equations, and 7. 1. Hence, or the specific inductive capacity is equal to the square of the index of refraction divided by the coefficient of magnetic induction. Propagation of electromagnetic disturbances in a crystallized medium. 102. Let Ns now calculate the conditions of propagation of a plane wave in a medium for which the values of k and mu are different in different directions. As we do not propose to give a complete investigation of the question in the present imperfect state of the theory as extended to disturbances of short period, we shall assume that the axes of magnetic induction coincide in direction with those of electric elasticity. 103. Let the values of the magnetic coefficient for the three axes be lambda, mu, v, then the equations of magnetic force, B, become. The equations of electric currents, C, remain as before. The equations of electric elasticity, E, will be where 4 pi A2, 4 pi B2, and 4 pi C2 are the values of k for the axes of x, y, z. Combining these equations with A and D, we get equations of the form 104, if L, M, N are the direction cosines of the wave, and V its velocity, and if then F, G, H, and psi will be functions of W. And if we put f, g, h, for the second differentials of these quantities with respect to w, the equations will be. If we now put, we shall find, with two similar equations for g, and h, hence either. Or. The third supposition indicates that the resultant of f, g, h, is in the direction normal to the plane of the wave, but the equations do not indicate that such a disturbance, if possible, could be propagated, as we have no other relation between psi and f, g, h. The solution V equals 0 refers to a case in which there is no propagation. Asterisk the solution U equals 0 gives two values for V2 corresponding to values of f, g, h, which are given by the equations. 105. The velocities along the axes are as follows. Now we know that in each principal plane of a crystal the ray polarized in that plane obeys the ordinary law of refraction, and therefore its velocity is the same in whatever direction in that plane it is propagated. If polarized light consists of electromagnetic disturbances in which the electric displacement is in the plane of polarization, then if, on the contrary, the electric displacements are perpendicular to the plane of polarization. We know, from the magnetic experiments of Faraday, Plucker, and C, that in many crystals lambda, mu, v are unequal. The experiments of Knobloch on electric induction through crystals seem to show that A, B and C may be different. The inequality, however, of lambda, mu, v is so small that great magnetic forces are required to indicate the difference, and the differences do not seem of sufficient magnitude to account for the double refraction of the crystals. On the other hand, experiments on electric induction are liable to error on account of minute flaws, or portions of conducting matter in the crystal. Further experiments on the magnetic and dielectric properties of crystals are required before we can decide whether the relation of these bodies to magnetic and electric forces is the same, when these forces are permanent as when they are alternating with the rapidity of the vibrations of light. Relation between electric resistance and transparency. 106. If the medium, instead of being a perfect insulator, is a conductor whose resistance per unit of volume is ρ, then there will be not only electric displacements, but true currents of conduction in which electrical energy is transformed into heat, and the undulation is thereby weakened. To determine the coefficient of absorption, let us investigate the propagation along the axis of x of the transverse disturbance g. By the former equations, if g is of the form, we find that, where v is the velocity of light in air, and I is the index of refraction, the proportion of incident light transmitted through the thickness x is. Let R be the resistance in electromagnetic measure of a plate of the substance whose thickness is x, breadth b, and length l, then 107. Most transparent solid bodies are good insulators, whereas all good conductors are very opaque. Electrolytes allow a current to pass easily and yet are often very transparent. We may suppose, however, that in the rapidly alternating vibrations of light, the electromotive forces act for so short a time that they are unable to effect a complete separation between the particles in combination, so that when the force is reversed the particles oscillate into their former position without loss of energy. Gold, silver, and platinum are good conductors, and yet when reduced to sufficiently thin plates they allow light to pass through them. If the resistance of gold is the same for electromotive forces of short period as for those with which we make experiments, the amount of light which passes through a piece of gold leaf, of which the resistance was determined by Mr. C. Hocken, would be only 10 to 30 of the incident light, a totally imperceptible quantity. I find that between of green light gets through such gold leaf. Much of this is transmitted through holes and cracks. There is enough, however, transmitted through the gold itself to give a strong green hue to the transmitted light. This result cannot be reconciled with the electromagnetic theory of light, unless we suppose that there is less loss of energy when the electromotive forces are reversed with the rapidity of the vibrations of light than when they act for sensible times, as in our experiments. Absolute values of the electromotive and magnetic forces called into play in the propagation of light. 108. If the equation of propagation of light is, the electromotive force will be, and the energy per unit of volume will be, where P represents the greatest value of the electromotive force. Half of this consists of magnetic and half of electric energy. The energy passing through a unit of area is, so that, where V is the velocity of light, and W is the energy communicated to unit of area by the light in a second. According to Pouillet's data, as calculated by Professor W. Thompson *, the mechanical value of direct sunlight at the Earth is 83.4 foot-pounds per second per square foot. This gives the maximum value of P in direct sunlight at the Earth's distance from the Sun. P equals 60 million, or about 600 Daniell's cells per meter. At the Sun's surface the value of P would be about 13,000 Daniell's cells per meter. At the Earth the maximum magnetic force would be 193. At the Sun it would be 413. These electromotive and magnetic forces must be conceived to be reversed twice in every vibration of light. That is, more than 1,000 million times in a second. Point 7. Calculation of the coefficients of electromagnetic induction. General methods. 109. The electromagnetic relations between two conducting circuits, A and B, depend upon a function m of their form and relative position, as has been already shown. M may be calculated in several different ways, which must of course all lead to the same result. First method. M is the electromagnetic momentum of the circuit B when it carries a unit current, or where F, G, H are the components of electromagnetic momentum due to a unit current in A, and D is an element of length of B, and the integration is performed round the circuit of B. To find F, G, H, we observe that by B and C, with corresponding equations for G and H, P, Q, and R, being the components of the current in A. Now if we consider only a single element ds of A, we shall have, and the solution of the equation gives, where ρ is the distance of any point from ds. Hence where θ is the angle between the directions of the two elements ds, ds, and ρ is the distance between them, and the integration is performed round both circuits. In this method we confine our attention during integration to the two linear circuits alone. 110. Second method. M is the number of lines of magnetic force which pass through the circuit B when it carries a unit current, or where Ma, Mb, Mg are the components of magnetic induction due to unit current in A, S, is a surface bounded by the current B, and L, M, N are the direction cosines of the normal to the surface, the integration being extended over the surface. We may express this in the form where ds is an element of the surface bounded by B, ds is an element of the circuit A, ρ is the distance between them, θ and θ are the angles between ρ and ds and between ρ and the normal to ds, respectively, and phi is the angle between the planes in which θ and θ are measured. The integration is performed round the circuit A and over the surface bounded by B. This method is most convenient in the case of circuits lying in one plane, in which case sin θ equals 1, and sin phi equals 1. 111. Third method. M is that part of the intrinsic magnetic energy of the whole field which depends on the product of the currents in the two circuits, each current being unity. Let alpha, beta, gamma be the components of magnetic intensity at any point due to the first circuit, alpha, beta, gamma, the same for the second circuit, then the intrinsic energy of the element of volume dV of the field is the part which depends on the product of the currents is. Hence, if we know the magnetic intensities I and I, due to the unit current in each circuit, we may obtain M by integrating over all space, where theta is the angle between the directions of I and I. Application to a coil. 112. To find the coefficient, M, of mutual induction between two circular linear conductors in parallel planes, the distance between the curves being everywhere the same, and small compared with the radius of either. If r be the distance between the curves, and the radius of either, then when r is very small compared with a, we find by the second method, as a first approximation. To approximate more closely to the value of m, let r and the1 be the radii of the circles, and b the distance between their planes, then we obtain m by considering the following conditions. First, m must fulfill the differential equation. This equation being true for any magnetic field symmetrical with respect to the common axis of the circles, cannot of itself lead to the determination of m as a function of a, a1, and b. We therefore make use of other conditions. 2 ndly. The value of m must remain the same when r and the 1 are exchanged. 3 rdly. The first two terms of m must be the same as those given above. M may thus be expanded in the following series. 113. We may apply this result to find the coefficient of self-induction, L, of a circular coil of wire whose section is small compared with the radius of the circle. Let the section of the coil be a rectangle, the breadth in the plane of the circle being c, and the depth perpendicular to the plane of the circle being b. Let the mean radius of the coil be a, and the number of windings n. Then we find, by integrating, where m, x, y, z, means the value of m for the two windings whose coordinates are x, y, and z, respectively, and the integration is performed first with respect to x and y over the rectangular section, and then with respect to x and y over the same space. Here equals mean radius of the coil. R equals diagonal of the rectangular section, theta equals angle between r and the plane of the circle. N equals number of windings. The logarithms are Napierian, and the angles are in circular measure. In the experiments made by the Committee of the British Association for determining a standard of electrical resistance, a double coil was used, consisting of two nearly equal coils of rectangular section, placed parallel to each other, with a small interval between them. The value of L for this coil was found in the following way. The value of L was calculated by the preceding formula for 6 different cases, in which the rectangular section considered has always the same breadth, while the depth was, and n equals 1 in each case. We calculate the coefficient of mutual induction M, AC, of the two coils thus. Then if N1 is the number of windings in the coil A and N2 in the coil C, the coefficient of self-induction of the two coils together is 114. These values of L are calculated on the supposition that the windings of the wire are evenly distributed so as to fill up exactly the whole section. This, however, is not the case, as the wire is generally circular and covered with insulating material. Hence the current in the wire is more concentrated than it would have been if it had been distributed uniformly over the section, and the currents in the neighboring wires do not act on it exactly as such a uniform current would do. The corrections arising from these considerations may be expressed as numerical quantities, by which we must multiply the length of the wire, and they are the same whatever be the form of the coil. Let the distance between each wire and the next, on the supposition that they are arranged in square order, be d, and let the diameter of the wire be d, then the correction for diameter of wire is. The correction for the 8 nearest wires is. For the 16 in the next row. These corrections being multiplied by the length of wire and added to the former result, give the true value of L, considered as the measure of the potential of the coil on itself for unit current in the wire when that current has been established for some time, and is uniformly distributed through the section of the wire. 115. But at the commencement of a current and during its variation the current is not uniform throughout the section of the wire, because the inductive action between different portions of the current tends to make the current stronger at one part of the section than at another. When a uniform electromotive force P arising from any cause acts on a cylindrical wire of specific resistance ρ, we have where F is got from the equation, R being the distance from the axis of the cylinder. Let one term of the value of f be of the form trn, where t is a function of the time, then the term of p which produced it is of the form. Hence if we write the total counter current of self-induction at any point is from t equals 0 to t equals infinity. From t equals 0 to equals infinity. Also if L be the length of the wire, and R its resistance. And if C be the current when established in the wire, the total counter current may be written. Now if the current instead of being variable from the center to the circumference of the section of the wire had been the same throughout, the value of F would have been where gamma is the current in the wire at any instant, and the total counter current would have been hence, or the value of L which must be used in calculating the self-induction of a wire for variable currents is less than that which is deduced from the supposition of the current being constant throughout the section of the wire by where L is the length of the wire, and mu is the coefficient of magnetic induction for the substance of the wire. 116. The dimensions of the coil used by the Committee of the British Association in their experiments at King's College in 1864 were as follows. The value of L derived from the first term of the expression is 437,440 meters. The correction depending on the radius not being infinitely great compared with the section of the coil as found from the second term is 7,345 meters. This value of L was employed in reducing the observations, according to the method explained in the report of the committee. The correction depending on L varies as the square of the velocity. The results of 16 experiments to which this correction had been applied, and in which the velocity varied from 100 revolutions in 17 seconds to 100 in 77 seconds, were compared by the method of least squares to determine what further correction depending on the square of the velocity should be applied to make the outstanding errors a minimum. The result of this examination showed that the calculated value of L should be multiplied by 10618 to obtain the value of L, which would give the most consistent results. The value of L calculated from the dimensions of the coil is probably much more accurate than either of the other determinations. Elektrodynamische Maßbestimmungen. Leipzig Trans. Volume 1 1849, and Taylor's Scientific Memoirs, Volume vs. Art. XIV. Explicar tentator quomodo fiat ut lucis planum polarizationis per vias electricas vel magneticas declintur. Halles Saxonum, 1858. On the possible density of the luminiferous medium, and on the mechanical value of a cubic mile of sunlight, Transactions of the Royal Society of Edinburgh, 1854, page 57. Experimental Researches, Series 19. Comps Rendus, 1856, second half year, page 529, and 1857, first half year, page 1209. Proceedings of the Royal Society, June 1856 and June 1861. Faraday, Experimental Researches, Series 11. Mossotti, Mem. Della Soc. Italiana, Modena, Volume 24, Part 2, page 49. Faraday, Experimental Researches, 1233–1250. Reports of British Association, 1859, page 218, and Report of Committee of Board of Trade on Submarine Cables, pp. 136 and 464. As, for instance, the composition of glue, treacle, and C, of which small plastic figures are made, which after being distorted gradually recover their shape. Conservation of Force, Physical Society of Berlin, 1847, and Taylor's Scientific Memoirs, 1853, page 114. Reports of the British Association, 1848, Philosophical Magazine, December 1851. Philosophical Magazine, May 1846, or Experimental Researches, 3, page 447. Lagrange, Mech. Anal, 2, 2, section 5. Experimental Researches, Series 1, IX. Annales de Chimie, Sir. 3, 34, 1852. Page 64. Experimental Researches, Series 160 and C. In those circumstances the values of X and Y found in Art. 44 require modification before being inserted in equation 24. This has been pointed out by Lord Rayleigh, who employed the method described in the text in his second determination of the British unit of resistance in absolute measure. See the Philosophical Transactions, 1882, Part 2. pp. 677, 678. Asterisk, On Physical Lines of Force, Philosophical Magazine, 1861-62. In this volume page 451. Asterisk, Since this paper was communicated to the Royal Society, I have seen a paper by M. Gorgon in the Annales de Chimie for 1864, in which he has deduced the phenomena of electric absorption and secondary discharge from the theory of compound condensers. Leipzig Transactions, Volume Versus, 1857. Page 260, or Poggendorf's Annalen, August 1856, page 10. Comptes Rendus, Volume 29, 1849. Page 90. Ibid. Volume LV, 1862. pp. 501, 792. Asterisk, Although it is not expressly stated in the text, it should be noticed that in finding equations 91 and 92, the quantity psi is put equal to 0. See section 98 and also the corresponding treatment of this subject in the Electricity and Magnetism E, section 796. It may be observed that the equations referred to in the table given in section 105 may perhaps be more readily understood from a different mode of elimination. If we write, it is readily seen that, with similar expressions for G, H, from these we readily obtain by reasoning similar to that in section 104, the equation corresponding to 86, viz. This form of the equation agrees with that given in the Electricity and Magnetism E, section 797. By means of this equation the equations 91 and 92 readily follow when psi equals 0. The ratios of F, G, H, for any direction of propagation may also be determined. Philosophical Magazine, 1852. Transactions of the Royal Society of Edinburgh, 1854, Mechanical Energies of the Solar System. The horizontal magnetic force at Q is about 176 in metrical units. British Association Reports, 1863, page 169. From the Philosophical Magazine, volume 27, asterisk 26, on the calculation of the equilibrium and stiffness of frames. The theory of the equilibrium and deflections of frameworks subjected to the action of forces is sometimes considered as more complicated than it really is, especially in cases in which the framework is not simply stiff, but is strengthened, or weakened as it may be, by additional connecting pieces. I have therefore stated a general method of solving all such questions in the least complicated manner. The method is derived from the principle of conservation of energy, and is referred to in Lamé's-Lecon's sur l'élasticité, Lecon 7 as Clapeyron's theorem, but I have not yet seen any detailed application of it. If such questions were attempted, especially in cases of 3 dimensions, by the regular method of equations of forces, every point would have 3 equations to determine its equilibrium, so as to give 3 equations between E unknown quantities, if S be the number of points and E the number of connections. There are, however, 6 equations of equilibrium of the system which must be fulfilled necessarily by the forces, on account of the equality of action and reaction in each piece. Hence, if the effect of any external force will be definite in producing tensions or pressures in the different pieces, but if E greater than 3/6, these forces will be indeterminate. This indeterminateness is got rid of by the introduction of a system of E equations of elasticity connecting the force in each piece with the change in its length. In order, however, to know the changes of length, we require to assume 3 displacements of the S points. 6 of these displacements, however, are equivalent to the motion of a rigid body, so that we have 3/6 displacements of points, E extensions and E forces to determine from 3s6 equations of forces, equations of extensions, and E equations of elasticity, so that the solution is always determinate. The following method enables us to avoid unnecessary complexity by treating separately all pieces which are additional to those required for making the frame stiff, and by proving the identity in form between the equations of forces and those of extensions by means of the principle of work. On the stiffness of frames. Geometrical definition of a frame. A frame is a system of lines connecting a number of points. A stiff frame is one in which the distance between any 2 points cannot be altered without altering the length of one or more of the connecting lines of the frame. A frame of S points in space requires in general 3s6 connecting lines to render it stiff. In those cases in which stiffness can be produced with a smaller number of lines, certain conditions must be fulfilled, rendering the case one of a maximum or minimum value of one or more of its lines. The stiffness of such frames is of an inferior order, as a small disturbing force may produce a displacement infinite in comparison with itself. A frame of S points in a plane requires in general two S3 connecting lines to render it stiff. A frame of S points in a line requires S1 connecting lines. A frame may be either simply stiff, or it may be self-strained by the introduction of additional connecting lines having tensions or pressures along them. In a frame which is simply stiff, the forces in each connecting line arising from the application of a force of pressure or tension between any 2 points of the frame may be calculated either by equations of forces, or by drawing diagrams of forces according to known methods. In general, the lines of connection in one part of the frame may be affected by the action of this force, while those in other parts of the frame may not be so affected. Elasticity and extensibility of a connecting piece. Let E be the extension produced in a piece by tension unity acting in it, then E may be called its extensibility. Its elasticity, that is, the force required to produce extension unity, will be. We shall suppose that the effect of pressure in producing compression of the piece is equal to that of tension in producing extension, and we shall use E indifferently for extensibility and compressibility. Work done against elasticity. Since the extension is proportional to the force, the whole work done will be the product of the extension and the mean value of the force, or if X is the extension and F the force. When the piece is inextensible, or E equals 0, then all the work applied at one end is transmitted to the other, and the frame may be regarded as a machine whose efficiency is perfect. Hence the following theorem. If P be the tension of the piece due to a tension unity between the points B and C, then an extension unity taking place in A will bring B and C nearer by a distance P. For let X be the tension and X the extension of A, Y the tension and Y the extension of the line BC, then supposing all the other pieces inextensible, no work will be done except in stretching A, or. But X equals Py, therefore Y equals Px, which was to be proved. Problem I. A tension F is applied between the points B and C of a frame which is simply stiff. To find the extension of the line joining DAD, all the pieces except a being inextensible, the extensibility of a being E. Determine the tension in each piece due to unit tension between B and C, and let P be the tension in A due to this cause. Determine also the tension in each piece due to unit tension between D and E, and let Y be the tension in the piece A due to this cause. Then the actual tension of A is Fp, and its extension is EFP, and the extension of the line D due to this cause is FEPQ by the last theorem. Core. If the other pieces of the frame are extensible, the complete value of the extension in D due to a tension F in BC is, where sigma, EPQ, means the sum of the products of EPQ, which are to be found for each piece in the same way as they were found for A. The extension of the line BC due to a tension F in BC itself will be sigma, EP2, may therefore be called the resultant extensibility along BC. Problem 2. A tension F is applied between B and C. To find the extension between D and E when the frame is not simply stiff, but has additional pieces R, S, T, and C, whose elasticities are known. Let P and Q, as before, be the tensions in the piece due to unit tensions in BC and D, and let R, S, T, and C be the tensions in A due to unit tension in R, S, T, and C. Also let R, S, T be the tensions of R, S, T, and ρ, sigma, tau their extensibilities. Then the tension A, the extension of A, the extension of R, extension of S, extension of T, also extension of D, the extension required. Here we have as many equations to determine R, S, T, and C, as there are of these unknown quantities, and by the last equation we determine X the extension of D from F the tension in BC. Thus, if there is only one additional connection R, we find. And, if there are two additional connections R and S, with elasticities ρ and sigma. The expressions for the extensibility, when there are many additional pieces, are of course very complicated. It will be observed, however, that P and Q always enter into the equations in the same way, so that we may establish the following general theorem. The extension in BC, due to unity of tension along D, is always equal to the tension in D due to unity of tension in BC. Hence we have the following method of determining the displacement produced at any joint of a frame due to forces applied at other joints. First, select as many pieces of the frame as are sufficient to render all its points stiff. Call the remaining pieces R, S, T, and C. Second, find the tension on each piece due to unit of tension in the direction of the force proposed to be applied. Call this the value of P for each piece. Third, find the tension on each piece due to unit of tension in the direction of the displacement to be determined. Call this the value of Q for each piece. Fourth, find the tension on each piece due to unit of tension along R, S, T, and C, the additional pieces of the frame. Call these the values of R, S, T, and C, for each piece. Fifth, find the extensibility of each piece and call it E, those of the additional pieces being rho, sigma, tau, and C. Sixth, R, S, T, and C are to be determined from the equations. As many equations as there are quantities to be found. Seventh, X, the extension required, is then found from the equation. In structures acted on by weights in which we wish to determine the deflection at any point, we may regard the points of support as the extremities of pieces connecting the structure with the center of the earth, and if the supports are capable of resisting a horizontal thrust, we must suppose them connected by a piece of equivalent elasticity. The deflection is then the shortening of a piece extending from the given point to the center of the earth. Example, thus in a triangular or Warren girder of length L, depth D, with a load W placed at a distance from one end, 0, to find the deflection at a point distant B from the same end, due to the yielding of a piece of the boom whose extensibility is E, distant X from the same end. The pressure of the support at and if X is less than A, the force at X will be or. If X is greater than A. Similarly, if X is less than B. But if X is greater than B, the deflection due to X is therefore WPQ, where the proper values of P and Q must be taken according to the relative position of A, B, and X. If A, B, L, X represent the number of the respective pieces, reckoning from the beginning and calling the first joint 0, the second joint and the piece opposite 1, and C, and if L be the length of each piece, and the extensibility of each piece equals E, then the deflection of B due to W at A will be, by summation of series. This is the deflection due to the yielding of all the horizontal pieces. The greater the number of pieces, the less is the importance of the last term. Let the inclination of the pieces of the web be A, then the force on a piece between 0 and A is or. And, also, if E be the extensibility of a piece of the web, we have to sum W sigma Ec, to get the deflection due to the yielding of the web. Owing to an oversight, this paper is out of its proper place. It should have been immediately before the memoir on the electromagnetic field. Number 25. Index to Volume 1.